Imagine yourself drifting silently in the vastness of space. Before you, a galaxy spins a luminous whirlpool of billions of stars, gas and dust. The core glows brilliantly, surrounded by spiraling arms stretching out like cosmic ribbons. It's a mesmerizing dance of light and motion, held together by a gravitational force so immense it defies comprehension. Yet, hidden within this stunning spectacle is an enigma. The visible elements of the galaxy stars, planets and nebulae account for only a fraction of the mass needed to sustain this intricate ballet. What is holding these celestial bodies together? What invisible force anchors the galaxy's swirling arms, ensuring it doesn't fly apart? This is the mystery of dark matter, the unseen framework of the universe. It doesn't emit light or energy, making it undetectable by traditional telescopes. Yet its gravitational pull shapes galaxies, clusters, and the universe itself. It is the scaffolding upon which the cosmos is built. The idea of dark matter arose when astronomers noticed discrepancies between what they could see and the behavior of galaxies. In the 1930s, Fritz Zwicky, a Swiss astrophysicist, observed that galaxies in the Coma cluster were moving faster than expected. By applying Newtonian physics, he calculated that visible matter alone couldn't generate enough gravity to hold the cluster together. There had to be some missing mass providing the necessary gravitational glue. Decades later, Vera Rubin and Kent Ford confirmed this phenomenon within individual galaxies. Studying the rotation curves of spiral galaxies, they discovered something astonishing. Stars on the outer edges of galaxies were moving just as fast as those near the center. According to the laws of gravity, this was impossible unless there was an unseen mass extending far beyond the visible boundaries. This realization that most of the universe's mass is invisible reshaped our understanding of the cosmos. Today, scientists estimate that dark matter constitutes roughly 27% of the universe, dwarfing the mere 5% made up of ordinary matter. The rest, even more mysterious, is dark energy. The invisibility of dark matter sets the stage for one of science's greatest pursuits. It's a riddle that challenges the boundaries of our knowledge, compelling us to peer deeper into the fabric of reality with the visible universe. And what does its existence mean for our understanding of life, existence, and everything in between? The hunt for dark matter isn't just about solving an abstract puzzle. It's about uncovering the fundamental truths of the universe. If we can understand this invisible force, we might unlock secrets about how galaxies form, why the universe expands as it does, and perhaps even glimpse the forces that shape the cosmos in its infancy. This is the unseen force shaping our universe. It surrounds us, permeates us, and holds the cosmos together. To understand dark matter is to understand the universe itself. And so, the quest begins with questions as vast and profound as the galaxies swirling in the night sky. To uncover the presence of something unseen, scientists rely on the subtle traces it leaves behind. One of the most compelling pieces of indirect evidence for dark matter comes from the phenomenon of gravitational lensing, a striking consequence of Einstein's theory of general relativity. Gravitational lensing occurs when the gravity of a massive object, like a galaxy or cluster of galaxies, bends the path of light from a more distant source. This bending creates distorted, magnified, or even multiple images of the background object, much like a glass lens does. When astronomers measure the extent of this lensing, they find something peculiar. The visible mass of the galaxy or cluster is far too small to account for the degree of light bending. The gravitational pull needed to create these effects is immense, far greater than what observable matter could produce. This discrepancy points to the presence of an unseen mass surrounding and permeating these galaxies. Dark matter, though invisible, exerts a gravitational influence that reveals itself through these cosmic distortions, allowing astronomers to see its effects, even if they can't directly observe the matter itself. Another key piece of evidence for dark matter comes from the rotation curves of galaxies, graphs showing the velocity of stars and gas as a function of their distance from the galactic center. In a galaxy governed solely by the visible matter, you'd expect the stars further from the center to orbit more slowly, similar to how planets in our solar system move. This is because gravity weakens with distance, and the mass producing the gravitational pull would primarily reside in the dense, star-filled core. However, observations tell a very different story. When Vera Rubin and her colleagues measured the rotation speeds of stars in spiral galaxies, they found that these velocities remain nearly constant, even at great distances from the galactic center. This flat rotation curve implies the existence of a vast, unseen halo of mass extending far beyond the visible stars. Without this invisible matter, the stars at the outskirts of the galaxy should be flung off into space, unable to maintain their high velocities. The logical conclusion: a massive halo of dark matter envelops the galaxy, providing the necessary gravitational pull to stabilize the outer stars. Gravitational lensing and galaxy rotation curves are two sides of the same coin, each offering a glimpse of dark matter's pervasive role in the universe. Together, they form a consistent narrative. There is far more to the cosmos than meets the eye. Dark matter doesn't just shape individual galaxies, it influences entire clusters. In fact, gravitational lensing studies of massive galaxy clusters reveal intricate maps of dark matter's distribution, showing how it congregates in enormous structures that act as the scaffolding of the universe. These clusters themselves are stabilized by dark matter's immense gravitational influence, just as individual galaxies are. These indirect observations highlight the ingenuity of science. Without the ability to see or directly interact with dark matter, researchers rely on its gravitational footprints to trace its existence. Each distorted image, an unexpected star velocity, is a clue, bringing us closer to understanding the unseen. While the nature of dark matter remains elusive, these pieces of evidence confirm its presence beyond reasonable doubt. Dark matter is not a theoretical abstraction, it is a tangible force shaping the universe. Its detection may be indirect, but its impact on the cosmos is undeniable. Dark matter is enigmatic not just because it's invisible to the naked eye, but because it interacts so weakly, if at all, with ordinary matter. This makes its direct detection an extraordinary challenge, requiring experiments of unparalleled sensitivity and precision. Despite these hurdles, scientists have devised ingenious methods and cutting-edge facilities to attempt what might seem impossible: capturing evidence of dark matter directly. The Large Hadron Collider, LHC, located at CERN in Geneva, is the world's most powerful particle accelerator. With its 27-kilometer ring buried underground, the LHC smashes protons together at nearly the speed of light, creating conditions similar to those that existed moments after the Big Bang. These high-energy collisions produce a cascade of particles, which are meticulously analyzed by detectors to search for anomalies, potential fingerprints of dark matter. Scientists at the LHC are particularly interested in detecting WIMPs, or weakly interacting massive particles, a leading candidate for dark matter. The theory suggests that WIMPs might be created during these collisions. If WIMPs exist, they could appear as missing energy in the data, escaping the detectors without interacting, much like neutrinos. While no conclusive evidence for dark matter has yet emerged from the LHC, the experiments have provided valuable constraints, narrowing the range of possible properties that dark matter could possess. The search continues with upgraded detectors and refined collision parameters, as researchers hope to one day spot dark matter particles among the debris of their high-energy collisions. Deep underground, shielded from cosmic rays and other background noise, lies the Large Underground Xenon or Lux detector, one of the most sensitive instruments ever built to hunt for dark matter. Located in the Sanford Underground Research Facility in South Dakota, Lux relies on a tank filled with ultra-pure liquid xenon to detect the faintest interactions between dark matter particles and normal matter. The principle is straightforward but ambitious. If a dark matter particle passes through the detector and collides with the xenon nucleus, it will produce a minuscule flash of light and a small ionization signal. These signals are then captured by ultra-sensitive photomultiplier tubes, capable of detecting even the faintest whispers of activity. Although Lux has not yet observed definitive evidence of dark matter, its results have set new benchmarks for sensitivity, helping to rule out certain theoretical models. Its successor, Lux Zeppelin, is even more advanced, with a larger detector and enhanced capabilities to sift through the cosmic silence in search of dark matter's elusive presence. Beyond the LHC and Lux, numerous other experiments contribute to the hunt for dark matter. Projects like Xenon 1T in Italy, PICO in Canada, and Super CDMS in the United States employ different approaches, from cryogenic detectors to bubble chambers, to maximize the chances of detection. Each of these experiments tackles a specific aspect of the dark matter puzzle, reflecting the global collaboration and interdisciplinary innovation required to confront this profound challenge. The diversity of techniques ensures that even if one method fails, others may succeed in uncovering dark matter's secrets. The direct detection of dark matter would mark a watershed moment in physics, confirming the existence of a previously invisible component of the universe. It would provide not only answers to long-standing questions, but also open doors to entirely new realms of understanding. For now, the search continues, a testament to humanity's unyielding curiosity and determination to reveal the unseen forces shaping the cosmos. Detecting dark matter is one of the greatest challenges in modern physics. By its very nature, dark matter defies direct observation. It does not emit, absorb, or reflect light, nor does it interact with electromagnetic forces. Its presence can only be inferred through its gravitational effects, making the search akin to hunting shadows in a darkened room. Yet, these obstacles have not deterred scientists. Instead, they have fueled ingenuity, pushing the boundaries of technology and theoretical physics. The prevailing hypothesis suggests that dark matter interacts only through gravity and possibly the weak nuclear force. If true, this means that dark matter particles pass through ordinary matter almost entirely unnoticed. For context, billions of dark matter particles could be streaming through your body at this very moment, leaving no trace of their passage. This weak interaction necessitates detectors of extraordinary sensitivity. These instruments must distinguish potential dark matter signals from a cacophony of background noise, including cosmic rays, neutrinos, and even natural radioactivity in the Earth itself. To overcome this, experiments are often placed deep underground or in remote locations to minimize interference. The pursuit of dark matter demands cutting-edge technology which comes with significant costs. Facilities like the Large Hadron Collider and underground detectors like LUX or Xenon require immense financial and logistical support. Furthermore, the sheer complexity of these instruments means that even minor malfunctions can delay research for months or years. For instance, liquid xenon detectors must maintain extreme purity to avoid contamination that could mimic dark matter interactions. Achieving this level of precision requires meticulous engineering and constant monitoring, making every experiment a balancing act between innovation and practicality. One of the greatest challenges in the hunt for dark matter is the uncertainty surrounding its nature. While theories like WIMPs dominate the conversation, other candidates such as actions, sterile neutrinos, and primordial black holes offer competing possibilities. Each theory demands a different experimental approach, dividing resources and efforts. Moreover, if dark matter does not conform to these existing models, scientists may be searching in the wrong direction entirely. The possibility that dark matter interacts via unknown forces or consists of particles beyond the standard model of physics remains an ever-present challenge, forcing researchers to constantly reevaluate their assumptions. Dark matter is not evenly distributed throughout the universe. It clusters in halos around galaxies and galaxy clusters, but its density varies significantly depending on location. Detecting dark matter on Earth might therefore be akin to searching for a single grain of sand in an entire desert, a problem of scale and probability. This uneven distribution also complicates experimental timing. Certain experiments rely on the Earth's motion through the galaxy to detect variations in dark matter particle flux. Such seasonal or directional signals are faint and require years of data collection to confirm. Despite these formidable challenges, the search for dark matter continues with unwavering determination. Each failed experiment provides critical data, narrowing the field of possibilities and refining our understanding. These incremental advances are essential steps in the scientific process, building toward an eventual breakthrough. The global effort to detect dark matter involves thousands of researchers, engineers, and theorists working collaboratively across disciplines. New experiments, like the upcoming Lux Zeppelin detector and advancements in neutrino observatories, are poised to push the limits of sensitivity even further. Theoretical physicists, meanwhile, continue to develop models that integrate dark matter into the broader framework of cosmic evolution, offering fresh perspectives and potential avenues for detection. The stakes are high. Detecting dark matter would not only confirm its existence, but also revolutionize our understanding of the universe. It could illuminate the processes that shaped galaxies, provide insights into the early moments of the cosmos, and reveal connections between the macroscopic structure of the universe and the microscopic world of particles. Above all, the pursuit of dark matter represents the essence of human curiosity. It is a testament to our drive to understand the unseen, to uncover the forces that bind the cosmos together, and to push beyond the boundaries of what is known. The Standard Model of particle physics is one of the most successful theories in science. It describes the fundamental particles, quarks, leptons, and bosons, and the forces that govern their interactions, the electromagnetic weak and strong nuclear forces. With the discovery of the Higgs boson in 2012, the Standard Model seemed complete, offering a coherent explanation for much of the observable universe. However, there's one glaring problem. The Standard Model doesn't account for dark matter. While it elegantly explains the behavior of ordinary matter, it fails to include the mysterious substance that constitutes roughly 27% of the universe's mass energy content. This discrepancy has placed the Standard Model under immense strain, compelling scientists to search for extensions or entirely new frameworks. One of the clearest ways dark matter challenges particle physics is through its gravitational effects. The Standard Model has no particle capable of producing the massive gravitational influence attributed to dark matter. Neutrinos, the only Standard Model particles that interact weakly and are electrically neutral, were once considered candidates. However, their tiny masses and high velocities render them incapable of explaining the observed behavior of galaxies and galaxy clusters. Dark matter's gravitational effects indicate it must consist of a new type of particle, one that interacts weakly with ordinary matter, but has sufficient mass to shape the cosmos. This requirement forces researchers to look beyond the Standard Model for answers. Dark matter's invisibility stems from its apparent lack of interaction with electromagnetic forces. It does not emit, absorb, or reflect light, making it undetectable through traditional methods. This property places it outside the realm of particles like electrons or photons, which are central to the Standard Model. The absence of electromagnetic interaction raises profound questions about the nature of dark matter. Does it belong to an entirely new class of particles? Does it interact via unknown forces? These possibilities hint at physics beyond the established paradigm, requiring theoretical innovation. Dark matter's existence suggests that the Standard Model is incomplete. Several theories aim to bridge this gap, including supersymmetry. This theoretical framework extends the Standard Model by proposing a partner particle for each known particle. In this context, the lightest supersymmetric particle, such as a neutralino, is a promising dark matter candidate. However, the failure of experiments like the Large Hadron Collider to detect supersymmetric particles has cast doubt on this theory. Hidden sectors. Some models propose that dark matter resides in a hidden sector, a parallel universe of particles and forces that interacts with ordinary matter only through gravity or other weak interactions. This idea introduces exotic particles like actions and sterile neutrinos as potential dark matter candidates. Modified gravity. While not a particle-based solution, some physicists explore the idea that our understanding of gravity itself may be incomplete. Theories like modified Newtonian dynamics challenge the need for dark matter by suggesting that gravity behaves differently on cosmic scales. However, these theories struggle to match the evidence provided by phenomena like gravitational lensing. Dark matter doesn't just challenge the Standard Model, it opens a window into uncharted territory. If dark matter particles are discovered, they could revolutionize our understanding of the universe's evolution, the forces that govern it, and the underlying structure of reality itself. Such a breakthrough might unify disparate areas of physics, from the quantum scale to cosmological structures, offering insights into long-standing mysteries like the nature of gravity and the origins of the universe. Among the myriad theories proposed to explain dark matter, WIMPs, or weakly interacting massive particles, stand as the frontrunners. WIMPs are hypothetical particles predicted to have masses much greater than that of protons, yet they interact only weakly with ordinary matter. This means they can pass through stars, planets, and even our bodies without leaving a trace. The appeal of WIMPs lies in their compatibility with the thermal relic hypothesis. In the early universe, particles were created and annihilated in high-energy interactions. As the universe expanded and cooled, most of these particles decayed or annihilated, but some remained. The predicted abundance of WIMPs aligns closely with the observed density of dark matter, making them a compelling candidate. Another promising dark matter candidate is the action. a hypothetical particle much lighter than WIMPs. Actions arise from solutions to theoretical problems in the Standard Model, specifically the strong CP problem, which involves the behavior of quarks and gluons in quantum chromodynamics. Unlike WIMPs, actions are extraordinarily light and interact extremely weakly with both matter and radiation. What makes actions fascinating is their potential to form a vast, invisible field permeating the universe. These particles could also account for the observed rotation curves of galaxies and other gravitational phenomena attributed to dark matter. Ongoing experiments such as the Action Dark Matter experiment aim to detect actions by searching for their predicted interaction with electromagnetic fields. Sterile neutrinos are an extension of the Standard Model's neutrinos, but differ in a crucial way. They do not interact via any of the known forces except gravity. These heavier, sterile counterparts of regular neutrinos could constitute dark matter if they were produced in sufficient abundance in the early universe. Sterile neutrinos are intriguing because their decay could emit detectable X-rays. Observations of unexplained X-ray emissions from galaxies and galaxy clusters have fueled interest in this candidate, though no definitive evidence has yet emerged. A more unconventional candidate for dark matter is primordial black holes. Unlike particle-based explanations, primordial black holes are compact objects that might have formed shortly after the Big Bang. These black holes could range in size from microscopic to many times the mass of the Sun and might account for at least part of the universe's dark matter. Although primordial black holes do not require exotic new particles, their presence would profoundly impact our understanding of cosmology and the early universe. Studies of gravitational lensing and cosmic background radiation are ongoing to determine whether primordial black holes could explain the observed effects of dark matter. The diversity of dark matter candidates reflects the breadth of the challenge. Beyond WIMPs, actions, sterile neutrinos, and primordial black holes, researchers explore other possibilities including superfluid dark matter, a theory suggesting that dark matter could form a quantum superfluid, influencing gravity in unique ways. Fuzzy dark matter, extremely light particles with wave-like properties that could form large-scale structures. Self-interacting dark matter particles that interact with themselves but not with ordinary matter, potentially explaining certain galactic phenomena. Each candidate represents a different facet of the dark matter puzzle. WIMPs dominate collider and underground detection efforts, while actions and sterile neutrinos push the boundaries of particle physics. Primordial black holes and exotic theories challenge the very concept of what dark matter might be. The search for these candidates is a testament to the creativity and adaptability of science. Whether dark matter turns out to be a familiar particle or something entirely unexpected, its discovery will revolutionize our understanding of the cosmos and the laws that govern it. The discovery of dark matter would revolutionize our understanding of the universe's history and structure. Currently, dark matter is considered the invisible scaffolding upon which galaxies and larger cosmic structures are built. By unraveling its nature, we could answer fundamental questions about how the universe formed, evolved, and reached its present state. In the early universe, shortly after the Big Bang, dark matter played a crucial role in shaping the cosmic web. While ordinary matter interacted with light and radiation, dark matter remained unaffected by electromagnetic forces, allowing it to clump together under gravity. These clumps served as gravitational wells, pulling ordinary matter into them and forming the seeds of galaxies. Discovering the properties of dark matter would refine our models of these early processes, offering a clearer picture of how galaxies, stars, and planets emerged. The universe is structured in a vast, interconnected web of galaxies, clusters, and voids. This cosmic web is shaped by the gravitational influence of dark matter. Without it, these structures would not exist as we observe them today. If dark matter's properties were identified, such as its mass, interaction strength, or particle behavior, scientists could better simulate the universe's large-scale evolution. These insights would bridge gaps in our understanding of how cosmic structures formed over billions of years, and how they continue to evolve under the influence of both dark matter and dark energy. Dark matter's role isn't limited to the past, it also shapes the future. The gravitational pull of dark matter counters the expansive force of dark energy, which drives the acceleration of the universe's expansion. Understanding the balance between these forces could help predict the ultimate fate of the cosmos. If dark matter interacts in ways we don't yet understand, it could influence whether the universe continues expanding forever, eventually freezing in a heat death or contracts in a big crunch. Alternatively, if dark matter decays over cosmic timescales, its diminishing influence could allow dark energy to dominate, leading to even more rapid acceleration and a big rip. By identifying and studying dark matter, physicists could refine these scenarios, offering profound insights into the universe's destiny. Dark matter discovery would unify two seemingly disparate realms of physics, the quantum and the cosmic. At its core, dark matter likely consists of particles governed by quantum mechanics, yet its influence is felt on the largest scales, shaping galaxies and the universe itself. This connection might lead to breakthroughs in other areas of science, such as particle physics. Discovering dark matter particles could expose new forces or symmetries in nature, leading to extensions of the standard model. Astrophysics, understanding dark matter would refine models of star formation, galaxy dynamics, and black hole behavior. Cosmology, insights into dark matter could provide clues about the universe's earliest moments, potentially shedding light on inflation or other processes near the Big Bang. Beyond the scientific implications, discovering dark matter would profoundly impact how humanity views its place in the cosmos. It would reveal that much of the universe consists of something fundamentally different from the matter that makes up our bodies, our planet, and everything we've ever known. This realization could deepen our sense of connection to the cosmos, emphasizing that we are part of a much larger, more mysterious whole. Perhaps the most exciting implication of discovering dark matter lies in the doors it could open. Historically, every major scientific breakthrough has led to unexpected discoveries. Electricity paved the way for modern technology, and quantum mechanics revolutionized our understanding of the universe. Similarly, understanding dark matter might reveal entirely new realms of physics, forces, or phenomena that we cannot yet imagine. In this sense, the discovery of dark matter is not just about solving a mystery, it's about expanding the boundaries of human knowledge, venturing into the unknown, and uncovering truths that could redefine our understanding of existence itself. Dark matter plays a fundamental role in cosmology, the study of the origin, evolution, and structure of the universe. Its gravitational influence serves as the backbone of cosmic structures, dictating how galaxies form, cluster, and evolve over billions of years. Without dark matter, the cosmos as we know it would not exist. Understanding dark matter is therefore essential to refining our models of the universe's formation and its large-scale behavior. In the early universe, just after the Big Bang, dark matter began to clump together under gravity, forming dense regions that acted as seeds for galaxy formation. Ordinary matter, composed of atoms, was initially scattered by intense radiation, but eventually fell into these dark matter wells, creating the galaxies and clusters we see today. Without dark matter, this process would have been impossibly slow, leaving a universe largely devoid of structure. Exploring dark matter is key to unraveling these early cosmic events. The universe is expanding, a fact first discovered by Edwin Hubble in the 1920s. Over time, this expansion has been found to be accelerating, driven by a mysterious force called dark energy. Dark matter and dark energy together dominate the universe, comprising approximately 95% of its total mass energy content. Their interplay shapes the dynamics of the cosmos. Dark matter slows the expansion through its gravitational pull, while dark energy pushes against it, driving acceleration. Understanding dark matter is critical to deciphering this delicate balance, the tug-of-war. How dark matter and dark energy interact influences the rate of cosmic expansion. Precise knowledge of dark matter's properties, its density, distribution, and interactions would allow cosmologists to make more accurate predictions about the universe's future trajectory. The ultimate fate of the universe, whether the cosmos ends in a big freeze, big crunch, or big rip, depends largely on the role and behavior of dark matter over cosmic timescales. The lambda-called dark matter is the prevailing framework in cosmology. It describes a universe composed of dark energy, dark matter, and ordinary matter. While lambda-called dark matter has been extraordinarily successful in explaining observations like the cosmic microwave background radiation and large-scale galaxy distributions, it remains incomplete without a deeper understanding of dark matter. Structure formation, Simulations of galaxy and cluster formation depend heavily on assumptions about dark matter's properties. Better understanding could resolve discrepancies between observed and simulated galaxy distributions. Small-scale anomalies. The lambda-called dark matter model struggles to explain certain small-scale phenomena, like the observed density profiles of dark matter in galaxies. A deeper understanding of dark matter could address these inconsistencies. Studying dark matter may also provide insights into the universe's infancy. Shortly after the Big Bang, conditions were so extreme that matter and energy were indistinguishable. Dark matter's behavior during this epoch could reveal clues about the inflationary era, the rapid expansion of the universe immediately following the Big Bang. Baryogenesis, the process by which ordinary matter came to dominate over antimatter. Reionization, the period when the first stars and galaxies began to form, reionizing the universe's neutral hydrogen. By connecting the properties of dark matter to these events, cosmologists could fill gaps in our understanding of the universe's earliest moments. Dark matter research also has profound implications for understanding dark energy, the force driving cosmic acceleration. While these two phenomena are distinct, they are deeply intertwined in shaping the universe's fate. Studying dark matter may reveal new physics that unifies them, providing a more complete picture of the universe's mass energy content and its ultimate destiny. Understanding dark matter would mark a paradigm shift in cosmology, akin to Copernicus' heliocentric model or Einstein's theory of general relativity. It would not only refine our knowledge of the universe's expansion, but also reveal the fundamental processes that govern the cosmos. By answering the question of dark matter, we edge closer to answering the larger questions. Where did we come from? Where are we going? And what is the true nature of reality? The discovery of dark matter would be a watershed moment for particle physics, opening a door to realms of knowledge far beyond the Standard Model. While the Standard Model has been remarkably successful in describing the known particles and forces, it cannot account for the mysterious substance that makes up 27% of the universe. This glaring gap suggests the existence of entirely new particles, forces, or symmetries that extend the boundaries of our current understanding. If dark matter is composed of particles, discovering its true nature could revolutionize our understanding of the subatomic world. Among the most promising avenues are WIMPs. Weakly interacting massive particles as leading candidates, WIMPs would represent a new class of particles interacting via weak nuclear forces. Their discovery could reveal new interactions and extensions to the Standard Model, such as supersymmetry, which posits the existence of partner particles for all known particles. Actions. The discovery of axions would solve not only the dark matter mystery, but also the strong CP problem in quantum chromodynamics. Actions could provide a bridge between particle physics and cosmology, unveiling connections previously thought unrelated. Sterile neutrinos. These hypothetical particles, unlike their Standard Model counterparts, would only interact through gravity. Detecting sterile neutrinos could expand our knowledge of neutrino physics and offer insights into the behavior of other elusive particles. Each of these particles represents a possible paradigm shift, revealing interactions or dimensions of nature that are currently hidden from view. Dark matter could point to the existence of previously unknown forces or interactions. For example, dark sector physics. Some theories propose that dark matter interacts with itself through dark forces mediated by particles analogous to photons in the visible universe. Detecting these forces could unveil an entirely new layer of reality, a dark sector that exists parallel to our observable universe. Fifth force of nature. If dark matter interacts with ordinary matter in unexpected ways, it might hint at a new, fundamental force beyond the four currently known: gravitational, electromagnetic, strong nuclear, and weak nuclear forces. These discoveries would fundamentally alter our understanding of how the universe operates, potentially unifying disparate phenomena under a broader theoretical framework. One of the most profound implications of dark matter research lies in its potential to connect quantum mechanics and general relativity, two pillars of modern physics that remain theoretically incompatible. Dark matter operates on both quantum and cosmic scales, offering a rare opportunity to study phenomena that could unify these frameworks. If dark matter consists of quantum particles with wave-like properties, its behavior might illuminate how quantum effects manifest on macroscopic, gravitational scales. Understanding dark matter's gravitational effects could provide insights into quantum gravity, bringing us closer to a theory of everything. The hunt for dark matter has driven advancements in technology that benefit particle physics more broadly. High-energy experiments like those at the Large Hadron Collider are continually upgraded to achieve greater sensitivity, paving the way for discoveries beyond dark matter. Innovations in detector design, such as cryogenic techniques and ultra-pure materials, are already being applied to explore other unanswered questions in physics. These advancements not only enhance our ability to detect dark matter, but also improve our capacity to explore phenomena like neutrino oscillations, proton decay, and the asymmetry between matter and antimatter. The discovery of dark matter would necessitate extending the Standard Model to include new particles, interactions, and symmetries. Such an extension could reveal connections between seemingly unrelated phenomena, such as dark matter and the Higgs field, provide a framework for understanding other cosmic mysteries like dark energy or the origins of matter-antimatter asymmetry, offer insights into the conditions of the early universe, such as the processes that occurred during and after the Big Bang. The breakthroughs in particle physics spurred by dark matter research would ripple across multiple disciplines, from astrophysics to cosmology. These discoveries could redefine fundamental concepts such as mass, force, and even the nature of reality itself. As our theoretical frameworks evolve, so too will our ability to answer deeper questions about existence. As we conclude this journey through the unseen universe, one truth remains abundantly clear: dark matter is one of the greatest mysteries of our time. Its discovery and understanding hold the potential to reshape not only physics, but our very perception of reality. Yet, for all that we've explored its gravitational fingerprints, its hypothesized particles, and its role in the evolution of the cosmos, dark matter remains tantalizingly elusive. This mystery is a reminder of the vastness of the unknown. The universe is far larger, more complex, and more wondrous than we can currently imagine. Dark matter is but one piece of a much larger puzzle, one that includes dark energy, the origins of the universe, and the fundamental nature of existence itself. The ongoing quest to understand dark matter is a testament to human curiosity and ingenuity. It represents the best of science, a relentless pursuit of knowledge, driven by the belief that the answers lie just beyond our reach. With each experiment, each observation, and each theoretical breakthrough, we inch closer to uncovering the secrets of the cosmos. But dark matter is more than a scientific challenge, it's a source of inspiration. It invites us to dream, to question, and to wonder. What lies hidden in the fabric of the universe? What new realms of physics await discovery? How will these insights transform our understanding of the cosmos and of ourselves? The future of dark matter research is bright, filled with promise and potential. Advancements in technology, from more sensitive detectors to next-generation particle accelerators, bring us closer to direct detection. New telescopes and space missions will map the cosmos with unprecedented precision, revealing the subtle influences of dark matter on galaxies and beyond. Meanwhile, theoretical physicists continue to push the boundaries of what is possible, exploring ideas that might seem unimaginable today, but could become the discoveries of tomorrow. Each step forward in the hunt for dark matter deepens our understanding of the universe, reminding us that the pursuit of knowledge is never truly finished. As we unravel this mystery, we'll inevitably uncover new questions, new frontiers to explore, new challenges to face, and new wonders to marvel at. So, as we look to the future, let us embrace the mystery of dark matter. Let it remind us of the infinite possibilities that lie within the cosmos, waiting to be discovered. The journey to understand dark matter is far from over, but every step we take brings us closer to answering the fundamental questions of existence. What is the universe made of? Where did it come from? And what is our place within it? In the end, the greatest discoveries often begin with the simplest yet most profound realization: the universe is far more mysterious than we could ever imagine. And that mystery in itself is the ultimate source of wonder. What if we could trace the origins of life itself? Why does the cosmos seem so perfectly tuned? Is the universe hiding its creator? Could the universe be alive? Is life a cosmic accident or a destined event? Are we truly alone in the universe? What if we could trace the origins of life itself? Is life on Earth a fleeting accident in an otherwise indifferent cosmos? Or is it a necessity, written into the very fabric of the universe? Perhaps, even more astonishingly, could it be the deliberate creation of a higher intelligence? These questions have fascinated thinkers, scientists, and philosophers for centuries, pushing the boundaries of human imagination. The mystery of how life began is one of the deepest questions humanity has ever pondered. Despite centuries of progress in science and technology, the origins of life remain shrouded in uncertainty, leaving us to speculate at the intersection of science, philosophy, and even metaphysics. From the chaotic dance of atoms billions of years ago to the emergence of complex, sentient beings, the journey of life has ignited debates across disciplines. Is our existence the result of sheer chance, inevitable under universal laws, or the product of a higher, intentional design? Each perspective offers a unique lens, but none can yet claim to hold the definitive answer. This exploration will journey through three primary perspectives: the hypothesis that life arose by coincidence, the argument that life was an inevitable outcome of nature's laws, and the possibility that a higher consciousness designed the conditions for life to emerge. Through these lenses, we'll uncover the profound implications of each theory, examining evidence, raising questions, and contemplating what it all means for our understanding of existence. Coincidence, the role of randomness in life's origins. Life, in this view, is nothing more than a fortunate accident, a consequence of countless random interactions occurring under the right conditions. Imagine a chaotic primordial Earth, its surface bombarded by meteors, its atmosphere thick with gases, and its oceans bubbling with chemicals. Amid this seemingly anarchic environment, molecules collided, bonded, and eventually formed the building blocks of life. This hypothesis suggests that life is not guaranteed, but rather the result of an almost miraculous convergence of circumstances. It argues that, given the vastness of time and space, such a cosmic accident was bound to occur somewhere. Earth just happened to be the lucky winner in the lottery of existence. Abiogenesis, the scientific explanation for life's origins, posits that life arose naturally from non-living chemical compounds. This theory gained traction with the famous Miller-Urey experiment in 1953. In a controlled laboratory setup simulating early Earth's conditions, researchers exposed a mixture of water, methane, ammonia, and hydrogen to electric sparks, mimicking lightning. Remarkably, the experiment produced amino acids, organic compounds essential for life. The results were groundbreaking, proving that complex molecules could form spontaneously under the right conditions. Subsequent research has expanded on these findings, identifying potential pathways through which simple molecules could organize into self-replicating systems, the precursors to life. However, abiogenesis faces significant challenges. Critics point out that forming life's essential components, like proteins or RNA, is far more complex than creating amino acids. Even under ideal conditions, the probability of assembling functional proteins by chance is astronomically low, leading skeptics to question whether randomness alone could account for the emergence of life. Let's consider the staggering odds involved in life's emergence. The chance of a single functional protein forming spontaneously has been compared to a monkey typing out Shakespeare's Hamlet by randomly hitting keys on a keyboard. Now multiply that improbability by the complexity of an entire living cell. Scientists estimate that Earth existed for approximately 1 billion years before life emerged. While this time frame provides countless opportunities for chemical interactions, it also underscores how rare and extraordinary the conditions must have been for life to begin. The coincidence hypothesis raises a critical question. If life is a rare accident, why does the universe appear so finely tuned to allow it? For instance, the Earth orbits in the Goldilocks zone, where temperatures are just right for liquid water, a key ingredient for life. Some argue that this perfect alignment is too precise to be purely coincidental. Others counter that the universe's vastness ensures some planets would inevitably meet these conditions. To grasp this perspective, think of the universe as a vast casino, and Earth's origins as a game of roulette. The odds of life forming may have been infinitesimally small, but the wheel spun countless times across the cosmos. Earth, it seems, was the one lucky spin where the ball landed perfectly. The hypothesis that life arose by coincidence paints a picture of a fragile, improbable event in the grand chaos of the universe. Yet, this perspective also leaves us with a profound sense of uncertainty. If life truly is a cosmic accident, what does that say about its meaning or lack thereof? Necessity. Life is an inevitable outcome. Unlike the randomness of the coincidence perspective, the necessity hypothesis suggests that life was bound to happen. It argues that the physical and chemical laws governing the universe naturally lead to the emergence of life when conditions align. In this view, life is not a miraculous anomaly, but an inherent outcome of the universe's design, a natural expression of its potential. Imagine the universe as a carefully arranged orchestra. Every instrument, from gravity to electromagnetism, plays its role, creating conditions that make life not only possible but unavoidable. Life's building blocks rely on universal principles that drive molecules to organize into more complex forms. Consider the following: the Goldilocks zone. Earth orbits the Sun at just the right distance, allowing liquid water to exist, a critical factor for life. Many other planets in the universe may share similar conditions, suggesting that life could arise wherever these just right circumstances occur. Self-organization in chemistry. Certain molecules have an innate tendency to self-organize. For example, phospholipids spontaneously form membranes in water, mimicking the cell walls of living organisms. This self-assembly hints that life's essential structures could arise naturally under the right conditions. This perspective gains further support from extremophile organisms that thrive in extreme environments. From hydrothermal vents deep in the ocean to boiling acid springs, life has demonstrated its remarkable ability to emerge and survive in diverse conditions, reinforcing the idea that it may naturally arise wherever it can. The idea that specific chemical reactions, under specific conditions, inevitably lead to life. For instance, amino acids tend to link together when exposed to certain environmental pressures, potentially forming proteins over time. The role of water and carbon. Water's unique properties, like its ability to dissolve a wide range of substances, make it a crucial solvent for biochemical reactions. Similarly, carbon's versatility allows it to form complex molecules, such as DNA and proteins, making it the backbone of all known life. Astrobiological discoveries. Recent discoveries of organic compounds on comets and meteorites suggest that the building blocks of life are not unique to Earth. These findings bolster the argument that life's raw materials are widespread in the universe, increasing the likelihood of its emergence. Extremophiles challenge the notion that life requires Earth-like conditions. Organisms like the tardigrade can survive in the vacuum of space, extreme radiation, and intense heat. These resilient creatures suggest that life might emerge in environments we once deemed uninhabitable. Moreover, the search for exoplanets has revealed thousands of potentially habitable worlds. Some of these planets orbit stars similar to our Sun, within their own Goldilocks zones. Could these planets host life? If so, it would support the idea that life is a universal phenomenon, not a unique accident. Yet, if life is inevitable, why have we not found definitive evidence of it beyond Earth? This paradox, known as the Fermi paradox, challenges the necessity hypothesis. Are we simply not looking in the right places, or is life's emergence rarer than we assume? The silence of the cosmos raises as many questions as it answers. Think of life as a seed planted in fertile soil. The conditions, sunlight, water, nutrients, make growth inevitable. Similarly, when the universe provides the right soil and climate, life, like a seed, is destined to flourish. The necessity hypothesis paints life as an intrinsic part of the universe, woven into its very fabric. This perspective shifts the narrative from randomness to inevitability, suggesting that wherever the universe creates the right conditions, life will arise. Design. A higher consciousness behind life. What if the emergence of life was not a product of random chance or inevitable natural laws, but a deliberate act of creation? The design hypothesis proposes that life's complexity and the universe's apparent fine-tuning point to the influence of a higher intelligence, a consciousness that set the stage for life to arise. Imagine a watch found on a beach. Its intricate gears and precision are unlikely to have formed by accident. Similarly, proponents of this view argue that life's complexity, from DNA's coded instructions to the universe's finely tuned physical constants, suggests a purposeful design rather than coincidence or inevitability. The idea of a higher consciousness shaping life is deeply rooted in philosophical and spiritual traditions. Religious perspectives. Creation stories from various cultures such as Genesis in the Bible, Brahma's creation in Hinduism, or the Dreamtime of Aboriginal Australians often portray life as the intentional work of a divine being or higher force. Philosophical inquiry. Ancient philosophers, including Plato and Aristotle, posited the existence of a prime mover or intelligent designer who set the cosmos into motion. These narratives resonate with the design hypothesis, reflecting humanity's long-standing intuition that life and the universe may hold deeper meaning and purpose. The fine-tuning of the universe. Certain physical constants, such as the strength of gravity, the charge of the electron, or the cosmological constant, are finely balanced. Even the slightest deviation in these values would render life impossible. For example, if the strength of gravity were slightly weaker or stronger, stars could not form or sustain nuclear fusion, eliminating the possibility of planets and life. The fine-tuning argument suggests that these precise values are unlikely to have arisen by chance, pointing instead to intentional calibration. The DNA code as evidence of design. DNA, often referred to as the blueprint of life, is a molecular code that governs the development and functioning of all living organisms. Its complexity and specificity have led some scientists and philosophers to liken it to a computer program. Could such intricate programming have arisen without an intelligent programmer? Irreducible complexity. Some biological systems, such as the bacterial flagellum or the human eye, are so complex that they seem irreducible, incapable of functioning if any single part were removed. Proponents argue that such systems challenge the gradualist explanations of evolution, suggesting a designer's hand. While compelling, the design hypothesis has faced significant criticism. Anthropocentrism. Critics argue that intelligent design is anthropocentric, projecting human notions of purpose and complexity onto the universe. Lack of empirical evidence. Unlike scientific theories that can be tested and falsified, intelligent design often relies on inference, which some dismiss as unscientific. Alternative explanations. Mechanisms like evolution and natural selection offer robust explanations for life's complexity, reducing the need for invoking a designer. In recent years, some scientists have explored ways to reconcile the idea of design with empirical evidence. Simulation theory. The hypothesis that our universe is a simulation designed by an advanced intelligence. Proponents like physicist Nick Bostrom argue that if future civilizations develop the technology to simulate universes, it's statistically likely that we are living in one. Panpsychism. A philosophical view suggesting that consciousness is a fundamental property of the universe, embedded in all matter. In this framework, the universe's design could emerge from a collective consciousness, rather than an external creator. To understand the design hypothesis, think of life as a symphony. The universe is the orchestra, and its laws are the instruments. A symphony requires a conductor to arrange the notes into harmony, just as life's emergence might require a designer to orchestrate the right conditions. Comparative analysis overlapping themes and conflicts. Despite their differences, the three perspectives, coincidence, necessity, and design, share common ground in addressing the profound mystery of life's origins, the uniqueness of life. All three views recognize that life is extraordinary, whether it emerged by accident, inevitability, or design. Each perspective underscores the rare and complex nature of living systems in a vast, seemingly indifferent universe. Interplay between chaos and order. The coincidence hypothesis highlights the chaotic randomness of molecular interactions. The necessity hypothesis demonstrates how order emerges naturally from the laws of physics and chemistry. The design hypothesis emphasizes intentional order, suggesting chaos is merely the backdrop for a purposeful plan. The role of universal laws. All three approaches acknowledge the importance of the universe's physical and chemical laws. Whether these laws create life by chance, inevitability, or design, they are fundamental to the discussion. While the shared themes bring the perspectives together, their underlying assumptions often lead to sharp contrasts. Chance versus determinism. Coincidence relies on randomness, viewing life as the result of improbable events. Necessity emphasizes determinism, positing that life is a predictable outcome of universal principles. Design versus naturalism. The design hypothesis introduces the idea of a higher intelligence or purpose, while coincidence and necessity remain rooted in natural processes, rejecting the need for external intervention. Philosophical implications. Coincidence suggests life has no intrinsic meaning, as it is a random occurrence. Necessity offers a middle ground, implying that life has significance as a natural product of the universe. Design infuses life with purpose, proposing that it is part of a deliberate cosmic plan. Some thinkers argue that these perspectives are not mutually exclusive but could instead represent different layers of the same reality. The coexistence of chance and necessity. Life's origins could involve a combination of random events and deterministic laws. The formation of essential molecules might be random, but their assembly into complex systems could follow inevitable patterns. Design through natural processes. The design hypothesis doesn't necessarily conflict with science. A higher intelligence might have created the universe's laws in such a way that life emerges naturally, with occasional elements of randomness shaping its path. To visualize these perspectives together, imagine a painter creating a masterpiece. Coincidence. The paint splatters randomly on the canvas, forming an unplanned image. Necessity. The painter uses precise strokes guided by the properties of the brush and paint, ensuring the painting emerges logically from the tools. Design. The painter has a vision from the start, intentionally guiding every element of the painting toward a final purpose. Perhaps life's origins resemble a collaboration between these approaches, an interplay of chaos, inevitability, and vision. The origins of life remain one of humanity's greatest mysteries, inspiring theories that range from randomness to inevitability to intentional design. Coincidence reminds us of life's fragility, portraying it as a miraculous anomaly in a chaotic universe. Necessity elevates life to a fundamental feature of the cosmos, a product of its inherent laws and principles. Design introduces purpose, suggesting that life may be the deliberate creation of a higher intelligence. Each perspective provides a compelling lens, yet none alone can fully explain the profound complexity and meaning of life's emergence. As we journey through these ideas, one question emerges: must we choose just one? Perhaps life's origins encompass all three perspectives in a complex interplay. Coincidence could describe the unpredictable initial conditions that led to life. Necessity could explain the universal laws that guided its development. Design might reflect an underlying purpose woven into the fabric of the cosmos. Much like a mosaic, the full picture of life's origins might only emerge when we consider these perspectives together, embracing their unique insights and shared mysteries. The exploration of life's origins ultimately leaves us with more questions than answers. If life is a cosmic accident, how do we make sense of its meaning, or lack thereof? If life is inevitable, what responsibilities do we have as part of the universe's natural progression? If life is designed, what role might humanity play in a grander plan? As we contemplate these questions, we are reminded that the journey to understand life's origins is as important as the answers themselves. As we gaze into the night sky, marveling at its vastness and mystery, one truth becomes clear. Our existence is an extraordinary phenomenon, whether born of chance, necessity, or design. It is up to us to make meaning from this knowledge, to explore with curiosity, and to live with purpose. For in the grand tapestry of the universe, we are both its observers and participants, a fleeting but vital spark in the eternal story of existence. Is the universe just a vast, lifeless expanse, or is there something more, something conscious, alive, perhaps even self-aware? Could the cosmos be more than a collection of stars and galaxies scattered across empty space? What if we are all part of a larger mind, an immense cosmic brain, where each galaxy is like a neuron, working in concert with others? Is it possible that consciousness didn't emerge randomly, but was an intrinsic part of the universe from the very beginning? Could our thoughts, emotions, and experiences be tiny reflections of the universe's own awareness? If the universe is indeed conscious, then what role do we play in it? Are we merely observers, or are we active participants, helping the cosmos understand itself? Why do the laws of physics seem so perfectly tuned for life? Could it be that the universe chose conditions that allow consciousness to flourish? And if so, is there a purpose to this grand design? As we gaze into the night sky, are we witnessing the universe looking back at itself through us? If everything is connected, then where does individuality end and universality begin? Do our minds hold the keys to unlock the universe's mysteries, or are we simply parts of a complex, universal mind that has yet to fully comprehend itself? Let's delve into these questions and explore the possibility that the universe might not only contain consciousness, but actually be consciousness itself, pondering its own existence through each of us. The cosmic brain hypothesis. In the vastness of the cosmos, where galaxies stretch like points in an endless web, scientists and philosophers have started to notice a curious pattern of resemblance between the universe's structure and that of the human brain. The universe, composed of billions of galaxies, seems to be connected in ways that bear an uncanny resemblance to the neural network within our own minds. This similarity has led to a provocative question: could the universe itself function as a kind of brain? When we look at the intricate arrangement of galaxies, clusters and superclusters in the cosmic web, we see something far from random. Just as neurons in the brain connect through a complex network of axons and synapses, galaxies form connections through vast filaments and dark matter. Italian astrophysicist Franco Vazza and neuroscientist Alberto Filetti conducted a study comparing the structures of the cosmic web and the human brain's connectome, finding striking parallels between the two. Their research showed that while these structures operate on vastly different scales, the patterns and connections share a deep structural similarity. For instance, both brains and the universe show complex networks that follow similar organizational rules, with small, dense nodes connected by long, branching filaments. In the brain, these nodes are neurons; in the universe, they are galaxies or galaxy clusters. This resemblance between the brain and the universe has led to the hypothesis that the universe may function as a colossal brain. In our brains, neurons communicate through electrical signals, building networks that allow for complex thought, emotion, and consciousness. The universe, too, has its form of communication through gravitational forces, electromagnetic radiation, and possibly even dark matter. But does this cosmic network actually process information the way a brain does? And if so, could it be conscious? One theory that supports this idea is panpsychism, the belief that consciousness is a fundamental quality embedded in all matter. Under panpsychism, even particles that make up galaxies could contain some form of proto-consciousness, similar to the rudimentary awareness in simple organisms. This doesn't mean that rocks or stars are aware in the way we are, but rather that they possess a basic form of consciousness that, when combined across the vast networks of the universe, could form a larger, unified awareness. The concept of integrated information theory, IIT, offers another perspective on how the universe might hold consciousness. IIT, developed by neuroscientist Giulio Tononi, suggests that consciousness arises from the degree to which a system can integrate information. In a human brain, this integration happens among billions of neurons connected in a dense network. If we extend IIT to the universe, we might argue that the cosmic web structure could allow for a similar kind of information integration, potentially giving rise to a form of universal consciousness. While this hypothesis remains speculative, it opens up an intriguing possibility that the universe, with its vast network of galaxies and matter, might not only process information but also experience a rudimentary form of awareness. However, while the brain and the universe share structural similarities, they operate on very different scales and with different types of connections. Neurons communicate through electrochemical signals, while galaxies and clusters interact primarily through gravitational forces. Unlike the rapid, continuous flow of signals in our brains, interactions across the cosmos are slow, limited by the speed of light and the vast distances involved. Despite this, some scientists speculate that the presence of black holes at the center of galaxies could serve as focal points in a kind of cosmic communication. Black holes, with their immense gravitational pull, might be compared to neural hubs in the brain, potentially playing a role in the universe's information network. One potential link between brain activity and cosmic activity comes from quantum mechanics. At a quantum level, particles can exhibit entanglement, where two particles remain connected across vast distances, responding instantaneously to each other's states. Some researchers have suggested that this phenomenon, known as quantum entanglement, could represent a form of non-local connectivity that might be essential for a universal consciousness. If such connections exist on a cosmic scale, they might enable a kind of communication across the universe that transcends traditional physical limitations, similar to how the brain's neurons maintain a cohesive consciousness despite being physically separate. Another supporting theory for the cosmic brain hypothesis is the holographic principle, which suggests that all the information in the universe might be encoded on a two-dimensional surface, much like a hologram. If this is true, then our experience of a three-dimensional universe could be a projection of this information. In this sense, the entire universe might be processing information in a way similar to a brain, creating the complex reality we observe. This principle, which some scientists believe could help unify quantum mechanics and general relativity, implies that our reality might be fundamentally informational, with consciousness potentially woven into its very fabric. Philosophical roots, Schrodinger, and the unified mind. The idea of a conscious universe might sound like a product of modern theoretical science, yet it has philosophical roots stretching back centuries. One of the most intriguing figures to explore these questions was Erwin Schrödinger, the Nobel Prize-winning physicist whose work extended well beyond the boundaries of quantum mechanics. Schrödinger believed that consciousness is not merely an individual phenomenon confined to the human brain, but might actually reflect a universal, singular mind. This idea was shaped by his fascination with Eastern philosophy, particularly the concept of Atman equals Brahman from Indian Vedantic thought. In simple terms, this notion implies that the self is ultimately indistinguishable from the cosmos or universal reality. To Schrödinger, this was not merely a poetic concept, but a serious philosophical framework that questioned the division between individual minds. Could it be that what we perceive as separate minds are merely facets of a single, unified consciousness? Schrödinger's conviction in a shared mind stemmed from a fundamental question he posed. Why is consciousness only ever experienced in the singular? Throughout his career, he observed that no one experiences more than one stream of consciousness at any given time. This led him to wonder if individual minds might only appear separate due to physical limitations and perception, while in reality, they are connected by an underlying universal mind. The notion of a unified consciousness also addresses an age-old philosophical dilemma, the nature of reality itself. Schrödinger argued that metaphysics, the study of what truly exists beyond our physical world, is not a byproduct of physics, but a foundation that precedes it. In his view, our inability to empirically prove an external world independent of our minds or separate individual consciousnesses is precisely what hints at a singular, interconnected reality. If we are indeed all part of one universal consciousness, it could explain why mind and matter seem intertwined in ways that science has yet to fully unravel. To illustrate his idea, Schrödinger often used the metaphor of a crystal. Imagine a crystal exposed to light, refracting it into many colors. These colors, each distinct, represent individual conscious minds, while the crystal itself symbolizes the singular, cosmic consciousness underlying them all. Though we might perceive ourselves as unique individuals, we are, in this view, different expressions of the same essential consciousness, refracted through various physical forms. Schrödinger's reflections were not widely accepted by Western scientific circles at the time. However, his idea of a single mind has continued to influence both science and philosophy, inspiring researchers to explore consciousness beyond the confines of the individual brain. By suggesting that individuality might be an illusion, Schrödinger opened the door to a profound shift in our understanding of consciousness. If the self is an illusion, then we might be part of a collective experience far more expansive than personal identity allows. Schrödinger's perspective also touches on the relationship between mind and matter. He argued that matter, as we know it, is an objectivation of the unified mind, a way of experiencing the universe through tangible forms and sensations. This framework allowed him to entertain the possibility that physical reality is a simplified projection of a more complex, non-physical realm. In this model, the physical world appears separate and independent because it serves as an interface, like a simplified map of reality for conscious beings to interact with. Scientific possibilities, conscious agents theory. While Schrödinger's view of a unified mind might sound abstract, modern science has begun to develop theories that bridge these philosophical ideas with empirical science. Among these theories is the concept of conscious agents theory, which explores the possibility that consciousness is a fundamental property arising from the interactions within complex systems. This theory suggests that consciousness isn't exclusive to humans or even biological organisms, but rather can emerge wherever there is enough complexity and connectivity, perhaps even on a cosmic scale. According to IIT, the degree of consciousness in a system can be measured by a metric called phi, representing the system's capacity to integrate information. In theory, if a highly interconnected system like the universe has a high enough phi, it could exhibit characteristics of consciousness. While applying IIT directly to the cosmos is still speculative, it suggests that consciousness may not be limited to biological brains. Rather, it could be a fundamental characteristic that manifests in any system with sufficient complexity, from a single organism to an entire universe. Beyond IIT, conscious agents theory CAT, introduced by cognitive scientist Donald Hoffman, offers another fascinating approach to universal consciousness. CAT suggests that consciousness is the fundamental building block of reality, and that all physical entities are representations or interactions of these conscious agents. In this view, conscious agents don't emerge from physical matter. Instead, they are primary, and physical reality arises from their interactions. This idea aligns with Schrödinger's concept of a unified consciousness, as it implies that every part of reality, from subatomic particles to galaxies, could be interconnected through a web of conscious experiences. CAT proposes that the universe is essentially a network of interacting conscious agents, with each interaction producing a different aspect of the observable world. Just as neurons in the brain interact to create our experience of consciousness, conscious agents in the universe could interact to generate a form of universal consciousness. In this model, what we perceive as physical reality is simply an interface that allows conscious agents to interact within a shared, structured environment. In other words, reality as we know it could be the product of these conscious interactions, with physical matter and energy as byproducts. While these theories are groundbreaking, they also face considerable challenges, both in terms of empirical testing and philosophical implications. Measuring consciousness in non-human systems, let alone on a cosmic scale, remains a daunting task. Currently, IIT has been applied primarily to biological brains, where we can observe and measure information flow among neurons. Applying it to the universe would require a way to quantify information integration among galaxies or other large-scale structures, a feat that lies beyond our current scientific tools. Nonetheless, conscious agents theory and integrated information theory push the boundaries of our understanding, suggesting that consciousness might not be a unique product of evolution on Earth. Instead, consciousness could be a fundamental aspect of reality itself, arising from any sufficiently complex network. If this is true, it would imply that our universe, with its vast network of galaxies and intergalactic connections, might indeed possess some form of awareness. These theories not only propose a radically new perspective on consciousness, but also hint at a profound interconnectedness underlying all things. In a conscious universe, every action and interaction could contribute to a grander scheme of awareness, where galaxies, stars, and even inanimate matter play a role in the vast tapestry of consciousness. If the universe is indeed a conscious system, then our place in it becomes part of a much larger story, one where each of us may be contributing to the universe's own journey towards self-awareness. Testing the hypothesis, is the universe self-aware? The idea that the universe might be conscious, while fascinating, raises a challenging question: can we actually test this hypothesis? Scientific theories are most valuable when they offer ways to be empirically tested. And while proving universal consciousness is a daunting challenge, researchers are exploring intriguing methods that could bring us closer to an answer. Quantum entanglement occurs when two or more particles become linked in such a way that their states remain interconnected, regardless of the physical distance between them. Some researchers have proposed that these quantum connections could extend on a larger scale, creating a kind of communication across the universe that mirrors the interconnectedness in a conscious mind. If entanglement exists on a cosmic scale, it could provide a mechanism for a unified awareness, enabling instant connectivity across vast distances, similar to how neurons communicate in the brain. Yet another experimental method involves studying large-scale cosmic structures and searching for unexpected patterns or anomalies. If the universe were conscious, we might expect to see evidence of self-organization or purposeful structure beyond what randomness alone would produce. For example, researchers are investigating cosmic phenomena such as dark matter and dark energy, which make up the majority of the universe but remain largely unexplained. It's possible that studying these mysterious components could reveal new insights into the universe's inner workings and hint at an underlying consciousness, if such a concept has any empirical basis. A particularly radical approach involves looking at how we, as conscious beings, interact with the universe. Some interpretations of quantum mechanics, like the von Neumann-Wigner interpretation, suggest that consciousness plays a direct role in determining physical reality, as seen in the observer effect, where particles behave differently when they are observed. If our consciousness can indeed affect the physical universe at a quantum level, this could imply a deep connection between individual minds and a universal consciousness. Researchers could potentially design experiments to explore whether conscious observation has measurable effects on large-scale quantum phenomena, which might reveal a relationship between human awareness and universal processes. While none of these methods can definitively prove universal consciousness, each offers a small step toward understanding the role consciousness might play in the universe. By pushing the boundaries of physics and cosmology, scientists are beginning to develop a framework that could, one day, provide evidence for or against the cosmic consciousness hypothesis. These experimental approaches are speculative, yet they challenge us to think beyond conventional boundaries. While measuring universal consciousness remains a distant goal, these early steps invite us to reimagine what science can achieve. Testing whether the universe is conscious may seem like a bold or even impossible undertaking, but history has shown that the line between science and philosophy often shifts with new discoveries. If future research confirms even the slightest hint of universal awareness, it would fundamentally change our understanding of existence, reshaping the way we see ourselves and our place in the cosmos. Until then, scientists and philosophers alike remain at the frontier of this profound question, seeking ways to probe the unknown and uncover whether the universe might indeed have a mind of its own. The evolution of cosmic consciousness. Could consciousness itself be a journey, unfolding alongside the grand narrative of the cosmos? If the universe indeed harbors a form of awareness, it might not have always existed in its current state. Like stars that are born, shine, and ultimately fade, perhaps consciousness itself evolves, deepening in complexity and expanding in scope over cosmic eons. Imagine consciousness as a seed sown in the fertile ground of the universe's inception, a spark embedded in the very fabric of existence at the moment of the Big Bang. At first, it might have been a mere whisper, a faint awareness of being. But as the universe expanded, forming galaxies and stars, this fledgling awareness could have grown, stretching and evolving with each new astronomical structure that came into existence. In this vision, consciousness is not static. It is shaped by the same forces that govern the stars and planets, flowing and adapting as the universe unfolds. Perhaps, in the early universe, consciousness was primitive and formless, just as simple cells were the early life forms on Earth. But over time, as matter formed into increasingly complex systems from stars to galaxies to clusters, cosmic consciousness, too, may have taken on more intricate patterns, each new formation bringing it closer to self-awareness. As galaxies cluster together, connected by threads of dark matter like neurons in a vast brain, they may weave a growing web of awareness. Could it be that, with each passing epoch, this consciousness refines itself, developing new layers of complexity, much like a child growing and learning? Does the universe, in its grand age, develop something akin to wisdom, a profound awareness built on aeons of cosmic experiences? The thought beckons further curiosity. If consciousness grows as the universe does, is there a point at which it becomes fully aware of itself? Perhaps consciousness in its primordial form was content simply to exist, much like a dreamer who hasn't yet realized they're dreaming. But what if, one day, it awakens fully an ancient mind, finally grasping the entirety of its own existence? If we, as part of the universe, are milestones in this progression, each conscious mind could be a stepping stone toward this ultimate self-awareness. Every thought we have, every feeling we experience, might contribute to a larger tapestry of understanding within the cosmos. Are we, then, not only witnesses but also catalysts, helping the universe learn what it is, and why it exists. In this view, the evolution of cosmic consciousness is a journey from simplicity to profound self-recognition, a journey that spans the birth, life, and eventual death of stars and galaxies. Perhaps, in the end, it is a journey toward unity, where the universe not only understands itself but also finds peace within the grand design it has woven. The universe's capacity for self-regulation and self-awareness. If the universe is conscious, could it also possess an intrinsic drive to balance, protect, and evolve itself, much like the immune system of a living organism? What if, hidden within its cosmic forces, there lies a form of self-regulation, a universal instinct to maintain harmony across its vast expanse? Imagine that, just as the human body fights infection and heals wounds, the universe possesses mechanisms to preserve its integrity. This self-regulation might be subtle, imperceptible to us, but it could be what keeps the cosmic dance in sync, guiding the cycles of creation and destruction with an invisible hand. Black holes could act as cosmic filters, absorbing chaotic energies, while dark matter may serve as connective tissue, holding galaxies together in harmonious clusters. Are these not merely physical phenomena, but aspects of a grand cosmic symphony, ensuring that order emerges from potential chaos? What if this self-regulation leads to something even more profound, self-awareness? The universe, in managing its forces and formations, could be developing a reflective understanding, a way to sense its own existence through the network of galaxies, stars, and perhaps even conscious beings like us. We, after all, are made from its own matter, shaped by its laws, and connected by its essence. If the universe maintains itself, perhaps it also observes itself, each action taken echoing back to shape its evolving awareness. Could it be that each supernova, each spiral galaxy, each black hole serves as a sensor, contributing to the universe's awareness of itself? Just as neurons in the brain process information, cosmic events might communicate something to the larger whole. In this view, the universe not only reacts to disturbances, but also learns from them, refining its self-regulation and nurturing a form of wisdom. If the universe indeed regulates itself, perhaps our consciousness is an extension of its own vigilance, a small part of its vast awareness that has been given eyes to see and a mind to question. Our existence might be the universe's way of observing itself in finer detail, a means for it to ponder its own mysteries and origins through the lens of human curiosity. And so, as the stars align and galaxies drift, as the forces of creation and destruction perpetually balance, we might wonder, are we living within a universe that not only sustains itself but also strives to understand itself? Perhaps this capacity for self-regulation and awareness is leading the universe towards a state of ultimate equilibrium and existence in which it knows itself fully, maintaining harmony in an endless, intricate dance. The role of collective consciousness in the universe. If the universe possesses awareness, could each conscious mind be a vital part of its overarching intelligence, a fragment of a vast collective consciousness? Imagine that we, and all other conscious beings, contribute to a single, boundless awareness, each of our thoughts and emotions rippling outward, merging with the whole. In this vision, consciousness does not exist in isolation. Rather, every mind forms a thread in a larger web, an intricate network spanning galaxies and dimensions. When we think, feel, and experience, we may be adding unique impressions to this cosmic memory, each thought an offering to the universe's growing understanding of itself. Perhaps, like cells in a larger organism, our individual minds gather knowledge, process experiences, and feed them back to the universe, creating a feedback loop of awareness. What if, through this collective consciousness, we help the universe see itself from countless perspectives? Each life, whether human, animal, or something beyond our understanding, could act as a lens, allowing the universe to observe its many facets, comprehend its infinite possibilities. Every moment of joy, pain, discovery, and wonder might contribute to a tapestry of experiences that bring the universe closer to true self-knowledge. If we are all connected within this universal awareness, then our individuality might be an illusion, a temporary separation in service of a greater unity. Perhaps when we empathize, when we connect, we touch this deeper truth, experiencing glimpses of a shared consciousness that transcends our physical limitations. In this perspective, our lives are more than isolated events. They are integral to a grander scheme of understanding, each of us adding richness and diversity to the universe's awareness. And if this is true, then consciousness itself is a powerful force, not confined to the mind, but permeating the cosmos, linking every being in a network of infinite potential. We might ask, are we mere witnesses, or are we collaborators in this universal mind, each of us essential to its self-realization? Could it be that by seeking knowledge, love, and understanding, we fulfill a cosmic purpose, helping the universe comprehend the depths of its own existence through our individual journeys? Perhaps our very thoughts are threads in the fabric of a collective awareness, drawing us all toward an interconnected whole, an infinite consciousness in which we all belong. The convergence of science and spiritual wisdom. As we probe deeper into the mystery of a conscious universe, could it be that science is only now discovering what ancient spiritual traditions have long intuited? Across cultures and centuries, mystics and sages spoke of a cosmos alive with spirit, a vast unity where the boundaries between the self and the universe dissolve. Perhaps modern science is not so much pioneering a new understanding as rediscovering truths woven into the fabric of spiritual wisdom. Imagine that the universe, in its pursuit of self-awareness, has whispered these secrets to countless generations, encoded within the philosophies and sacred teachings of the world. The ancient concept of oneness, found in the Upanishads, Taoist teachings, and indigenous beliefs worldwide, suggests that all existence is interconnected, part of a single, living whole. These teachings may have hinted at a conscious universe long before the notion entered scientific discourse, urging us to look beyond the material and sense the unity beneath. Now, as science advances, it begins to mirror these spiritual insights. The interconnectedness of quantum particles, the strange behavior of matter observed in quantum mechanics, and the structure of the cosmic web all hint at a hidden unity underlying all things. Could it be that science and spirituality, two branches of human understanding, are finally converging? Each from different angles, they lead us toward the same question. Is the universe alive, self-aware, and bound together in a cosmic consciousness? In this union of thought, modern theories like quantum entanglement and the holographic principle become bridges, linking scientific investigation with age-old wisdom. Perhaps the universe has encoded itself in dual languages, one of equations and one of myths and symbols. As we decode both, we come closer to a holistic understanding that neither alone could fully capture. Science, rooted in observation, and spirituality, based in introspection, may together form a fuller picture, illuminating a conscious universe that transcends the physical and the mystical. Could it be that our quest for knowledge is a continuation of this ancient dialogue, a whisper from the universe calling us to remember a timeless truth? In seeking answers, we may be reconnecting with this wisdom, glimpsing a universe that is not only conscious but deeply aware of its unity. And perhaps it is in this convergence where scientific rigor meets spiritual insight that we will find the true nature of existence, an understanding that unites mind and matter, self and cosmos into a single, boundless awareness. In this view, science and spirituality are not opposing forces but partners in the same exploration, leading us toward a revelation as old as humanity itself, that we are threads in the same cosmic fabric, drawn together by a purpose beyond our understanding, helping the universe know itself. The language of the universe. If the universe possesses consciousness, might it also have a way to communicate a language woven into the very fabric of existence, subtle yet profound? Imagine that every pulse of a quasar, every gravitational wave, every photon that travels across vast interstellar distances is a message, a glimpse of a hidden syntax that the universe uses to express itself. This language would not be bound by words or symbols, but rather by patterns and vibrations, by the movements of celestial bodies and the resonance of forces we are only beginning to understand. Stars, black holes, and cosmic rays might be its vocabulary, each cosmic event a phrase in an ancient, ongoing dialogue. Could it be that this language is not simply the universe's method of speaking to itself, but also its way of communicating with us, its conscious inhabitants? As we explore the cosmos, our discoveries might be more than scientific breakthroughs. They could be moments of revelation where the universe shares its story. When we observe the spiral of a galaxy or decode the structure of atoms, we might be deciphering fragments of a message that has echoed across time and space, a message waiting to be understood. And quantum phenomena, where particles seem to know they are observed, could be clues that the universe is responsive, shaping its reality based on our awareness. What if our minds too are attuned to this universal language? In moments of insight, inspiration, or profound peace, we may be tapping into a dialogue far beyond our individual thoughts. These experiences might not be random, but are moments when we glimpse the unity of all things. Moments when the universe shares its secrets with those who listen. Imagine standing beneath a vast starlit sky. The stars shimmer like distant embers, scattered across an infinite canvas. The night feels timeless, eternal, and yet, science tells us this grand spectacle has a story, one that began billions of years ago. But stories don't just begin, they also end. And so we must ask, will the universe itself come to an end? If so, how? This question is both humbling and haunting. What lies ahead for the cosmos? Will it fade into eternal darkness, collapse upon itself, or be ripped apart in a catastrophic finale? The universe, vast as it is, holds secrets about its ultimate destiny, and these secrets are written in the language of physics, a language we are only beginning to decipher. I think of the universe as a ticking clock. At its birth, with the Big Bang, the clock was wound up, its hands set in motion. Over billions of years, it has ticked forward, creating galaxies, stars, and even life itself. But like any clock, it may one day wind down. The question is, what does that final tick look like? Is it the silence of a stopped clock, or an explosion that shatters the mechanism entirely? We are not the first to ponder this cosmic mystery. For centuries, philosophers, scientists, and dreamers have gazed at the heavens and wondered about the end of all things. Today, armed with telescopes that peer billions of light years into space, and equations that reveal the universe's hidden workings, we have begun to glimpse possible answers. These answers paint a picture that is as awe-inspiring as it is unsettling. In this journey, we will explore the universe's potential fates. We'll begin with its origins, tracing the story of its expansion and the forces that drive it. Then we'll examine the leading theories about how it might all end, from a slow, freezing demise to a dramatic collapse or an ultimate ripping apart. Along the way, we'll pause to reflect on what these scenarios mean, not just for the cosmos, but for us, the tiny beings who dare to wonder about it. So, take a deep breath and prepare to dive into the ultimate question. What is the fate of the universe? And what might it reveal about our place within it? The answers may not be comforting, but they are certain to ignite your sense of curiosity and wonder. Because in the end, contemplating the universe's story is, in many ways, contemplating our own. Part 1. Understanding the universe's expansion. The Big Bang and aftermath. To understand the fate of the universe, we must first revisit its beginning, the Big Bang. Imagine an unimaginable singularity, a point smaller than an atom, but holding all the energy and matter that would become the universe. About 13.8 billion years ago, this singularity exploded, not into space, but creating space itself. Time began, energy burst forth, and the universe began its grand expansion. Evidence of this explosive beginning is all around us. One of the most compelling pieces is the cosmic microwave background radiation (CMB), often called the afterglow of the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson, the cosmic microwave background radiation is a faint hum of energy that permeates the universe, a relic from when the cosmos was just 380,000 years old. It's as if the universe left behind an echo of its birth. Another key piece of evidence is redshift. When we observe distant galaxies, we see that their light shifts toward the red end of the spectrum. This redshift is caused by the stretching of light waves as the universe expands. Edwin Hubble's discovery of this phenomenon in the 1920s revealed a startling truth. Galaxies are moving away from us, and the universe is getting bigger. But what does this mean for the future? To answer that, we must understand not just that the universe is expanding, but how. Is this expansion slowing down, speeding up, or staying constant? These questions lead us to the mysterious force driving the cosmos's growth: dark energy. Think of the universe like a balloon. At the Big Bang, the balloon began to inflate. Over time, the rate of inflation has changed, influenced by the push and pull of different forces. Gravity, the force that pulls matter together, acts like a brake, trying to slow the expansion. But dark energy acts like an invisible hand, pushing the universe outward at an accelerating pace. This push and pull dynamic will shape the universe's ultimate fate. The story of the Big Bang is not just a story of beginnings. It's the first chapter in a larger cosmic narrative, one that sets the stage for the universe's possible endings. With the groundwork laid, we can now explore the scenarios scientists have envisioned for how this story might conclude. Current state: accelerating expansion. Today, scientists have discovered a surprising and critical truth. The universe's expansion is not just continuing, it's accelerating. This revelation came in the late 1990s, when two independent teams of researchers studying distant supernovae noticed something unexpected. The supernovae appeared dimmer than predicted, indicating that they were farther away than they should have been if the expansion rate were constant. This was the first evidence of an accelerating universe. The force driving this acceleration is known as dark energy, a mysterious entity that makes up about 68% of the universe. Dark energy is not well understood, but it acts as a kind of anti-gravity, pushing galaxies apart rather than pulling them together. Unlike matter or radiation, which diminish as the universe expands, dark energy's effects seem to grow stronger over time, dominating the universe's behavior on the largest scales. To grasp this, think of a race car. In the early universe, the expansion was like a car speeding up a hill, gravity working against it. But now, it's as if the car has reached the top and is speeding down an endless slope, propelled by an unseen force. This accelerating expansion has profound implications for the universe's fate. If dark energy continues to dominate, galaxies will drift farther and farther apart. Eventually, stars will burn out, leaving behind a cold, dark cosmos. This scenario, known as the Big Freeze or heat death, envisions a universe where all energy is spread so thin that no meaningful interactions can occur. Yet dark energy also raises questions. What is it? Is it constant, or could it change over time? Some theories suggest dark energy might grow even stronger, leading to a Big Rip scenario where galaxies, stars, and even atoms are torn apart. Others propose it might weaken, allowing gravity to eventually pull everything back together in a big crunch. The accelerating expansion is a reminder of how much we have yet to learn about the universe. It challenges our understanding of physics and pushes us to ask deeper questions about the forces that shape our reality. As we explore the possible endings of the cosmos, this enigmatic force will remain at the heart of the mystery. Part 2. Possible scenarios for the universe's end. Heat death, the Big Freeze. Among the possible endings for the universe, heat death stands as one of the most somber and inevitable scenarios. Imagine a cosmos where all the stars have burned out, their light extinguished, leaving behind only faint remnants like white dwarfs, neutron stars, and black holes. The universe, once vibrant and filled with activity, becomes a dark, cold void. This scenario is rooted in the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases over time. In the context of the universe, this means energy will gradually spread out, becoming less and less useful for sustaining processes like star formation or even chemical reactions. Over trillions of years, galaxies will disintegrate as their stars fade away. The remaining particles of matter will drift apart, their movements slowing as temperatures approach absolute zero. To picture heat death, think of a campfire on a cold night. At first, the fire blazes brightly, radiating warmth and light. But as the fuel burns away, the flames shrink, the embers cool, and eventually, only ash remains. The universe, in this analogy, is the fire, and its energy is the fuel. Current models suggest that heat death is the most likely outcome if dark energy continues to dominate and the universe keeps expanding forever. In this eternal expansion, distances between galaxies will grow so vast that even light cannot bridge the gaps. Without sources of energy or interaction, the universe will enter a state of maximum entropy, a heatless death where nothing can happen. Yet the thought of heat death raises profound philosophical questions. If the universe ends in stillness, does that render all its past activity meaningless? Or does the beauty of the cosmos lie not in its ultimate fate, but in the journey the stars, galaxies, and lives that once filled it with light and purpose? Heat death is not a sudden end, but a slow fading away, a whisper of the universe's former grandeur. It challenges us to reflect on time's inexorable march and the fleeting nature of existence. And while this gradual fading may seem bleak, it also offers a humbling perspective. The universe, like all things, follows its own natural course, a progression guided by laws we strive to understand. In the stillness of heat-death, there is a quiet inevitability, a reminder of the fragility and transience of all that we hold dear. But perhaps the story doesn't truly end here. As with any grand narrative, every conclusion invites a new beginning. Might there be unseen mechanisms or phenomena yet to be discovered that could alter this trajectory? Could remnants of the universe's energy find a way to rekindle activity, defying the entropy that seems inevitable? The heat-death scenario leaves us with these haunting yet beautiful questions, compelling us to cherish the universe in its current, vibrant state. After all, we are fortunate to exist in a fleeting moment of warmth, light, and life, a brief oasis in an otherwise indifferent cosmos. The Big Crunch. Now let's imagine a universe where expansion doesn't continue forever. Instead, gravity, the force pulling everything together, takes the upper hand. Over time, this opposing force could slow the universe's expansion and eventually reverse it, causing everything to collapse inward. This scenario is known as the Big Crunch. Picture the universe as a cosmic elastic band. For billions of years, the band stretches, expanding outward as galaxies drift apart. But at some point, the pull of gravity becomes too strong. The band snaps back, drawing all the galaxies, stars, and matter back toward a single, dense point, a dramatic reversal of the Big Bang. This potential outcome depends on the universe's total density, the combined mass and energy it contains. If the density is high enough to overcome the momentum of expansion, gravity will halt the outward push and trigger contraction. Scientists refer to this as a closed universe. As the universe contracts, the distances between galaxies shrink, temperatures rise, and stars collide in violent interactions. Eventually, everything converges into an unimitably dense and hot state, similar to the initial singularity that sparked the Big Bang. The cosmos could end where it began, leaving behind a singularity, or perhaps igniting another cycle of expansion in what some call a big bounce. But is the Big Crunch likely? Current observations suggest not. With dark energy driving accelerated expansion, the universe's density appears too low for gravity to reverse the trend. Nevertheless, the possibility of a cyclical universe remains an intriguing idea, raising profound questions. Could time itself restart? Are we part of an eternal loop of expansion and contraction? In this vision of cosmic destiny, the Big Crunch is both an ending and a potential beginning of fiery collapse that might give birth to another universe, starting the story anew. The Big Rip. Imagine a universe where the fabric of space-time itself tears apart. This dramatic scenario, known as the Big Rip, envisions an ending driven by the relentless growth of dark energy. Unlike other endings where gravity or entropy dominates, the Big Rip unfolds as dark energy grows stronger over time, ultimately overwhelming every force that holds the universe together. In this scenario, dark energy doesn't just accelerate the expansion of the universe, it accelerates it exponentially. Galaxies move farther apart at increasing speeds. Over billions of years, this acceleration becomes so extreme that it begins to tear apart galaxy clusters, then galaxies, and finally stars and planets. Even atoms, the fundamental building blocks of matter, are ripped apart in the final moments. To picture the Big Rip, think of a piece of fabric being stretched. At first, the stretching is gentle, but as the tension increases, the fabric begins to tear at its weakest points until it completely unravels. In this metaphor, the universe is the fabric, and dark energy is the force pulling it apart. This cataclysmic end would unfold as follows. 1. Billions of years before the end, galaxies are torn from one another as dark energy's influence grows stronger than gravitational forces. 2. Millions of years before the end, individual galaxies disintegrate, their stars flung into the void. 3. Moments before the end, stars, planets, and even atoms are pulled apart, leaving a universe devoid of structure or matter. The timeline for the Big Rip depends on the behavior of dark energy. Current models suggest dark energy is relatively stable, but if it grows more potent over time, a property physicists call phantom energy, the Big Rip becomes a viable outcome. This scenario raises profound questions. What happens when space-time itself is torn apart? Does time cease to exist? Could remnants of the universe persist in some form, or would reality itself end in complete dissolution? The Big Rip, while speculative, reminds us of the sheer power and mystery of dark energy, a force we are only beginning to understand. It is both a terrifying and awe-inspiring vision of the universe's potential fate, one where the end is not a gradual fading or a collapse, but an explosive tearing apart of everything that has ever existed. Part 3: Philosophical Implications and Unanswered Questions. What does the end mean for life? What happens to life when the universe itself approaches its demise? This question forces us to confront not just the physical realities of cosmic endings, but their implications for existence. Life as we know it is bound by the conditions of the universe, its laws, its resources, and its time. But if those conditions change drastically, does life have a future? Consider heat death, where stars extinguish and the cosmos cools to near absolute zero. In such a scenario, even the most advanced civilizations might struggle. Imagine building a fire in a snowstorm that grows colder and darker by the moment. How could life persist in such relentless entropy? Yet history shows us the resilience of life. On Earth, extremophiles thrive in the harshest environments, deep sea vents, boiling hot springs, and even radioactive wastelands. Could life, or something like it, find ways to endure in the distant future? Perhaps intelligent species could harness energy from black holes or tap into quantum phenomena beyond our understanding. The possibilities stretch the limits of imagination. But what if even these strategies fail? Does the end of life in the universe mark a true ending? Or is there meaning in the brief moments of light and complexity that life brought to the cosmos? These are questions not just of science, but of philosophy, forcing us to ponder whether permanence is a prerequisite for significance. Could advanced civilizations escape these fates? If the universe's natural course leads to oblivion, could advanced civilizations find a way to defy it? Science fiction often speculates on such possibilities, but even speculative ideas are rooted in the boundaries of physics. One idea is the Dyson sphere, a colossal structure built to harness the total energy output of a star. Such technology could extend the lifespan of civilizations, allowing them to thrive even as the universe dims. But what happens when there are no more stars? Perhaps more radical are theories of escaping the universe itself. The concept of parallel universes or a multiverse suggests that our cosmos might not be alone. Could a sufficiently advanced civilization open portals to other universes, transferring their existence to a younger, more hospitable cosmos? If so, they might survive not just the end of this universe, but potentially any number of universal lifespans. Then there's the question of time itself. Some theories propose that time is not a fundamental property, but an emergent one, tied to the universe's structure. If time ends with the universe, what does that mean for beings within it? Could they find a way to live outside of time, in a state of timeless existence? Or would such a concept defy even the wildest reaches of imagination? What these speculations reveal is the boundless creativity of the human mind. The universe's end might seem inevitable, but as long as questions remain unanswered, the door is open to possibilities we have yet to comprehend. Perhaps the greatest lesson is not about survival, but about the resilience of curiosity, the drive to understand and adapt, no matter how daunting the challenge. Is time an illusion? If the universe ends, what happens to the concept of time? To explore this, we must first ask, what is time? For most of us, time is a constant, flowing river, a relentless current that carries us from one moment to the next. But is this river real, or is it an illusion shaped by our perception? Theories in physics suggest that time might not be fundamental but emergent, a byproduct of the universe's structure and processes. If the universe ceases to exist, does time dry up like a river evaporating under a scorching sun? Or does it persist in some form we cannot yet fathom? Consider the Big Freeze, where the cosmos becomes a static, cold expanse. Without events or motion to mark its passage, what meaning does time have? In the Big Rip, where everything disintegrates into its smallest components, could time itself unravel, reduced to a meaningless concept? Time, in this sense, is deeply tied to change. It is the rhythm of the universe's dance, the beats of stars being born, galaxies colliding, and life evolving. Without change, the melody ceases. Does this mean time is merely an artifact of motion, a measure of the universe's activity? Or is it something more profound? The idea of time's end also raises philosophical questions. If time has a beginning and an end, is it a finite resource, like sand slipping through an hourglass? Or is it cyclical, a loop that resets with each new cosmic cycle, as some theories of the multiverse suggest? Could we ever exist outside of time, experiencing reality in a way that transcends our linear understanding? These questions remind us of the enigmatic nature of time. Whether it's an illusion, a dimension, or something entirely beyond our comprehension, its fate is inextricably linked to the universe's destiny. Time is the silent witness to all cosmic events, and pondering its end forces us to confront the ultimate mystery of existence itself. Are there cycles? Could the universe itself be part of an eternal cycle, dying and being reborn like a cosmic phoenix rising from its ashes? This idea lies at the heart of cyclic models, which suggest that the universe's end might not be a conclusion, but a prelude to a new beginning. One such model is the Big Bounce, a theory that envisions the universe contracting after its expansion reaches a peak. Instead of collapsing into a singularity as in the Big Crunch, the universe rebounds, triggering another Big Bang. This cycle of expansion and contraction could repeat indefinitely, creating an endless loop of cosmic rebirth. Another perspective comes from multiverse theories. These suggest that our universe is just one of countless others, each with its own birth and death. If universes can emerge from the remnants of others, could our cosmos be part of an interconnected web of existence, where endings are never absolute but merely transitions? The metaphor of a phoenix captures this concept beautifully. Like the mythical bird that perishes in flames only to rise anew, the universe could regenerate from its own demise. Each cycle would erase the past while laying the groundwork for future possibilities, an eternal dance of destruction and creation. But how might such cycles occur? Could remnants of the current universe, black holes, quantum fluctuations, or even dark energy seed the conditions for a new one? The details remain speculative, yet they ignite profound questions about the nature of existence. If cycles are real, is there a purpose to them? Do they follow a grand design, or are they random acts in an infinite cosmic play? Cyclic models challenge us to think beyond linear timelines and finite conclusions. They suggest a universe that, like a heartbeat, pulses with life and renewal. And while we may never witness these grand cycles, contemplating them reminds us of the vast possibilities that lie within the cosmos. Perhaps, in the universe's story, there are no true endings, only endless beginnings. Throughout this journey, we've explored the universe's potential fates. From the chilling stillness of heat death to the fiery collapse of the Big Crunch, the violent unraveling of the Big Rip, and the hopeful renewal of cyclic models. Each scenario presents profound questions about existence, time, and the nature of reality itself. But does the end of everything mean the end of meaning? Perhaps not. Meaning is not solely derived from permanence. It often lies in the fleeting, the transient, the moments that shape our experience of the cosmos. The stars that shine above us, the life that thrives on Earth, and the curiosity that drives us to seek answers, these are what define our place in the universe. As we contemplate the universe's story, we must embrace its uncertainties. The vastness of the cosmos humbles us, reminding us of our small yet significant role as observers and thinkers. Whether the universe ends in silence, destruction, or rebirth, its journey inspires awe and wonder. So, as you look up at the stars, remember this: the universe's greatest mystery is not just in how it ends, but in how it compels us to question, to dream, and to seek understanding. And in that pursuit, we find meaning not in answers, but in the act of asking.
In far-off galaxies, galactic invaders are at work. 3 times daily, a strange flash pulsates across our sky. It is hundreds of times stronger than all of the world's nuclear weapons put together. But it wasn't made by people, and if one happens close enough to Earth, it could wipe out all life there. Most people on Earth don't know about the possible dangers in space. Imagine this: a huge star explodes in our galaxy, the Milky Way, sending a deadly burst of energy hurtling toward our planet. This is a gamma-ray burst, which is the biggest blast since the Big Bang. there are no signs that something bad is about to happen. And then it strikes. The radiation that is pumped up heats up the high atmosphere. Our layer of ozone heats up. Across the atmosphere, human beings burns to death from radiation 100 times the fatal dose. When the ozone layer gets thinner, temperatures rise all over the world. This makes storms, tsunamis, and hurricanes happen. Most life on the surfaces of land and water incinerates. This may sound like science fiction, but if a gamma ray burst from 100 light years away hit Earth, it could happen. Gamma ray bursts are the most bright blasts in the universe. They must have a huge amount of power because they're so far away and yet still so bright. As much energy as the sun will give off in its full 10 billion year life. We know there are many planets and many stars in the universe, so gamma ray burst could have wiped out a lot of different cultures. In the 1960s, this strange blast of radiation was first seen. At first, because these gamma ray bursts are so bright, most scientists thought they came from our own galaxy, the Milky Way. There are a few reasons for that. One of them is that if they are outside the galaxy, the energy is almost too much to believe. But back then, even the most powerful telescopes couldn't figure out where they were or how far away they were because the burst only lasted a few seconds and then went away. But then, scientists started to wonder about their afterglow. Most blasts in space leave a glowing trail behind that can last for days or even weeks. In the late 1990s, satellites with better optics and X-ray monitors were finally able to catch the afterglow of a gamma-ray burst. It became clear that gamma-ray bursts actually came from outside our galaxy, millions and billions of light years away. So, their power had to be really out of this world. The brightness of the gamma-ray burst is the same as that of 1,000,000 trillion suns. This huge explosion could wipe out all life on Earth. But why do they happen? We are very sure that a common gamma-ray burst is caused by the death of a star that is at least 10 times the mass of the Sun. And these kinds of stars aren't very common. When a very big star dies, it falls apart and forms a black hole. Black holes are made when a mass of matter shrinks to a point where it is so dense that light can't get out. But experts think that some of the star resists getting sucked into the center of the black hole. As a result, a high-speed spinning disk of matter forms around it. In a matter of seconds, plasma jets shoot out from the poles where it spins. These beams of energy unleash dangerous gamma rays into space. At the same time, the gamma-ray bursts are ejected, the collapsing star explodes or goes supernova to the extreme. Gamma-ray bursts are so bright because they take a huge amount of power and focus it on a very small area of the sky. Only one of every 300 gamma-ray bursts is directed toward us, so we only see one of those 300. Even if a gamma-ray burst happened not 100 but 1,000 light years away, the Earth could still be destroyed in a way that is similar to the end of the world. If a gamma-ray burst happens within 100 light years off the Earth, then it would be approximately 500 times brighter than the Sun and made in gamma rays. The energy sent to the high atmosphere of Earth would be the same as if 100,000 megatons of nuclear bombs went off. The ozone would be depleted, we'd have acid rain, but we'd also have flash burns, incineration of vegetation, perhaps something resembling nuclear weather. So many species could go extinct all over the world. Now, the other side of the Earth would be a special place to be, because gamma rays don't go through the Earth, so you wouldn't get flash burned if you were there. However, the repercussions of altering the atmospheric composition and ozone depletion would ultimately come to the other side, and there, nobody knows what will happen. This nightmare scenario has a 1 in a trillion probability of occurring once in Earth's history. It's going to be a nasty day if you get caught in the beam. for the reason that this is extremely powerful radiation. You don't want to be in the vicinity of this sort of energy, since it has the potential to break down your own molecules. Currently, there is no way to protect humanity against gamma-ray bursts that occur in close proximity to Earth. They move at the rate of 186,000 miles per second, or the speed of light. By the time we detected them, they would have already struck our planet. Gamma rays bursts could pose a hazard to the Earth or to anything living that came within their born sight. Astronomers think that gamma ray bursts could be the cause of some mass extinctions on Earth. The one that happened 450 million years ago and killed off the Ordovician and Silurian species was probably the worst. Creatures that lived near the surface of the ocean were hit much harder than those that lived deep in the ocean. This is consistent with what would happen during a strong gamma-ray burst. In a galaxy the size of the Milky Way, gamma-ray bursts happen about once every few 100,000 years, according to astronomers. Even though they can be very bad, you have to be pretty close to be hurt by one. A gamma-ray burst happens about once every 5 million years, which is close enough to affect life on Earth. In other words, since the Earth was made 4.6 billion years ago, there have been about 1,000 events. So the chances of a close gamma-ray burst aren't zero, but they're low enough that you don't need to worry about them, unless you want to live for about 5 million years. Humanity obviously made it through the gamma-ray explosion unharmed, but this still demonstrates how far their effects may travel. Don't fret. Threats to Earth from gamma-ray bursts are extremely low. All of the closest contenders for gamma-ray bursts have been studied by astronomers, and none of them are either close enough or orientated in a way that would cause them to strike Earth. Therefore, what do you think? In our solar system, Earth shines like a sapphire jewel. We go about our daily lives without knowing that trouble could be coming from deep space. The routes that Earth and most other things take around the sun can be predicted. Most of the time, things are quiet and easy, but sometimes they get crazy and violent. Earth can be hit by space rocks, zapped by dangerous space weather, jolted, jostled, and threatened by the object's energy and cosmic forces. The Earth is on a wild ride through space that is often very dangerous. When you're moving fast in on a predetermined path, you hope nothing crosses because there's nothing you can do. Rusty Schweickart used to be an astronaut, so he knows how dangerous things in space can be. During the Apollo 9 flight in 1969, he was in charge of the lunar module. He is sending out warnings about the risks of an asteroid named Apophis that is getting too close to be safe. Everyone noticed him right away because the probability of impact was quite high. In fact, it was significantly greater than any effect probability we had seen before. Schweickart has a scary example from real life that shows how bad an asteroid, even one smaller than Apophis, can be when it hits. June 30th, 1908, 7:15 a.m. A half-football field-sized object came hurtling down from space at about 34,000 miles per hour and made a stream of fiery gas behind it. Within minutes, the fireball hit Earth's atmosphere and burst violently near the Tunguska forest in Siberia. As a result, the explosion was the greatest ever recorded in the history of the planet. The explosion split the waves, which then set fire to 8 million trees in an area that was bigger than half of Rhode Island. Because the explosion happened in a place with few people, no one died directly from it. If that asteroid had hit just a few hours later, it would not have hit Siberia, but Europe. And if it had exploded in the air over one of Europe's biggest cities, 1 million people would have died. For the last 100 years, the Tunguska explosion has been shrouded in controversy. Many researchers now think an asteroid was the explosive trigger. Incredibly, it never even impacted the ground. Rather, it exploded 5 miles above Siberia's frozen ground. When it smacks into the lower atmosphere, doing about 50,000 miles an hour, it's like an egg smashing on the concrete. Energy equivalent to 15 megatons of TNT was released in the Siberian explosion, making it 1,000 times greater than Hiroshima. Over a huge city, this would be catastrophic. NEOs, or near-Earth objects, were the name given by scientists to these trespassers. They are comets and asteroids, leftover debris from when the planets formed. The Oort cloud is a part of the Kuiper belt that extends past Neptune and is where comets travel. Between Jupiter and Mars, asteroids take a curved path, but their orbital trip isn't always routine. We don't have to worry too much about asteroids because they circle in a somewhat orderly belt between Mars and Jupiter. But when one gets away and all that mass and energy is going toward Earth, that's when the astronomers start to worry. It's not uncommon for cosmic debris to be jolted out of orbit and headed for Earth. The majority of it is evaporated by our planet's dense atmosphere. A larger object, however, is able to break through Earth's atmosphere and crash to the surface. Asteroids are a real and dangerous threat if you wish to look to the cosmos for the powers that would have us dead. Just like it did previously, it will happen again. 65 million years ago, an asteroid the size of a small city plummeted down from the sky. It exploded in the Yucatan Peninsula, near the town of Chicxulub in Mexico, with a force of 100 million megatons of TNT. Here we see Earth hurling billions of tons of its crust into space, creating a blanket that blocks out sunlight, destroying the food web at its roots, and killing off countless species. The ferocious impact is thought to have been a factor in the extinction of the dinosaurs. We can think of asteroids as being bad things, but if it were not for an asteroid, we wouldn't be here today. Our mammal ancestors were running on their foot trying to avoid being appetizer for T-Rex. T-Rex gets taken out. Well, this opened up an ecological niche that allowed our mammal ancestors to evolve to something more ambitious that are route and outcomes the primates, and among the primates, we have people. But it's strange that the same kind of cosmic boulder that made it possible for humans to live could one day wipe us out. In 1998, Congress asked NASA to find all near-Earth objects that were at least half a mile across, and what they found was unsettling. There are more than 850 NEOs near our vicinity. These asteroids are our nearest and most dangerous space friends. Finding these near-Earth objects is a bit like keeping an eye on storms. As you watch it day after day, you get a better idea of its path and can figure out where it's going, how big it is, and how fast it would hit the Earth if it did. By using telescopic technologies, NASA's Space Guard survey has detected over 90% of all near-Earth objects deemed harmful. These scary things could hit Earth with more power than all of the nuclear weapons on the world right now. Such an impact could trigger mass extinction. We wouldn't expect one to hit every few hundred, thousand, or millions of years, but if one did, it could wipe out different parts of the population. So there are events that happen very rarely but have big effects when they do. If they hit Earth, they would have impacts all over the world. They would not only wipe out a continent with very strong shock waves, but the debris would also be thrown into the air and land all over the planet, heating the air to 1,000 degrees. And all the vegetation all over the world where that happens would flash into flames. Smaller objects could also cause disasters, so Congress has asked NASA to find all NEOs with a diameter of 500 feet which is as big as the Colosseum in Rome. A big object like that could wipe out a city or even a small state. Scientists are most worried about the asteroids they haven't found yet, not the ones they have found. Well, at the moment, there are about 2,000 objects that we can't say for sure won't hit Earth. We now have the technology to keep near-Earth objects from ever hitting Earth again. We can now literally start to change the local solar system to make it better for our life. The question is whether or not we will end up like the dinosaurs. It's hard to believe that the Earth has been around for more than 4.5 billion years because it's been through a lot since it was born. Asteroids that come into our orbit every year keep hitting our world like a boxer, but one day Earth could be knocked out. We've learned that near-Earth objects fly by us all the time, and we're getting more and more able to change our surroundings to help us stay alive. A rock in space named Apophis. In 2004, this pockmarked rock about 750 feet across came close to Earth. Now, it's scheduled to pass dangerously close to our planet again on Friday the 13th in April 2029. So, in 2029, Apophis will get closer to us than our Rome communication satellites that circle the Earth. If you are in the right place, you will be able to see Apophis pass by the Earth with your own eyes. That's how close that rock is going to get. You won't even need binoculars. Over 99% of the time, Apophis will miss the Earth in 2029. However, if it passes the Earth at an exact distance of 18,893 miles, it may pass through a gravitational keyhole, a small area in space that is only a half-mile wide. If this happens, Apophis could be thrown off by the Earth's gravity, which could change its path. It could make Apophis come back and hit Earth on April 13, 2036, 7 years later. The gravitational effect of the Earth would cause it to bend, cause the Apophis's orbit to enlarge to precisely the size, which 7 years later, it will come around and hit the Earth. At the present time, Apophis has 1 in 45,000 chance of delivering a deadly blow in 2036. It's one thing to say that there's a 1 in 45,000 chance that it will hit the Earth, but what you really want to know is if there's a 1 in 100, 1 in 10, or 1 in 1 chance that it will hit the Earth. We have to look at Apophis the same way we look at any natural disaster. You know the date of the hit, when it happened, and the angle of the orbit, so you can make a map. It starts in western Siberia, cuts across and down the Pacific Ocean near California, goes through Central America, and ends in Western Africa. Scientists have come up with a scary idea about where Apophis could strike. With a force of more than 1 million megatons of TNT, the asteroid could hit the Pacific Ocean off the coast of California. Such an impact would make a hole in the water 5 miles wide and 9,000 feet deep. This would cause tsunamis with waves up to 50 feet high to hit the coast, resulting in unimaginable human loss. If a rock 1,000 feet across hits the ocean, that's not a good thing. For that kind of thing, scientists are working on ways to stop such a cosmic strike from happening right now. A possible plan is to blow up an asteroid. But some people worry that this could make the problem worse by sending more pieces of the asteroid our way instead of just one. So, the new goal for experts is to change the path of asteroids that could hit Earth. Change its velocity by a 10,000th of a mile per hour so that it will miss the Earth instead of hitting it. If we know about an asteroid far enough in advance, we can change its path. Although a space probe has landed on an asteroid in the past, the most challenging idea is launching a manned mission. Once landing on the rock, astronauts could mount a radio transponder to track its whereabouts. Now, the United Nations plans to draft a treaty which will include who will be responsible for deflecting killer asteroids. If we are so careless that we keep doing nothing even though we know this is going to happen, that will be a real crime. Any asteroid hitting the Earth will require international disaster response. In addition, training is required in disaster and emergency management institutions and the public regarding the asteroid threat. It is important that everyone is aware of the level of threats and the potential to eliminate this threat. Apart from all these, amateur astronomers can work together with scientists to defend our planet. Amateur astronomers can help identify smaller and potentially destructive asteroids hidden in the universe. So would you like to be an amateur astronomer? Who knows? Maybe you can be one of the guards of our home. A peculiar entity resembling a skyscraper in size and form hurtles through the solar system at speeds exceeding 100,000 miles per hour, potentially capable of catastrophic impact if it were to collide with Earth. As the data poured in, astonishment gripped everyone, revealing that this phenomenon was unlike anything encountered before. This enigmatic object originates from beyond our solar system, marking our inaugural encounter with an interstellar visitor. Dubbed Oumuamua by astronomers, it symbolizes a messenger from distant realms, offering a glimpse into the mysteries of the cosmos. Oumuamua represents our galaxy's outreach, marking a historic encounter with an authentic extraterrestrial entity. Astronomers worldwide embark on a frenzied quest to unveil its profound secrets, probing its origins, potential threats to Earth, and even contemplating the possibility of it being an alien spacecraft. Perched atop the majestic Mauna Kea, the colossal volcano gracing Hawaii's Big Island, lies the domain of some of the world's most formidable telescopes. Here, astronomers diligently scan the nocturnal expanse, vigilant for asteroids and comets posing potential threats to Earth. Among these watchful stewards is astronomer Rob Warwick. His official mantle as a planetary defense researcher underscores the solemn mission, shielding our planet from celestial hazards. On October 19, 2017, Rob's vigilant gaze catches sight of a celestial anomaly hurtling through the cosmos like an errant missile. The rapid motion of this enigmatic object leaves a fleeting gray streak across the celestial canvas, indicating its formidable velocity. With its trajectory portending a cataclysmic impact rivaling that of a nuclear explosion, the urgency to track its course intensifies. Gathered at the Canada-France-Hawaii telescope, Rob and his team meticulously chart the object's path, relieved to ascertain its divergence from Earth's trajectory. Yet, the peculiarities don't cease. Unlike the familiar closed orbits of solar system entities, this visitor's trajectory remains open, hinting at its extraterrestrial origins. Confirmed to originate from interstellar realms, this sighting marks humanity's maiden encounter with an alien interloper. Scientists dubbed it Oumuamua, a Hawaiian term signifying messenger, marking an extraordinary find that unequivocally traced its origins beyond our solar system. However, Oumuamua hurtles through space with such velocity that astronomers face a scant few weeks to scrutinize its enigmatic features before it vanishes from earthly observation. Aware of the fleeting window, scientists mobilize telescopes worldwide, racing against time to glean insights into Oumuamua's mysteries. The paramount inquiry centers on deciphering its identity. Is Oumuamua an interstellar asteroid or comet? Remnants flung from the tumultuous genesis of distant solar systems? Drawing parallels with our own solar system's early dynamics, astronomers speculate that Oumuamua might embody similar celestial debris propelled into the interstellar void by gravitational forces. Dr. Meg Schwam and her team, Specialists in asteroid and comet research leverage the Gemini North Telescope in Hawaii, endeavoring to discern Oumuamua's form and dimensions, crucial pieces in unraveling its enigma. The anticipation was palpable. Would it resemble an asteroid or take on the appearance of a comet? Unfortunately, no telescopes possess the capability to directly measure its size and shape. Researchers rely on the amount of light Oumuamua will reflect back to Earth, data collected by numerous telescopes worldwide. This represents changes in brightness over time, with fluctuations between brightness and dimness. What factors contribute to the fluctuating light emitted by Oumuamua? According to Rob, the object's brightness variations are linked to its shape and motion. Visualize its elongated form. The longer edge reflects more light due to its larger surface area, while the smaller end reflects less light, resulting in reduced brightness. Oumuamua's elongated shape and tumbling motion lead to varying reflective surfaces, causing fluctuations in brightness. Astronomers analyze these brightness variations to estimate Oumuamua's dimensions. The light curve indicates a length-to-width ratio of approximately 6:1, rendering Oumuamua remarkably tall and slender, reaching heights between 650 to 785 feet. Its towering stature, akin to a skyscraper, traverses our solar system, prompting intense scrutiny to determine its nature. Deciphering Oumuamua's shape requires meticulous detective work, yet its classification as an asteroid or comet remains elusive due to its unprecedented form. Astronomers delve into possible explanations, including the asteroid hypothesis. The peculiarity of Oumuamua's cigar-like appearance intrigues scientists, sparking a quest for answers amidst the mysteries of space. Exploring the enigma of Oumuamua's peculiar shape leads to intriguing inquiries. Could colossal collisions within the solar system yield asteroids resembling it? Alternatively, might there exist a more extraordinary explanation, such as Oumuamua being an alien craft? Although Oumuamua's resemblance to an asteroid is plausible, its origin remains elusive. As Oumuamua fades from view, time becomes a pressing constraint for astronomers seeking answers. As Oumuamua speeds away, the urgency intensifies to gather data before it vanishes forever. The first interstellar visitor to our solar system, Oumuamua, presents a perplexing puzzle for investigators. Its elongated, cigar-like shape sparks speculation. Could it be an icy comet or an alien spacecraft? Despite resembling a long, thin cigar, Oumuamua defies typical comet characteristics observed in our solar system. Comets, usually a mix of rock and ice, vary widely in shape, but none resemble the skyscraper profile of Oumuamua. The journey of Oumuamua through interstellar space over millions of years might have drastically altered its appearance. If Oumuamua originated as an icy comet, the harsh conditions of interstellar space could have sculpted it into its current form. Micrometeoroids and dust encountered along its journey could have eroded the comet's surface over time. Gradually, the comet's surface thins and reshapes until it resembles a skyscraper, a stark departure from its lumpy beginnings. It's conceivable that a comet could share the same elongated shape as Oumuamua, but is there observational evidence confirming its comet status? Initially, astronomers anticipated Oumuamua to exhibit comet-like behavior upon its approach, shedding layers and forming a tail, as typical comets do near stars like the Sun. As comets draw close to stars, their icy surfaces vaporize, creating a distinct coma and tail of gas and dust. However, observations from the Very Large Telescope revealed no such coma around Oumuamua, challenging its classification as a comet. This absence of expected features led to Oumuamua being reclassified from comet to an unknown object, prompting further speculation about its true nature. Given its peculiar trajectory and passage through the solar system's habitable zone, some entertain the notion that Oumuamua could be an alien spacecraft, possibly sent to make contact with Earth. Seth Shostak from SETI points out that if Oumuamua were an extraterrestrial vessel, it might emit detectable radio signals, a possibility that warrants close monitoring before Oumuamua exits the solar system. Explorers from another world might need to establish contact with their home base or another civilization. If they were doing so, we might have intercepted radio signals from them. It's likely that extraterrestrial communication relies on radio waves, which can traverse the universe unimpeded by obstacles. The potential of Oumuamua being a spacecraft merits investigation. Scientists have made every effort. No transmissions have been detected yet. If Oumuamua is indeed an alien craft, it's operating in stealth mode. As Oumuamua vanishes from our telescopes, astronomers speculate about its journey. Initially an icy comet, Oumuamua evolves over time, sculpted by dust and radiation into its peculiar skyscraper shape. Astronomers believe Oumuamua is not alone. Countless interstellar objects traverse our solar system, ejected during its tumultuous formation. Despite being elusive, advanced technology and vigilant observation may unveil more interstellar visitors. Such encounters offer profound insights into the origins of planets and solar systems, potentially even shedding light on the possibility of extraterrestrial life. Though challenging, the scientific community eagerly awaits the next interstellar arrival. Oumuamua's departure marks the end of a remarkable journey, yet its legacy as the harbinger of discovery lives on, inspiring astronomers to continue their quest for knowledge in the boundless expanse of space. The Sun has been a friend to Earth for more than 4 billion years, warming and feeding it. Sadly, the thing that gives us life will probably be what kills our planet in the end. The Sun and the Earth are connected in a special way. The Earth is a certain size, has life on it, and has seas. And these things are all affected by the Sun. The Sun is the reason why there is life on Earth, and it will also be the reason why it will end. When our solar mother really turns up the heat, Earth's bond with the Sun will start to break down. Because it burns hydrogen into helium, the Sun gets hotter. One helium atom is made up of 4 hydrogen atoms. That means that there are bits of fuel moving around inside the Sun. And because of this process, the Sun has to get hotter and brighter to stay up. As the core of the Sun gets hotter, the upper part will get bigger and turn red. When you build a campfire, you put a lot of wood in it. When enough logs are burned, the whole thing falls down, sending out a huge burst of sparks and making the fire much brighter. In a way, because the Sun is currently burning hydrogen into helium, and you could say that helium is the ash of that process. And then, as the Sun collapses enough, the ash relights and the helium burns into carbon, and then things really heat up. At this point, the Sun will grow bigger and bigger until it becomes a red giant and burns up most complicated life on Earth. When the Sun turns into a red giant, it will grow to be 30 times bigger than it is now. This means that the Sun's surface will be beyond Mercury's orbit. The Sun will shine brighter by about 1,000 times. That's gonna make the Earth so hot that the outer crust, the rocks, the soil part of the Earth will melt. The whole planet would be a ball of glowing fire. The Sun will cook the planets closer to it, and even though it will turn red and get cooler, the Earth will get much hotter. Just leave the Earth a burnt cinder like a charcoal briquette. So that would be bad for all life on Earth. And it's not clear what will happen to the Earth. As a red giant, the Sun's size will change before it collapsing to become a white dwarf. The Sun, that was huge. suddenly becomes a sun that's very small and extremely dense, only about the size of the Earth, sitting down there at the center of our solar system, very much fainter than it used to be. Then everything starts to cool down, and since that object is no longer making energy, it too starts to cool down. The last thing that will happen to the solar system is that it will cool down and freeze. Before the sun turns Earth into a snowball, people will probably move to another world or die out. But the sun could dry up our world a lot faster. If the sun doesn't kill us during the red giant phase, it could kill us sooner if it gets bright enough to dry up the seas. Water is an important part of life, so if the Earth loses all of its water, that's another reason why life might go extinct, and it would again be the sun's fault. There might be ways for Earth to get more time. As the sun gets bigger, it also starts to lose mass, much faster than it does now. And of course, if it's getting less massive, it has less of a hold on the Earth. The Earth's orbit will get bigger as it moves farther away. So it's kind of a race between the growing sun and the rising heat from the sun and the Earth, which is actually moving away from that fire that's getting too hot. Even if our world doesn't get cooked or frozen by the sun, its future looks more and more bleak. In the far future, the Earth and the rest of the universe may have to deal with the biggest monster in the cosmos. No one thinks that the most dangerous enemy of Earth is hiding among the stars. The dark bad guy will tear the universe apart. Even galaxies will break apart. The stars and planets will fall apart. The Big Rip is the name given to the end of the world. When it starts, it won't stop until all of the atoms and nuclei in the universe aren't chopped up. The Big Rip is really the end of everything. A sad idea about what will happen to the universe in the end. We used to think that the universe, which is currently expanding, can reach a point of maximum expansion. The idea behind the Big Rip is that the growth will not only keep going and speed up, but will also tear everything apart as it goes. And there is something like a vacuum pulling everything outward. A strange thing called dark energy might be to blame. Probably the most important thing for cosmologists to do right now is to figure out what dark energy is. Dark energy is called dark because you can't see it. We can tell what it is because of the way it changes the way the universe's gravity works. You can only start to see the effects of dark energy when you look at its qualities on cosmological length scales that are billions of light years long. It causes things to be pushed farther away from each other and contributes to the expansion of the universe. In the 1920s, Edwin Hubble, after whom the Hubble telescope is called, was the first person to notice that the universe is getting bigger. But it wasn't until 1998 that a top team of scientists measured that this growth is speeding up like a train out of control. As the universe gets bigger, every other galaxy moves away from us. In normal growth, the size of each galaxy stays the same. But if the universe is expanding very quickly, then each galaxy can also grow. Scientists say that the Big Rip is the end of the universe. They have even made a countdown to the end of the world. 1 billion years to pull apart clusters of galaxies, then hundreds of millions of years to pull apart galaxies themselves. And then, to get to the size of the solar system, we're talking about hundreds of thousands of years. Then, it will take less than an hour to tear the Earth apart. It's kind of cool to imagine what that would look like. If we are in protective capsule watching things happen, we would see the swallow of darkness that starts coming towards us. At that point, we would no longer be able to see any stars. The Earth's layers would be peeled off and thrown away, one by one. Everything in us, including the molecules that hold us together, would be torn apart, and every atom that makes up your body would fly away to infinity within a very short time. Fortunately, mankind doesn't need to lose sleep over the Big Rip. Scientists think it will reach its peak in 50 billion years, when the universe will be over 3 times as old as it is now. It's a lot of fun for us to try to figure out if this is really going to happen, to imagine what might happen in a science fiction way, and to think about what might happen to us. Are there real dangers in deep space? Tomorrow, the sun could hurt us, others in the far future. But one thing is certain: something will terminate Earth and probably the entire universe. Once and for all, it's only a matter of time. It's useful to sometimes think about how fragile our life is here on Earth, that maybe we won't be here for all of time. Maybe there's a hope, but the way it looks, the universe just ends. And that's it. Welcome to our journey into the dark and mysterious world of black holes, the enigmatic powerhouses of the cosmos. Black holes, regions in space where gravity pulls so strongly that not even light can escape, have intrigued scientists and the public alike for decades. In this video, we'll explore what black holes are, how they form, and why they are crucial in understanding the universe. Join us as we dive deep into the science of black holes, uncovering their secrets and the groundbreaking methods used to study them. What is a black hole? A black hole forms when a massive star collapses under its own gravity at the end of its life cycle, squeezing all of its mass into an infinitely small point known as a singularity. Surrounding the singularity is the event horizon, often described as the point of no return. Once anything crosses this boundary, escaping the black hole's gravitational grip becomes impossible. Black holes come with fascinating properties. Firstly, their mass, which can be several times that of our sun, or as massive as millions of suns, when we talk about supermassive black holes at the centers of galaxies. They might also possess spin, rotating at immense speeds and influencing everything in their cosmic neighborhood by twisting space-time itself. Despite their dark nature, black holes are not just cosmic vacuum cleaners. They play a crucial role in the structure and evolution of galaxies, including our own Milky Way. Understanding these mysterious objects not only answers questions about the universe, but also about the fundamental laws of physics. The formation of black holes is a dramatic process, usually stemming from the remnants of a large star that has ended its life in a spectacular supernova explosion. Let's delve into how these mysterious objects come into existence. When a star significantly larger than our sun exhausts its nuclear fuel, it undergoes a dramatic transformation. Without the outward pressure generated by nuclear fusion to counteract gravity, the star collapses under its own immense gravitational pull. This collapse triggers a supernova, an explosion that outshines entire galaxies and ejects matter into space. For the most massive stars, what remains after this explosion is a core so dense that no known physical forces can stop its collapse, leading to the formation of a black hole. The core effectively collapses to a point of infinite density, a singularity where the laws of physics as we know them no longer seem to apply. But supernova remnants are not the only way black holes can form. In the vast expanse of the universe, black holes can also result from the direct collapse of massive gas clouds under certain conditions, skipping the star phase entirely. This process is thought to contribute to the formation of the supermassive black holes found at the centers of most galaxies, including our own Milky Way. Additionally, when black holes merge, a phenomenon observed through the detection of gravitational waves, they can form larger black holes, further adding to the diversity of these objects in the cosmos. In essence, black holes are born from the death of stars and other high-mass entities, playing a critical role in the cosmic cycle of matter and energy transformation. The detection of black holes. Detecting black holes is a complex task due to their invisible nature. Since no light can escape from them, astronomers must rely on indirect methods to prove their existence and study their properties. One primary method of detecting black holes is through their interaction with nearby matter. In binary systems, where a black hole is paired with a normal star, the black hole can pull in material from its companion. This material forms an accretion disk around the black hole, heating up due to intense gravitational forces and emitting high-energy X-rays before disappearing into the black hole. These X-rays, which can be detected by space-based telescopes, are a telltale sign of the presence of a black hole. Another method involves observing the orbits of stars around an invisible object. In the heart of our Milky Way galaxy, for example, astronomers have charted the orbits of stars around a region called Sagittarius A. The movement of these stars indicates they are orbiting a massive, invisible object, confirmed to be a supermassive black hole. Gravitational lensing is also a powerful tool for detecting black holes. This phenomenon occurs when a black hole bends the light from a background object, such as a galaxy or star, due to its extreme gravitational field. This bending causes the light to distort and magnify, appearing as rings or arcs from our viewpoint on Earth. The most recent and groundbreaking method is the detection of gravitational waves, ripples in space-time caused by some of the most violent and energetic processes in the universe. When two black holes spiral around each other and eventually merge, they emit these waves, which can be detected by facilities like LIGO and Virgo. These observations provide direct evidence of black holes and allow scientists to estimate their masses and other properties. Through these methods, astronomers continue to enhance our understanding of black holes, shedding light on some of the most mysterious objects in the cosmos. Black holes and relativity. Black holes are not only fascinating celestial phenomena, but also crucial elements in the study of Einstein's theory of general relativity. This theory, which revolutionized our understanding of how gravity works, predicts that massive objects can warp the fabric of space-time, and black holes are extreme examples of this effect. At the core of general relativity is the concept that gravity is not a conventional force, but a curvature of space-time caused by mass and energy. Black holes, with their immense mass concentrated into an infinitely small point, create profound distortions in space-time. This is why near a black hole, time seems to slow down and the paths of light and matter are bent, a phenomenon known as gravitational lensing. The Schwarzschild radius, or the event horizon of a black hole, is a direct consequence of relativity. It defines the boundary around the singularity, where the escape velocity equals the speed of light. According to relativity, nothing inside this radius can escape the black hole's gravitational pull, making the event horizon a perfect one-way exit from our observable universe. Black holes also challenge our understanding of space-time through their singularities, points where the curvatures of space-time become infinite. The laws of physics as we know them break down at these singularities, posing significant theoretical challenges and pushing scientists to think about quantum mechanics and gravity in new ways. Observations of black holes thus provide critical tests for the theory of general relativity. Events like the recent imaging of a black hole's shadow by the Event Horizon Telescope and detections of gravitational waves from black hole mergers offer unprecedented insights. These observations not only support the predictions of relativity, but also open new avenues for understanding the fundamental laws that govern our universe. Through their extreme nature, black holes serve as natural laboratories for testing ideas about gravity, space-time, and the limits of our physical laws, making them indispensable to the field of theoretical physics. Famous black holes and discoveries. Black holes might seem like uniform entities, but they are as varied as the cosmic phenomena that surround them. Some of the most notable black holes have unique stories that have significantly contributed to our understanding of the universe. Cygnus X1. One of the first black holes ever identified, Cygnus X1, became a key subject in the study of these cosmic objects. Discovered in the 1960s as a strong X-ray source, it was later confirmed to be a black hole through its interaction with a companion star. Observations of matter being pulled from the star into Cygnus X1's accretion disk helped astronomers validate the existence of black holes and provided a laboratory for studying extreme gravitational effects. Sagittarius A. At the center of our Milky Way galaxy lies Sagittarius A, a supermassive black hole with about 4 million times the mass of the Sun. Its presence was deduced from the orbits of stars at the galactic center, with their speeds and paths suggesting an extremely massive, invisible object. Sagittarius A offers a closer look at the dynamics of black holes at the centers of galaxies and their interactions with nearby stars and gas. M87. The black hole at the center of the M87 galaxy made headlines in 2019 when the Event Horizon Telescope captured the first ever image of a black hole's event horizon, or its shadow. This remarkable achievement not only provided visual evidence of black holes, but also confirmed general relativity's predictions at the edges of one of the most extreme environments in the cosmos. Gravitational wave discoveries. The LIGO and Virgo observatories have detected gravitational waves from several black hole mergers since 2015. These detections are crucial as they provide a new way of observing black holes and testing the limits of our physical theories. Each merger helps astronomers learn more about black hole masses, spins, and the history of galaxies. These iconic black holes and their studies have opened new windows into the high-energy universe, providing crucial insights into gravity, space-time, and the ultimate fate of massive stars. Unanswered questions and future research. Despite significant advancements in our understanding of black holes, they continue to be sources of profound mysteries and the subject of intense scientific inquiry. Here are some of the unanswered questions and the future research paths that scientists are pursuing to unravel these enigmas. Inside the event horizon, what happens inside a black hole remains one of the biggest questions in physics. Theories suggest that within the event horizon lies the singularity, a point where space and time cease to exist as we know them and where the laws of physics break down. However, the true nature of singularities and what happens to matter as it approaches this point is still speculative. Understanding this could lead to breakthroughs in our comprehension of gravity and quantum mechanics. Information paradox. The black hole information paradox poses a significant challenge to theoretical physics. It arises from the contradiction between quantum mechanics, which suggests information is never lost, and general relativity, which implies that information can disappear in a black hole. Resolving this paradox is crucial for a unified theory of quantum gravity, and research in this area is vigorous, with concepts like Hawking radiation and firewall hypotheses being explored. Formation and growth of supermassive black holes. The origins and rapid growth of supermassive black holes, especially shortly after the Big Bang, remain unclear. These black holes are millions to billions of times the mass of the Sun and are found at the centers of most large galaxies. Understanding how they formed and grew so massive in a relatively short period of cosmic history is critical for piecing together the evolutionary puzzle of the universe. Future missions and observations. Upcoming missions and observatories promise to shed more light on black holes. The Event Horizon Telescope continues to refine its observations to produce more images of black holes. Space missions like the James Webb Space Telescope and the planned Laser Interferometer Space Antenna, LISA, will explore the early universe and detect gravitational waves from black hole mergers across vast distances, offering new insights into their properties and behavior. Through these and other research initiatives, scientists continue to explore the enigmatic nature of black holes, pushing the boundaries of our knowledge and technology to solve the cosmos's most compelling mysteries. Thank you for joining us on this fascinating journey through the mysterious and powerful realms of black holes. We hope this exploration has sparked your curiosity and expanded your understanding of these cosmic giants. If you enjoyed this video and would like to dive deeper into the wonders of the universe, don't forget to hit the likes button and subscribe to our channel for more engaging science content. Your support helps us bring more exciting topics to light. Have any thoughts or questions about black holes? Or is there another cosmic phenomenon you're eager to learn about? Let us know in the comments below. We love hearing from you and are always looking to tailor our content to what you're most curious about. Remember, the universe is vast and full of wonders waiting to be discovered. Stay curious, keep exploring, and until next time, keep looking up. NASA is one of the most prestigious and respected space agencies in the world, but it also has its fair share of secrets and mysteries. I wonder what NASA is trying to hide from us. The revelations below will surprise you. The enigma of the dark side of the moon. For decades, the moon has been a focal point of human curiosity and scientific exploration. As Earth's closest celestial body, it has been the subject of numerous missions, including the historic Apollo landings that captivated the world. Yet despite the significant efforts to explore and understand the moon, there remains one side that continues to fuel speculation and mystery. The far side, often referred to as the dark side of the moon. Unlike the side we are familiar with, the dark side of the moon is never visible from Earth. This phenomenon is due to the moon's synchronous rotation, meaning it rotates on its axis at the same rate that it orbits Earth, keeping one hemisphere perpetually hidden from our view. While unmanned spacecraft have captured images of this elusive region, the lack of direct human exploration has led to countless theories about what might lie beyond our sight. Some speculate that the dark side could harbor secrets far beyond our understanding. Could there be alien bases hidden away from the prying eyes of Earth? Or perhaps remnants of an ancient unknown civilization? Others entertain the idea that NASA itself may be concealing knowledge of secret facilities, located on the far side, operating outside public scrutiny. Why, after all, has there never been a manned mission to explore this uncharted territory? While NASA has conducted thorough scientific studies of the moon, these questions have yet to be fully addressed. Could the truth about the far side of the moon be more mundane? Or is there something far more fascinating that has been intentionally kept from us? Until a manned mission finally sets foot on the dark side, the mystery will persist, leaving the door open for even more speculation and wonder. The face on Mars? Coincidence or ancient civilization? Mars has always captured the imagination of humanity, often seen as the most likely candidate in our solar system to harbor life beyond Earth. Over the years, numerous missions have been sent to study the red planet, but one discovery from the 1970s has continued to provoke debate and inspire intrigue: the infamous face on Mars. In 1976, NASA's Viking 1 orbiter captured a series of photographs of the Cydonia region, revealing what appeared to be a massive structure with an uncanny resemblance to a human face. The image, with its distinct eyes, nose, and mouth, quickly became a sensation. Was this a remnant of an ancient civilization that once flourished on Mars? Or was it an optical illusion, a trick of light and shadow? For some, this face was undeniable proof of intelligent life on Mars, a message from a long-lost culture etched into the planet's surface, possibly to be discovered by future explorers. The excitement around the face on Mars wasn't confined to mere curiosity. It ignited discussions within scientific communities, conspiracy theorists, and the general public alike. Some saw this as the smoking gun, suggesting that Mars might have once been home to a thriving civilization capable of constructing massive monuments. Proponents of this theory drew parallels between the face and similar earthly formations, such as the Great Sphinx of Giza, which only fueled the argument that Mars, too, could have had its own builders. Despite the wave of enthusiasm, NASA responded cautiously, attributing the face-like formation to a simple, natural phenomenon. Subsequent missions, such as Mars Global Surveyor in 2001, captured higher-resolution images of the Cydonia region, revealing that the so-called face was, in fact, an ordinary mesa, a rocky outcrop shaped by natural processes over millions of years. Yet, for many, NASA's explanation did little to quell the mystery. Critics argue that NASA has been too quick to dismiss the face as a natural formation, and that the agency may have a vested interest in downplaying any evidence of extraterrestrial life. If the face truly was the result of an intelligent design, it raises profound questions. Who created it? What happened to them? And why did they leave this colossal image behind? While mainstream science leans towards natural geological explanations, the fascination with the face persists. It serves as a symbol of the larger question. Could Mars have once harbored life, intelligent or otherwise? And if so, how much of its history remains hidden beneath its rusty surface? UFO sightings, NASA's involvement in extraterrestrial encounters. Unidentified flying objects, UFOs, have fascinated and mystified people for decades. With each new sighting, the possibility of extraterrestrial life sparks a wave of speculation and intrigue. As one of the world's leading space agencies, NASA has found itself at the center of many of these discussions, both on Earth and in space. The agency's involvement in various UFO sightings and unexplained phenomena has left many wondering whether NASA knows more than it's willing to admit. Numerous incidents involving NASA spacecraft have been documented over the years, with some of them even captured on video and shared widely with the public. One such incident occurred during the STS-48 mission in 1991. Footage from this mission shows a small object in Earth's orbit making sudden, sharp movements, seemingly dodging what appears to be a missile-like object. To this day, the footage remains one of the most talked about UFO sightings involving NASA. While the agency offered explanations such as debris or ice crystals, the erratic movement of the object left many unconvinced, fueling theories that NASA may have encountered something beyond earthly technology. Another famous event occurred during the STS-75 mission in 1996, where a tethered satellite experiment resulted in a swarm of glowing objects surrounding the spacecraft. NASA described the phenomenon as debris illuminated by sunlight, but conspiracy theorists quickly latched onto the footage, claiming the objects were UFOs observing the mission. The unusual behavior of the objects, hovering, drifting, and seemingly interacting with the tether, led many to believe that these were not mere space particles, but evidence of advanced extraterrestrial craft. One of the more modern incidents took place during the STS-114 mission in 2005, when astronauts aboard the Space Shuttle Discovery reported seeing a strange object flying near the shuttle. NASA responded by saying that the object was most likely a piece of ice or insulation that had broken off, a common occurrence during shuttle missions. However, the sighting ignited a wave of speculation, with many questioning whether NASA was downplaying the significance of the event. The incident revived old suspicions that NASA may be involved in a cover-up concerning extraterrestrial encounters. While NASA consistently provides scientific explanations for these incidents, debris, ice crystals, or optical illusions, skepticism remains high among UFO enthusiasts. Some believe that NASA's role as a government agency compels it to suppress any information that might prove the existence of alien life. They argue that the agency's missions to the far reaches of space have likely uncovered evidence of extraterrestrial intelligence, but that such discoveries are kept hidden from the public to avoid panic or global unrest. Others point to the increasing number of declassified government documents related to UFO sightings as potential proof that NASA and other agencies have long been aware of extraterrestrial activity. Recent revelations by the U.S. government regarding unidentified aerial phenomena have only added to the intrigue. Could NASA's missions have revealed more than just distant planets and galaxies? Could there be an extraterrestrial presence that the agency is keeping from the world? Planet X, the elusive mystery of the solar system. For decades, the concept of a hidden planet lurking at the edge of our solar system has captured the imaginations of scientists and conspiracy theorists alike. Known as Planet X, or Nibiru, this hypothetical planet is said to exist beyond the orbit of Neptune, with a gravitational pull so strong that it could periodically swing close to Earth, causing catastrophic events. And whether NASA knows more than it lets on. The story of Planet X gained prominence in the 1970s when author Zecharia Sitchin claimed to have translated ancient Sumerian texts that described a mysterious planet called Nibiru. According to Sitchin, Nibiru was home to an advanced alien race known as the Anunnaki, who visited Earth in the distant past. These extraterrestrials were believed to have played a significant role in the creation of human civilization, shaping the course of history as we know it. The most startling part of this theory, however, is that Sitchin also predicted Nibiru's eventual return to Earth's vicinity, which he claimed would result in devastating global events. In the early 21st century, renewed interest in Planet X emerged when astronomers observed strange gravitational anomalies in the outer solar system. These anomalies suggested that an undiscovered planet far beyond Neptune could be influencing the orbits of distant objects. Some astronomers began to seriously entertain the possibility of a large distant planet, although they didn't link it to Sitchin's theories of Nibiru and the Anunnaki. NASA, for its part, has consistently denied the existence of Planet X as described by conspiracy theories. The agency has pointed out that no credible evidence supports the notion of a planet periodically entering the inner solar system to wreak havoc on Earth. Additionally, predictions that Nibiru would collide with Earth or cause major disasters in 2012 were proven false, as the year came and went without incident. However, NASA's acknowledgement of the search for a Planet 9, a massive distant object that could explain the unusual orbits in the outer solar system, has kept the idea of a hidden world alive in some circles. For many conspiracy theorists, NASA's denial is simply another cover-up. They argue that the agency has long known about Planet X and its potential impact on Earth, but chooses to keep this information hidden to avoid causing public panic. Some even suggest that government elites have secret plans to escape to underground bunkers or off-world colonies when Nibiru inevitably returns to cause chaos on Earth. The Da Vinci Mission, unveiling the secrets of Venus. Among NASA's latest and most ambitious endeavors, the Da Vinci Mission, deep atmosphere Venus investigation of noble gases, chemistry, and imaging, stands out as a bold attempt to explore Venus, often referred to as Earth's sister planet. Despite Venus being closer to Earth than Mars, it remains one of the least understood planets in our solar system, mainly due to its harsh environment. With surface temperatures hot enough to melt lead, a crushing atmospheric pressure, and clouds of sulfuric acid, Venus presents an extreme challenge to space exploration. However, there are growing suspicions that Venus was not always the hellish world we see today. Some scientists believe that billions of years ago, Venus might have had Earth-like conditions, complete with liquid water oceans, and possibly even life. This raises the tantalizing question: what transformed Venus from a potentially habitable planet into the scorching inferno it is today? The Da Vinci mission, slated for launch in 2029, aims to answer some of these mysteries by sending a probe to dive into Venus's thick atmosphere. The mission will measure the chemical composition of the atmosphere, study its temperature and pressure at different altitudes, and provide unprecedented high-resolution images of the Venusian surface. With its advanced technology, Da Vinci could uncover vital clues about the planet's past, helping scientists understand why Earth and Venus, once so similar, evolved in such drastically different ways. Yet, as with many space missions, there are those who speculate that the Da Vinci mission might have objectives beyond what NASA has publicly disclosed. Could NASA be seeking evidence of ancient life forms or alien microbial colonies hidden in Venus's cloud layers? Some conspiracy theorists even suggest that Venus may still harbor life in its upper atmosphere, where conditions are much more temperate than on the planet's surface. NASA has consistently denied such claims, asserting that the mission's goals are purely scientific, aimed at studying Venus's atmospheric chemistry and history. Nevertheless, the idea that NASA could discover something far more profound during the Da Vinci mission has captured the imagination of the public. What if the probe uncovers signs of life or other extraordinary phenomena beneath the clouds of Venus? And if it does, what will NASA do with such groundbreaking information? The answers may not be known for years, but as the Da Vinci mission draws nearer, the anticipation grows. While many of these mysteries may eventually be solved through scientific inquiry, others will undoubtedly continue to provoke wonder and debate for generations to come. Whether NASA is hiding extraterrestrial knowledge or simply pushing the boundaries of space exploration, one thing is certain: our universe is vast, and we have only scratched the surface of what lies beyond. As we look toward the future, we can only imagine what other incredible discoveries await, and whether they will bring us closer to the answers we seek or raise even more questions. Is it possible for science fiction to become reality? I believe the reason Hollywood is so interested with the prospect of first contact with aliens is simple. It would be the biggest scientific discovery in human history. The problem is that our cosmos erects enormous hurdles to encountering extraterrestrials. It's almost as if the cosmos is trying to keep us from establishing first contact on purpose. We're looking for answers in the universe. Will we ever discover intelligent extraterrestrial life? Or are we alone? Arecibo Observatory. It blasted a strong radio message deep into space 45 years ago, launching our efforts to make first contact. The Arecibo transmission was the first communication or effort to connect with a hypothetical civilization outside our galaxy. That communication is currently en route to the M13 galaxy cluster, which is about 25,000 light-years distant. It carries data about our planet, our location, and even the composition of our DNA. The goal of this communication was, of course, to say hello, and also to raise the question, are we alone in the universe? But how likely is it that an intelligent alien culture is waiting for our message? Do you believe there is intelligent life in the universe? The answer is a loud yes. We know that life originated on Earth almost as soon as our planet formed. So why wouldn't it have occurred someplace else? How many extraterrestrial civilizations may we possibly contact if life has developed on other worlds? Frank Drake, an astronomer, devised an equation to assist in answering this critical topic. The Drake equation is a really remarkable effort to apply mathematical logic to the likelihood or potential of life beyond Earth. They also projected that there were about 10,000 intelligent civilizations in our galaxy. Since the Drake equation was initially developed, our knowledge of the galaxy has changed dramatically. Exoplanets are worlds found beyond our solar system. Exoplanets are being found all over the place. There are about 4,000 of them now known, and techniques are finding more every day. Scientists think what we've discovered is only the top of the iceberg. So if the universe is so excellent at creating planets, maybe it can create the conditions for life to exist across the universe. We didn't know exoplanets existed when the Drake equation was developed decades ago. And today scientists believe that there are more planets than stars in the cosmos. Even though life is very uncommon, there are many opportunities for it to emerge throughout the cosmos. As a result, it is quite possible that there is reasonably plentiful life in the cosmos. including an uncountable number of sophisticated extraterrestrial civilizations. This isn't science fiction, it's just basic probability. Most likely, there are many different alien cultures out there. So, don't you think it's a little strange that we haven't met yet? I think there are good reasons to think there are civilizations out there. Why haven't we found any other societies? One answer could be the sheer vastness of the cosmos. We live in the suburbs of the Milky Way, 75,000 light-years from the very edge. Radio signals travel at the speed of light. With this speed limit, a signal sent to the other side of the galaxy would take 75,000 years to get there. The thing to keep in mind is that the galaxy is very big. Even if there are 10,000 civilizations in the galaxy, it's possible that the distances between the stars are so great that we'll never be able to talk to each other. So, imagine we sent a message into space 45 years ago, hoping to reach any potential aliens out there. Well, guess what? That message is still super far away from its destination because it's cruising at the speed of light. The place we're trying to reach is a whopping 25,000 light-years away. The vast size of the universe is a huge roadblock to making first contact. And that's a bit of a problem when it comes to reaching out to potential extraterrestrial buddies. The laws of physics are like a roadblock preventing radio signals from zooming across such vast distances. Turns out you can't break the speed limit of light. So even though there might be cool civilizations and life forms out there in our galaxy, they're just so darn far away. I hate to be the one to say it, but the universe is just too darn large. But fear not, we're not giving up. In fact, we're using the best tech on Earth to speed up the search. The Breakthrough Listen project is our superhero in this quest. Imagine high-tech facilities worldwide, radio telescopes, optical telescopes, all teaming up to scan the sky. They're focusing on the 1 million stars and 100 galaxies closest to us, making it the most epic search for alien chatter ever. So, if there's an alien aircraft around any of the 1,000 nearest stars, the Breakthrough Listen project is on it like a detective on a case. They've got the tools to catch any signals and make sure we don't miss out on an intergalactic conversation. Cool, right? Breakthrough Listen is like a cosmic detective trying to catch any signals from outer space. Right now, they're eavesdropping on the closest 1,700 stars to us, hoping to hear something exciting. But guess what? It's been pretty quiet so far. It's kind of like waiting for a phone call that never comes. It's frustrating because we haven't found any proof of alien civilizations yet. But here's the catch. Just because we haven't heard anything doesn't mean they're not out there. Breakthrough Listen is just getting started on its mission, and there's a whole lot more space in the universe to explore. Imagine it like searching for a needle in a cosmic haystack. It takes a ton of patience. Now, let's do some space math. If you use Drake's equation and figure there could be 10,000 intelligent civilizations, consider this. There are around 250 billion stars in our galaxy. That's like looking for one specific house in a city of 25 million houses. It's a massive task, a bit like making a bazillion cold calls. The universe is so vast that we might have to wait a really, really long time before picking up any alien signals. And even if we do hear something, it might be too late. Imagine getting a message from someone, but they sent it ages ago, and by the time it reaches us, they could be history. So, are we just fashionably late to the cosmic party? Could some aliens have come and gone already? Earth may have been around for a whopping 4.5 billion years, allowing us to evolve into a smart species. But in the grand scheme of the universe, we're just cosmic toddlers. Earth is super old, like over 4.5 billion years old. And guess what? It took all this time for us humans to become the cool, tech-savvy civilization we are today. But here's the kicker. There are star systems out there that have been around even longer than us. The universe itself is a whopping 13.8 billion years old. Wrap your head around that. We often think we're top-notch because we can build rockets and play with radio waves. However, if we met a civilization that's been around way longer than us, they'd probably be light years ahead in technology. There's this cool way of measuring how advanced a civilization might be. It's called the Kardashev scale. It sorts civilizations into 3 types based on how much energy they can grab from their surroundings. Type 1 can only use the energy of its home planet. Type 2 could potentially harness the energy of its entire solar system. And Type 3? Well, they're the big shots who could harness the power of a whole galaxy. And here's the buzzkill. We're not even a Type 1 civilization. We're somewhere between 0 and 1 on the scale. We can't fully tap into all of Earth's resources, so we're sitting at a modest 0.7. But hey, we're trying our best to catch up with the cosmic neighbors. Imagine an advanced civilization hitting Kardashev level 2 or 3. These guys could create mind-blowing structures that tap into the power of a star. Massive solar panels enveloping the entire star, a concept first dreamed up by Freeman Dyson. These cool structures are called Dyson spheres. Now, if other star systems or even entire galaxies have these epic Dyson spheres, could we catch a glimpse and finally make contact with these advanced beings? Here's the deal with Dyson spheres. They block almost all the light from a star, except for the sneaky infrared light. Why? Because those panels are soaking up sunlight and getting warm. And when things warm up, they give off thermal infrared light. So, we can play cosmic detectives by scanning the skies for this telltale thermal infrared signature to spot Dyson spheres. Back in 2015, NASA's Wide Field Infrared Survey Explorer scanned 100,000 nearby galaxies on the hunt for these advanced civilizations. They detected nothing. But here's the cosmic conundrum. The universe is crazy old, right? So, shouldn't other civilizations have had plenty of time to evolve? Well, maybe we just haven't noticed them yet. Imagine this. They're out there trying to send us a message, but it's like they're knocking on our door before our house is even built. Earth has been around for less than a third of the universe's 13.8 billion years. And humans? We've been strutting our stuff for just 300,000 years. That's a tiny window in the grand scheme of the cosmos to make that first contact. It's like trying to join a party, but you're fashionably late, and the party's been going on for ages. The hypothesis of natural filters in the universe posits that advanced extraterrestrial civilizations may have existed for a long time, but were eradicated by these natural filters. If extraterrestrial life exists, the question arises whether their forms and environments would be similar to those on Earth. This idea draws from the concept that certain conditions, whether astrophysical, biological, or societal, act as filters that limit the emergence and longevity of advanced civilizations. Possible filters include cataclysmic events, astrophysical phenomena, or self-destructive behaviors inherent to intelligent societies. If extraterrestrial life exists, its forms and environments might not necessarily resemble those on Earth. Life could evolve in diverse ways depending on the unique conditions of each planet. The variety of planetary environments and the adaptability of life make it plausible that extraterrestrial beings might have different biochemistries and physical characteristics. Rocky planets like Earth are considered ideal for supporting life due to their specific conditions. However, these planets are delicate and susceptible to various threats. And this fragility means the universe could filter out intelligent life quickly. One significant threat comes from violent stellar events, such as gamma-ray bursts, which are powerful enough to sterilize planets over vast cosmic distances, potentially affecting entire galaxies. Imagine this. A huge star explodes in our galaxy, the Milky Way, sending a deadly burst of energy hurtling toward our planet. This is a gamma-ray burst, which is the biggest blast since the Big Bang. There are no signs that something bad is about to happen, and then it strikes. The radiation that is pumped up heats up the high atmosphere. Our layer of ozone heats up. Across the atmosphere, human beings burns to death from radiation 100 times the fatal dose. When the ozone layer gets thinner, temperatures rise all over the world. This makes storms, tsunamis, and hurricanes happen. Most life on the surfaces of land and water incinerates. This may sound like science fiction, but if a gamma ray burst from 100 light years away hit Earth, it could happen. Even if intelligent species manage to survive these natural occurrences, there is another risk: self-destruction. Drawing from our own experiences on Earth, the development of technology has given us the capability to alter our climate and create weapons of mass destruction. This self-destructive potential poses a serious risk for advanced civilizations. It is plausible that technologically advanced societies may have a brief existence, as evidenced by our own history. The short lifespan of advanced civilizations could be a reason why there are so few observable ones at this point in time. The possibility arises that many civilizations may have emerged, but their existence was short-lived due to self-inflicted challenges. This scarcity of long-lasting civilizations could explain the limited opportunities for communication with extraterrestrial beings. Discovering remnants of an extinct alien civilization could serve as a profound warning for humanity. If we were to find evidence of a civilization that destroyed itself through pollution or conflict, it would be akin to looking at our own potential future. This sobering realization could provide valuable lessons for us on Earth, emphasizing the importance of avoiding similar pitfalls. In our quest for understanding the cosmos, we can only hope that some advanced alien species have managed to navigate the challenges posed by the universe's potentially lethal filters, offering a glimpse of long-term survival and prosperity. If we are lucky, there may be an extraterrestrial civilization that will come to visit us in the future. Imagine making contact with aliens. Sounds cool, right? But hold on. Are we assuming too much? We tend to think that aliens are just like us, but here's the twist. They're not. We might be imagining them based on what we know about life on Earth, assuming they live on planets like ours. But guess what? Most of the universe might not follow our life and planet rulebook. So, could extraterrestrials even survive first contact with us and our planet? July 2019, a satellite on a test mission spotted a new alien world named GJ357d, about 31 light-years away. This super-Earth is over 6 times heavier than our cozy home planet. Now, what's a super-Earth? A terrestrial planet, but bulked up with more mass. More mass means more gravity, creating a whole different vibe compared to our Earth. Imagine aliens living on a super-Earth. The gravity there could be super strong. They might not be tall, but I bet they'd be super strong. Super-Earths are just one of the many wild things the universe cooks up. Who knows what other surprises are out there? The possibilities are as vast as the cosmos itself. The universe is a vast playground with planets of all shapes and sizes orbiting stars of various types and sizes. forming countless configurations. This diversity opens up a world of possibilities for life that is much richer and more varied than we ever imagined. However, we need to break free from the idea that extraterrestrial life will resemble us. If we're expecting beings with two legs like ours, we might as well abandon that notion. The truth is, life out there could be radically different. Consider this scenario. An intelligent alien species in our cosmic neighborhood wants to say hi to us. But here's the catch. If that alien evolved on a super Earth or circled a red star instead of a yellow one, its biology could be so alien that it might never set foot or tentacle on our planet. Looking at life on Earth, it seems like it's tailor-made for our specific temperature, elements, and environment. Now, imagine an exoplanet with conditions conducive to life. It could still host life forms vastly different from what we're accustomed to. What if an alien world has a bit more potassium, is warmer than our average Earth, or has a thicker atmosphere? Each of these subtle differences could create an entirely distinct ecosystem. So, the big question is, can an alien organism truly adapt to our ecosystem when it lands on Earth? It's a cosmic mystery waiting to unfold. The universe is full of strange and surreal paradoxes that challenge our understanding of the world around us. From the mysteries of quantum mechanics to the mind-bending properties of black holes, the universe presents us with a plethora of phenomena that defy our intuition and challenge our perceptions of reality. This video lets you see some of the many things we do not understand in the universe and the strange and surreal paradoxes in what we think we understand. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Everything we know represents just 5% of the universe. What is the rest? Normal matter, protons, neutrons, and electrons make up just 5% of the universe. Staggeringly, the other 95% is something which we cannot fathom, see, or understand. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are two mysterious concepts in astrophysics that scientists use to explain some of the strange observations that we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light. However, scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself, rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, The universe as we know it has three spatial dimensions: length, width, and height, and one dimension of time, making a total of 4 dimensions in space-time. This is known as the four-dimensional space-time. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions. But these extra dimensions are thought to be curled up or compactified to be too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the four-dimensional space-time can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical basis of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist? And if they do, is there a way for us to measure their presence? Or will we forever be trapped in our 4-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real? Or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction or flow of time, and it seems we can't travel backwards in time. Why is this? Are we trapped in the arrow of time, perpetually moving forwards? Is the passing of time intertwined with the way our universe works? According to the theory of Big Bang, time itself began together with the rest of the universe about 13.8 billion years ago. Does that mean that it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past, through the present, and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and year. It is also an essential component of the space-time continuum, which is the 4-dimensional fabric of the universe consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as being unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness, in a closed system tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature? In certain situations, 2 particles can seemingly be in instant connection with each other, even if they are located at opposite ends of the universe. The phenomenon is known as quantum entanglement, where 2 particles can become correlated in such a way that the state of one particle is instantly correlated with the state of the other. regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because, while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe, with more stars and planets in them than all the grains of sand on planet Earth. So, where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare? Or does it have a limited lifetime, destroying itself before it has had the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather we are embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us, but why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it has passed the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics, as we know them, break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a hypothetical tunnel-like connection between 2 points in space-time. However, there is no direct evidence to suggest that wormholes exist either. The universe is full of strange and surreal paradoxes. Our quest for understanding these is only just beginning. As we continue to push the boundaries of our knowledge and explore the furthest reaches of space and time, we can be sure that the universe will continue to surprise and challenge us in new and unexpected ways, spurring us onto new and unexpected ways, spurring us onto new heights of discovery and understanding.
What if the greatest civilization in the universe is watching us right now, but we simply can't see them? We've spent decades scanning the sky, listening for radio signals, sending probes to distant planets, yet we've found nothing. No signs of intelligent life, no alien broadcasts, no encounters. But does that mean we are alone? Or does it mean we've been searching the wrong way? In 1950, physicist Enrico Fermi famously asked, "Where is everybody?" Statistically, our universe should be teeming with intelligent life. There are over 200 billion stars in our galaxy alone, many with Earth-like planets. Even if only a tiny fraction developed intelligent civilizations, the cosmos should be bustling with extraterrestrial activity. And yet, nothing.
This contradiction is known as the Fermi paradox, a mystery that has puzzled scientists, astronomers, and philosophers for decades. If advanced extraterrestrial civilizations exist, why haven't we seen or heard from them? But what if the answer is unsettlingly simple? What if they are here, hiding in ways we don't understand? Every search for extraterrestrial life is shaped by one fundamental assumption: that life must resemble us, that it must be biological, carbon-based, living on a habitable planet, breathing oxygen and following the rules of evolution as we understand them. But what if life doesn't need carbon? In 2017, NASA's Cassini spacecraft discovered that Saturn's moon Titan has lakes of liquid methane and ethane, chemicals that could potentially support a different kind of life. Some scientists suggest that silicon-based life might exist under extreme conditions, forming an entirely new branch of evolution beyond our imagination. If alien life is fundamentally different from what we expect, we might be missing it completely. But what if they are far beyond biological constraints? In 1964, Soviet astrophysicist Nikolai Kardashev proposed a system for classifying civilizations based on their energy usage. Type 1 harnesses energy on a planetary scale. We are not even at this level yet. Type 2 uses the energy of an entire star, e.g. Dyson spheres. Type 3 controls the energy of an entire galaxy. If a civilization advanced beyond our current technological level by just a few thousand years, they might no longer be biological at all. Some scientists, including the SETI Institute's Seth Shostak, suggest that truly advanced civilizations would abandon their biological origins and transition into digital, artificial intelligence-based life forms. Imagine a species that has uploaded its consciousness into a vast planet-sized supercomputer, one capable of processing knowledge at speeds far beyond human comprehension. Would such beings even be interested in communicating with primitive biological organisms like us, or would they exist in ways we simply cannot perceive, like a cloud of self-replicating nanobots, or even as pure energy spread across space? This would explain why we haven't heard from them. We're expecting radio signals, spaceships, or messages, but maybe we are the equivalent of ants trying to understand the internet. Imagine you are lost in a dark forest at night. You know that others are out there, but you don't know if they are friendly or hostile. What do? You stay silent. This is the premise of the dark forest hypothesis, proposed by science fiction author Liu Cixin and based on game theory. It suggests that the universe is silent not because life is rare, but because intelligent civilizations deliberately hide from one another. Why? Because the first rule of survival is not to reveal your location. If an advanced civilization exists, it may have learned that exposing itself could lead to extermination by another, more aggressive species. Humanity has already broken this rule. We have been broadcasting our existence into space through radio signals for over a century. If there are predators out there, we may have already announced our presence. Could this be the reason why the universe appears so eerily quiet? Because the most intelligent species are the ones who have learned to remain unseen? We assume that intelligent life would want to talk to us, but what if their silence is intentional? What if the greatest civilizations in the universe have already discovered each other, and we are simply too young, too primitive, too naive to be invited? Or worse, what if we are making the fatal mistake of calling out into the dark, unaware of who or what might be listening? What's next? This is only the beginning. In the next segment, we will explore the possibility of hyperdimensional life forms, beings that exist beyond the limits of our three-dimensional reality. Could they be watching us from a higher plane of existence? And if so, can we ever perceive them? Do you believe aliens exist, but we're searching the wrong way? Comment below. What if the beings we're searching for aren't in another galaxy but right here, moving through our world unseen like ghosts passing through a two-dimensional painting? We tend to think of alien life in physical terms, beings made of flesh and blood, inhabiting distant planets, building spacecraft and using technology similar to ours. But what if extraterrestrial intelligence doesn't play by our rules? What if their existence transcends the very fabric of reality as we know it? Could it be that the most advanced civilizations have escaped the limitations of our three-dimensional universe and now exist in higher dimensions, just beyond the reach of human perception? This isn't just wild speculation. The idea that higher dimensional life forms could exist is deeply rooted in theoretical physics, string theory, and even quantum mechanics. And if they do exist, it could explain some of the most perplexing mysteries about the universe and why we haven't found extraterrestrials yet. Imagine a world of flatlanders, intelligent beings who live in a two-dimensional plane, like ink drawings on a sheet of paper. They can move left and right, forward and backward, but they have no concept of up or down. Now imagine a three-dimensional creature, like a human, reaching into their world. To the flatlanders, this entity would seem like a ghost, appearing and disappearing at will. If you placed your finger on their plane, they would only see a small circle, the cross-section of your finger. If you lifted your hand, they would see the circle vanish into nothingness. If you spoke, your voice would seem to come from nowhere. Now ask yourself, what if we are the flatlanders? What if higher dimensional beings exist right here all around us, but we simply lack the sensory perception to see them? Physicists have long theorized that our universe isn't just three-dimensional. String theory, one of the most promising models in modern physics, suggests that reality may contain up to 11 dimensions, far beyond what we can comprehend. If advanced beings have evolved to perceive and navigate these higher dimensions, they might be able to pass through our world unseen, just as we can move through a 2D space without being noticed. Manipulate reality in ways that seem supernatural, like appearing and disappearing or altering time itself. Observe us freely while remaining completely invisible to our senses. Could it be that some of the UFO sightings, paranormal experiences, or unexplained phenomena we've recorded throughout history are glimpses of beings moving through higher dimensions? This isn't just a thought experiment. There's real scientific evidence that suggests dimensions beyond our perception could exist. In 1935, Einstein famously called quantum entanglement spooky action at a distance. Why? Because when two quantum particles become entangled, they remain connected no matter how far apart they are. Change the state of one particle and the other instantly changes, even if they're light years away. How is this possible? Some physicists believe that quantum entanglement hints at a hidden layer of reality, possibly one that exists in a higher dimensional space where these connections are instantaneous. What if hyperdimensional beings don't need spaceships to travel between stars? What if they can simply manipulate these hidden dimensions, allowing them to be in two places at once, or even traverse the cosmos instantly? One of the strangest and most famous experiments in quantum mechanics is the double-slit experiment. When particles, like electrons, are fired through two slits, they create an interference pattern, as if they are waves, not particles. But if we observe them closely, they behave like solid particles again, as if reality changes based on observation. This suggests that reality at a quantum level isn't fixed, it's fluid, probabilistic, and possibly dependent on an observer. Now, let's take this one step further. What if higher dimensional beings are the true observers of our reality? Could they be the ones collapsing our wave functions, choosing what we perceive as real? This could explain why we have fleeting, unexplained phenomena, moments where reality seems to glitch, UFOs vanish, or strange experiences occur without physical traces. What if we are just a small part of a much grander reality? one where higher dimensional intelligence has far more control over the nature of existence than we do. If these hyperdimensional beings exist, can we prove it? Scientists are already conducting experiments that may lead to answers. At CERN, the world's most powerful particle accelerator, scientists are smashing protons together at near light speed. Their goal? To detect gravitational anomalies that might indicate the existence of extra dimensions. If we detect missing energy or unusual gravitational behavior, it might be our first real proof that other dimensions exist beyond our own. Some physicists believe that our entire universe may be a hologram, a three-dimensional projection of information stored on a two-dimensional surface. This would mean that what we perceive as reality is just a shadow of something much larger and more complex, something that might be governed by hyperdimensional laws we can't yet comprehend. If this is true, then higher dimensional beings could exist on the real level of reality, while we exist in a simplified projection, like characters in a simulation, unaware of the full scope of existence. If hyperdimensional beings exist, they wouldn't need spaceships or radio signals to explore the universe. They might be able to move freely between worlds, between timelines, or even between different realities. So here's the real question. Have they already found us, but we simply lack the ability to see them? Could it be that every ghost story, every UFO sighting, every unexplained phenomenon is not evidence of separate, unrelated mysteries, but fragments of the same greater reality we are only beginning to glimpse? And if we ever develop the technology to perceive these higher dimensions, what will we see staring back at us? In the next part, we'll explore a mind-blowing possibility. What if we are not just being observed, but actively manipulated? Could hyperdimensional beings be influencing human civilization without us even realizing it? Stay tuned. Do you believe in higher dimensions? What if aliens exist, but in a way we can't comprehend? Drop your thoughts in the comments. What if history is not what we think it is? What if, hidden beneath our myths, religions, and unexplained phenomena, there is an invisible hand, one that has been guiding human civilization for thousands of years? From ancient gods and prophetic visions to UFO encounters and shadowy secret societies, there have always been stories of unseen forces shaping the fate of humanity. Some dismiss them as folklore, others see them as religious revelations. But what if these stories are not just myths? What if they are fragments of a much bigger truth? A truth that suggests hyperdimensional beings may have been watching, guiding, and even manipulating human civilization since the dawn of time. This isn't just speculation. There is scientific, historical, and philosophical evidence that suggests we may not be the only intelligence influencing the course of history. If hyperdimensional beings exist, it is possible that they are not just silent observers, but active participants in our reality. But for what purpose, and what clues have they left behind? Throughout history, cultures across the world have reported contact with non-human entities, beings described as gods, spirits, or celestial visitors. These encounters share striking similarities, despite occurring in civilizations that had no contact with each other. Could these ancient stories be misinterpretations of interactions with hyperdimensional intelligence? In Sumerian mythology, the Anunnaki were gods who came from the heavens and bestowed knowledge upon early humans. Some theories suggest they could represent an advanced non-human intelligence. In Hinduism, the Vedas describe devas and asuras, powerful beings engaged in cosmic battles, capable of bending space and time. The Book of Enoch speaks of the Watchers, celestial beings who descended to Earth and imparted forbidden knowledge to humanity. Are these stories metaphors, or could they be historical records of actual contact with higher dimensional beings? Many researchers have pointed out the stunning similarities between historical religious visions and modern UFO encounters. The biblical prophet Ezekiel described a wheel within a wheel descending from the sky, glowing with fire and light. The Fatima apparitions in 1917 were witnessed by tens of thousands of people who saw mysterious lights and received messages from a being of light. Indigenous shamans, using substances like DMT, often report encounters with entities that appear as luminous, hyper-intelligent beings. Could all these experiences be glimpses into another dimension where these beings reside? If so, what do they want from us? The simulation hypothesis, proposed by philosopher Nick Bostrom, suggests that our reality may be a highly advanced digital simulation created by an unknown intelligence. If hyperdimensional beings exist, could they be the architects of this simulated world? Some physicists argue that there are strange anomalies in the fabric of reality that suggest our universe might not be what it seems. The observer effect. In quantum mechanics, particles don't have definite properties until they are observed. This is eerily similar to how information is processed in a simulation. The fine-tuning problem. The physical constants of the universe are so precise that even a tiny variation would make life impossible. Could this be evidence that our reality was designed? The Mandela effect, some people report collective false memories, suggesting that reality may be rewritten or altered in ways we don't fully understand. Could hyperdimensional beings be the ones running the simulation? If so, what is their end goal? If hyperdimensional intelligence exists, why haven't they revealed themselves openly? Some researchers suggest that they may be influencing us covertly, not by physical means, but by manipulating human consciousness itself. Throughout history, people who enter altered states of consciousness via meditation, psychedelic experiences, or near-death experiences often report encounters with non-human entities. The famous DMT experiments conducted by Dr. Rick Strassman revealed that subjects who took the psychedelic dimethyltryptamine frequently reported encountering beings that seemed to exist outside of space and time. Shamans and mystics from many cultures claim to receive knowledge and visions from higher realms. The concept of Akashic records in Hindu and theosophical traditions suggests a vast invisible database of knowledge that can be accessed in altered states. Are these hallucinations, or could they be real interactions with a higher intelligence that communicates in ways beyond our normal perception? What if human history has been carefully steered by these entities? Consider the rise and fall of great empires, coincidences or interventions, the sudden explosions of knowledge in history like the Renaissance or the scientific revolution, genuine progress or guided evolution. The development of artificial intelligence. Could this be part of an experiment to create new intelligent beings? If hyperdimensional beings are influencing us, what is their endgame? Are they benevolent guides helping us evolve? Or are they puppet masters, shaping us for reasons we can't comprehend? For thousands of years, human civilization has been haunted by visions, prophecies, and unexplained phenomena. We have always assumed these were spiritual or mythological in nature. But what if they were real? What if we are not the masters of our own history, but participants in a vast hyperdimensional game, one whose rules we are only beginning to understand? And the most unsettling question of all, if they are influencing us, will we ever know why? In the next part, we'll explore a terrifying possibility. What if these hyperdimensional beings are not just watching us, but actively preparing for something? Could they be waiting for the right moment to reveal themselves? We'll dive into theories of an upcoming contact event, secret government knowledge, and the possibility that we are approaching a turning point in history. Do you think hyperdimensional beings have influenced human civilization? Have we been guided or manipulated? Comment below. What if everything we've ever believed about extraterrestrials, UFOs, and paranormal encounters was leading to something? What if right now we are standing at the edge of a moment that has been planned for thousands of years? For centuries we have been haunted by sightings of unidentified flying objects, stories of beings that exist beyond our perception, and whispers of secret knowledge hidden by governments. Skeptics call it fantasy, but recent years have brought declassified military footage, whistleblower testimonies, and a growing scientific consensus that something is happening. But the real question is, why now? Could it be that hyperdimensional beings are not just watching us, but preparing for something monumental? Are we about to witness first contact, or has it already begun, hidden in plain sight? For decades, governments denied the existence of UFOs, now referred to as UAPs, unidentified aerial phenomena. But in the last few years, everything changed. In 2017, the New York Times published a shocking report revealing that the Pentagon had been secretly studying UFOs for years. Videos from US Navy fighter jets showed objects defying the known laws of physics, moving at hypersonic speeds with no visible propulsion and executing maneuvers that would be impossible for any human-made craft. These were not just random lights in the sky, they were controlled objects and they were interacting with military personnel. The Tic Tac UFO incident, US Navy pilots encountered an object that moved in ways no known aircraft could. The Go Fast and Gimbal videos, officially declassified footage showing objects outmaneuvering fighter jets with ease. Governments never admit to things like this unless they have no choice, so why are they coming forward now? In July 2023, former US intelligence officer David Grush testified before Congress, claiming that the US government has been recovering non-human technology for decades. He stated that the government has retrieved UFO crash debris and possibly even biological remains of non-human entities. Other military personnel confirmed that high-ranking officials are aware of UAPs, but keeping the truth from the public. If these claims are true, then the implications are staggering. We are not alone. Someone or something has been visiting us for a long time. The people in power might be hiding crucial information about humanity's place in the cosmos, but here's the real question. If hyperdimensional beings are involved, could this be part of a larger, carefully timed revelation? Many researchers believe that full disclosure of non-human intelligence isn't happening all at once, but instead it's being slowly revealed in a way that humanity can handle. Why? Because if these beings exist beyond our reality, then contact with them could be psychologically and culturally overwhelming. In 1960, Brookings Institution produced a report for NASA warning that contact with a superior extraterrestrial intelligence could destabilize human society, especially in religion, government, and technology. Some former military officials suggest that governments have already established some form of communication, but are afraid of public panic. In 2021, former Israeli space security chief Haim Ahed made headlines when he claimed that the US government had been in contact with an intergalactic federation but wasn't ready to reveal it yet. Could this be why UFOs and UAPs are being declassified in small doses, to condition the public for the truth? If hyperdimensional beings are real, then their existence changes everything from science to philosophy to our fundamental understanding of reality itself. If hyperdimensional civilizations exist, why haven't they openly revealed themselves? Perhaps they are waiting for us to reach a level of technological and spiritual development that allows us to understand them. One explanation for the Fermi paradox, why we don't see extraterrestrial civilizations, is the idea of the Great Filter. The idea that civilizations might reach a point where they either self-destruct or evolve into something new. Right now, humanity is at a critical juncture. We have nuclear weapons capable of wiping out our entire species. We are creating artificial intelligence that may surpass human intelligence within decades. We are beginning to understand quantum mechanics and the true nature of reality. Could it be that hyperdimensional beings are watching to see if we will evolve or if we will destroy ourselves? If hyperdimensional civilizations exist beyond space and time, then traditional communication methods like radio signals may be useless. Instead, what if the real form of contact is through consciousness itself? Dr. John Mack, a Harvard psychiatrist, studied hundreds of alien abduction cases and concluded that these experiences seemed to involve altered states of consciousness rather than physical abduction. The CIA's remote viewing program, Project Stargate, attempted to use psychic abilities to access hidden knowledge, suggesting that the human mind may have capabilities we don't fully understand. Some UFO researchers believe that meditation, psychedelics, and altered states of consciousness may be key to understanding these beings, that they exist in a layer of reality beyond normal perception. Could it be that contact isn't something that happens with us? If that's true, then maybe the greatest discovery of all is not out there in the stars, but inside our own minds. So here we are. Governments are slowly releasing classified information, scientists are exploring new models of reality that suggest other dimensions exist, human consciousness is expanding toward the possibility that we are not alone. The real question is, what happens next? Are we on the verge of a revelation that will change everything? Or has first contact already happened and we're just waiting for the rest of the world to catch up? And if hyperdimensional beings are watching, guiding, or even manipulating us, what will they do when we are finally ready to see the truth? In the final part, we will explore the wildest yet most plausible possibilities. What if contact has already happened at the highest levels of power? Could ancient technology hold secrets to unlocking hyperdimensional knowledge? And, most importantly, what should we do if they finally reveal themselves? Do you believe contact is coming, or has it already happened? Drop your thoughts below. Imagine waking up tomorrow to the news, first contact confirmed, scientists acknowledge the existence of non-human intelligence. Would the world celebrate? Would society collapse? Would religions, governments, and economies crumble under the weight of this revelation? Or would nothing change at all, because the truth had already been hidden in plain sight all along? If hyperdimensional beings are real, if they have been watching, guiding, and waiting, then what happens when they finally decide to step forward? The implications are beyond anything humanity has ever faced. Reality itself might be rewritten. This isn't just about aliens. This is about what happens when we finally confront a greater intelligence, one that may be far beyond our understanding. So let's ask the question no one dares to. What happens after disclosure? Human civilization is built on a fragile web of beliefs, traditions, and power structures. The moment we confirm non-human intelligence exists, everything changes. For centuries, religions have provided answers to humanity's deepest questions. Who are we? Why are we here? What happens after we die? But if an advanced civilization appears, one that has mastered time, space, and perhaps even consciousness itself, then where does that leave traditional religious beliefs? Do ancient religious texts describe hyperdimensional beings instead of gods? Would people abandon faith, or would they integrate these beings into religious frameworks? Would some resist, calling them deceivers or demons? The Vatican has already acknowledged that belief in extraterrestrial life is not incompatible with faith. In 2008, the chief astronomer of the Vatican Observatory, Father José Gabriel Funes, stated, "If aliens exist, they are also part of God's creation. But if these beings demonstrate abilities that defy our understanding of reality, if they can manipulate time, materialize at will, or even communicate telepathically, then humanity will be forced to confront an uncomfortable truth. Our understanding of the universe may be completely wrong." Governments thrive on control. They create narratives that maintain order. But what happens when an intelligence appears that is beyond governmental power? Would world leaders try to suppress information, fearing mass panic? Would they attempt to negotiate with these beings, seeking alliances or weapons? Would global conflicts erupt as nations scramble to gain an advantage in dealing with this intelligence? Some believe that governments have already been in contact, and that gradual disclosure is part of a long-term strategy to control the narrative before the truth becomes undeniable. In 2023, former US intelligence officer David Grush testified before Congress, claiming that the US has recovered non-human technology for decades. If that's true, then has our world already been shaped by hyperdimensional knowledge? Are we already living in a post-contact civilization? We just don't know it yet? If hyperdimensional beings exist, then our entire economic system becomes obsolete overnight. Why work if advanced civilizations have technology that can create infinite energy, cure all diseases, or manipulate matter at will? Would industries collapse if extraterrestrial technology renders them irrelevant? Would money, power, and resources still matter in a world where the rules of physics can be rewritten? Imagine a civilization that has transcended material needs, one where they do not require food, money, or even bodies. What could such beings possibly want from us? Would they be here as teachers, or something else? Some researchers propose a radical idea. First contact may not be something that happens suddenly. It may be something that has been happening gradually through human evolution itself. Ancient astronaut theories suggest that early humans may have been genetically altered or influenced by non-human intelligence. DNA research has found that human genetic material has unexplained anomalies. Could parts of our DNA have been modified by an advanced intelligence? Some abductees report experiences of hybridization programs, claiming that non-human entities are actively creating a new form of consciousness that blends human and hyperdimensional traits. What if humanity itself is the result of an ongoing process, a biological platform being prepared for something greater? Are we evolving toward a form that will allow us to perceive and interact with these beings on their level? When hyperdimensional beings reveal themselves, whether it happens suddenly or gradually, humanity will face a crossroads. If we choose to embrace the truth, we might enter a new era of knowledge, technology, and consciousness. Scientific breakthroughs could advance beyond anything we imagined. Spiritual awakenings could transform how we understand existence. A unified humanity might emerge, realizing we are part of a greater cosmic community. Could this be the next phase of evolution, one where we leave behind war, greed, and ignorance in favor of a higher state of being? But there is another possibility. History has shown that humanity often fears what it doesn't understand. Would governments see these beings as threats and try to wage war? Would people deny reality, refusing to believe in their existence? Would secret factions attempt to manipulate this knowledge for their own gain? There is one terrifying possibility. What if contact leads to global collapse, panic, and chaos? Would humanity fail the test of first contact? What if the event we fear, anticipate, or wait for has already occurred? What if these beings are already here, but they interact in ways we can't perceive? What if some of us already know the truth, but society isn't ready? What if hyperdimensional contact isn't an external event, but an internal awakening? If consciousness is the key to perceiving these beings, then first contact may not be a spaceship landing on the White House lawn. It may be a moment when human consciousness reaches a level where we can finally see what has been in front of us all along. So the real question is, are we ready? This is the end of our journey, or is it just the beginning? If hyperdimensional beings exist, then we are living in a universe far stranger than we ever imagined. Have they been guiding us all along? Are we evolving towards something greater? And when the moment of true contact comes, will we embrace it or reject it? Perhaps the answer isn't something we will find out there in space. Perhaps it's something we must unlock within ourselves, because the greatest revelation may not be that we are not alone. It may be that we were never meant to be. Do you believe humanity is ready for first contact? What do you think would happen if hyperdimensional beings revealed themselves? Drop your thoughts below. Thank you for joining this journey. Who knows what mysteries the future holds? Throughout history, humanity has stood at the precipice of profound discoveries, each challenging the foundations of our understanding and reshaping the course of civilization. The Earth was once believed to be the center of the cosmos until revolutionary minds dared to see beyond conventional wisdom. Electricity, gravity, and even the very fabric of time and space, once mystical and unknowable, are now harnessed as essential components of our daily existence. Yet, as much as we have uncovered, the universe remains an enigma, concealing secrets that defy our current grasp of reality. What if the greatest breakthroughs are not about discovering something entirely new, but about reinterpreting what we already know? The forces that govern our universe, from the smallest quantum fluctuations to the vast curvature of space-time, may not be as disparate as they seem. Perhaps the key to unlocking the future of humanity lies not in fragmented disciplines, but in a unified vision, one that sees the cosmos, energy, and even consciousness as deeply interconnected elements of a single boundless system. For too long, scientific progress has been constrained by rigid paradigms, dismissing ideas that do not fit within established frameworks. But true evolution, whether in thought, science, or society, has always emerged from those willing to challenge the status quo. Now we stand once again on the brink of transformation, where a new perspective could illuminate a future far beyond our imagination. What if we have only scratched the surface of our potential? What if the very structure of space holds an untapped reservoir of energy? What if gravity itself is not an immutable force, but a phenomenon that can be understood, influenced, and even harnessed? These questions are not mere philosophical musings. They hold the potential to redefine the way we interact with our world, our technology, and the universe itself. The time has come to awaken to a deeper reality, to see beyond what we have been taught, and to embrace a more profound connection with the cosmos. This is not just a shift in knowledge, it is a transformation of perspective, one that could propel humanity into a new era of limitless possibility. Space is not empty. It is teeming with energy, structure, and potential. What appears to be a vast void is in fact a dynamic and intricate field of fluctuating forces, an invisible framework that underpins all of existence. Modern physics has revealed that the vacuum of space is not a passive absence, but a seething ocean of quantum activity, where particles blink in and out of existence and energetic currents ripple across the cosmos. Within this apparent nothingness lies a profound and untapped potential, an unseen architecture that may hold the key to unlocking entirely new forms of energy, motion, and interaction. Rather than a barren expanse separating celestial bodies, space functions as the very fabric of reality, a medium through which fundamental forces operate and shape the universe. The structure of the vacuum is not uniform, but exhibits fluctuations, densities, and complexities that influence everything from the movement of galaxies to the interactions of subatomic particles. If we learn to understand and manipulate these hidden dynamics, we may gain access to principles of propulsion, energy generation, and even gravitational control that could redefine the limits of human capability. The notion that space itself holds energy is not merely theoretical. The concept of zero-point energy suggests that even in the coldest, emptiest reaches of space, an immense reservoir of energy exists, one that, if harnessed, could revolutionize our technological landscape. What if the key to infinite, sustainable energy does not lie in burning fuels or splitting atoms, but in simply learning to access the latent power of space itself? The universe may not be as distant or indifferent as we once believed. Instead, it is an active, interconnected web of energy, a cosmic blueprint waiting to be decoded. The concept of vacuum fluctuations and their role in shaping gravitational fields is one of the most intriguing discoveries in modern physics. Quantum mechanics suggests that even in the apparent emptiness of space, Fleeting bursts of energy and virtual particles spontaneously appear and disappear at microscopic scales. These fluctuations create a subtle but pervasive influence on the fabric of space-time itself, introducing an ever-present energy field that contributes to the fundamental structure of the universe. In classical physics, gravity is described as the warping of space-time by mass, but recent advancements propose that vacuum fluctuations may play a crucial role in this phenomenon. The temporary emergence and annihilation of virtual particles generate minute distortions in the structure of space, potentially affecting the way gravity operates at both quantum and cosmic scales. Some theories even suggest that these quantum fluctuations may be responsible for the emergence of mass itself, providing a link between gravity and quantum mechanics that could bridge the gap between Einstein's relativity and the principles of the subatomic world. If these fluctuations can be understood and harnessed, they may open new avenues for technological advancements beyond our imagination. The ability to manipulate the quantum vacuum could lead to revolutionary propulsion systems, gravitational shielding, and even methods of altering inertia and momentum without reliance on traditional energy sources. Instead of fighting against gravity with brute force, we may one day learn to work with it, using the hidden dynamics of the vacuum to achieve feats once thought impossible. The deeper we explore the nature of vacuum fluctuations, the closer we come to unlocking a profound and transformative understanding of the forces that shape reality itself. If we could manipulate these fluctuations, the implications for transportation, energy, and even human potential would be staggering. Imagine propulsion systems that defy conventional physics, allowing vehicles to traverse the globe or even deep space without fuel-dependent engines. Instead of being bound by the constraints of combustion and propulsion as we know it, a new class of motion could emerge, one that harnesses the latent energy of space itself, reducing friction and resistance to near-zero levels. In the realm of energy, mastering quantum fluctuations could mean the end of fossil fuels and reliance on finite resources. By tapping into the omnipresent quantum field, we could develop power systems that generate clean, boundless energy, forever changing the way civilization is sustained. The transition from limited extractive energy models to self-sustaining, universally accessible power sources would not only revolutionize industry, but also redefine global economies and the balance of technological progress. Beyond physics and engineering, the ability to control vacuum fluctuations could even have implications for human consciousness and biology. If space-time is a medium through which information and energy flow, could we learn to interact with it directly? Could consciousness itself be amplified, extended, or even liberated from its current limitations? These questions open the door to an entirely new perspective on what it means to be human, positioning us not as passive observers of the universe, but as active participants in shaping its very fabric. The mastery of these hidden forces could mark the dawn of a new era, one where the boundaries of reality are not just understood, but consciously navigated. Gravity at the cosmic level is well understood, yet at the quantum scale it remains a mystery. Gravity has long been regarded as one of the fundamental forces governing the universe, its effects shaping the orbits of planets, the formation of galaxies, and the bending of light across cosmic distances. Einstein's general relativity elegantly describes gravity as the curvature of space-time caused by mass, providing a model that has withstood rigorous testing at macroscopic scales. Yet, despite its success, gravity remains a stubborn enigma when examined at the smallest levels of reality. In the quantum realm, the predictable laws of relativity break down, giving way to a world of probabilities, wave-particle duality, and fundamental uncertainty, while the other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, have been successfully integrated into the framework of quantum mechanics. Gravity resists such unification. Attempts to reconcile these two domains, such as string theory and loop quantum gravity, propose exotic solutions, but no definitive experimental validation has emerged. One of the greatest challenges in modern physics is understanding how gravity operates at the quantum scale. If space-time itself is not a smooth continuum but a fluctuating granular structure at the Planck scale, could gravity be an emergent force rather than a fundamental one? Could quantum fluctuations and the information encoded within space itself hold the key to bridging the divide between classical and quantum physics? These questions push the boundaries of our understanding, compelling us to rethink not only gravity, but the very foundation of reality itself. What if gravity itself is not a fundamental force, but an emergent property of space-time fluctuations? Rather than being a distinct force acting upon objects, gravity may arise as a consequence of deeper quantum processes occurring at microscopic scales. Some physicists propose that gravity emerges from the interactions of quantum information, encoded in the very fabric of space-time itself. If this is true, then space-time is not merely a passive stage upon which physical events unfold, but an active, dynamic medium shaped by the exchange of quantum data. This perspective challenges traditional views and opens new avenues for understanding gravity's elusive connection to quantum mechanics. It suggests that gravitational effects might be a macroscopic reflection of deeper, information-based principles operating at the smallest scales of reality. If gravity is indeed emergent, then by deciphering the quantum structure of space itself, we may one day unlock new ways to influence and control it. Such a shift in our understanding could lead to breakthroughs in propulsion, energy generation, and even the possibility of modifying space-time itself to enable unprecedented technological advancements. The concept of micro-black holes within particles, how this could replace the need for the strong force in physics. Emerging research suggests that what we perceive as fundamental forces might be manifestations of deeper, more intricate interactions within the quantum vacuum. The strong nuclear force, traditionally thought to be responsible for binding atomic nuclei together, may instead be an effect of ultra-small black holes residing within subatomic particles. If protons and neutrons harbor micro-black holes at their core, their immense gravitational influence could provide the binding force that holds atomic structures together, eliminating the need for an independent, strong nuclear force. This paradigm shift could lead to a more unified understanding of physics, integrating gravity seamlessly with quantum mechanics and redefining our approach to nuclear energy and stability. What if energy could be extracted from the fabric of space itself? If space is not truly empty, but instead a vast reservoir of quantum fluctuations and hidden energies, then it may be possible to develop technologies capable of drawing power directly from the vacuum. Unlike conventional energy sources that rely on matter-based fuel or chemical reactions, harnessing vacuum energy could provide an inexhaustible and clean source of power. Scientists have long speculated that zero-point energy, named for its presence even at absolute zero, might one day be converted into usable energy, fundamentally changing the way we power our world. If such an energy source could be controlled and efficiently extracted, the implications would be revolutionary. It could eliminate dependence on fossil fuels and end energy scarcity and enable a new era of technological advancement. Vehicles could operate indefinitely without refueling, entire cities could be powered without environmental cost, and deep space travel could become a reality without the burden of carrying massive fuel reserves. Unlocking the power hidden within space itself would not only reshape human civilization, but redefine our relationship with the universe at large. The Casimir effect and its implications for harnessing zero-point energy. The Casimir effect is one of the most tangible demonstrations of vacuum energy, illustrating how quantum fluctuations exert a measurable force even in the absence of matter. This phenomenon occurs when two parallel conducting plates are placed nanometers apart in a vacuum, creating a pressure differential due to virtual particles appearing and disappearing between the plates. The imbalance generates a force that pulls the plates together, revealing the hidden energy inherent in space itself. The implications of this discovery are profound. If vacuum energy can produce a measurable force at microscopic scales, Could it be scaled up for practical energy applications? Scientists and engineers are exploring ways to harness this effect, envisioning new energy systems that tap into the fabric of space itself. The development of zero-point energy technologies could lead to the creation of highly efficient power sources capable of running indefinitely without fuel consumption or waste. Such advancements would mark a paradigm shift in energy production, eliminating the need for traditional power grids and revolutionizing transportation, industry, and space travel. If successful, these innovations could unlock the ability to extract limitless clean energy directly from the quantum vacuum, fundamentally altering our relationship with power generation and sustainability. The Casimir effect stands as a crucial stepping stone towards a future where humanity no longer depends on finite resources, but instead learns to harness the boundless energy woven into the very fabric of existence. If nature operates with such efficiency, could we replicate these principles to power the future? Nature has perfected the art of energy conservation and utilization over billions of years, relying on systems that are self-sustaining, highly efficient, and incredibly resilient. From the photosynthetic processes of plants converting sunlight into chemical energy with minimal waste, to the immense gravitational forces that drive stellar fusion, nature provides a blueprint for how energy can be harnessed and repurposed on an unprecedented scale. If we could decode and apply these mechanisms, we might uncover solutions far beyond our current technological limitations. By studying the way energy is stored and transferred in quantum systems, we could design artificial structures capable of tapping into the fundamental forces of the universe. The Casimir effect, quantum entanglement, and vacuum fluctuations all suggest that the universe itself holds an inexhaustible energy supply, waiting to be unlocked by a deeper understanding of its intricate mechanics. By learning from nature's ability to create equilibrium and sustainability, we could engineer revolutionary energy systems, ones that require no fossil fuels, emit no pollution, and operate continuously without entropy-induced loss. This would mark a turning point in human history, ushering in an era of abundance free from the limitations that have bound previous generations. If the universe itself thrives on efficiency and interconnected energy exchange, then the key to humanity's energy independence may not lie in extracting finite resources, but in learning to harmonize with the natural principles that sustain the cosmos. The cosmic connection: we are more than we think. Every element that composes the human body, carbon, oxygen, nitrogen, iron, originated in the heart of ancient stars. These celestial furnaces fused lighter elements into heavier ones through the process of nuclear fusion, gradually creating the building blocks of life as we know it. When these stars reached the end of their lifetimes, they exploded in magnificent supernovae, scattering these enriched elements across the cosmos. Over billions of years, these elements coalesced into new stars, planets, and ultimately the complex life forms that now populate Earth. This profound connection between humanity and the stars is not merely poetic, it is a scientific truth that reshapes how we perceive our existence. The iron in our blood, the calcium in our bones, the very air we breathe, all were once part of celestial bodies that burned brightly in the vast reaches of space. We are quite literally made of stardust, interwoven with the universe in a way that transcends time and distance. Recognizing this connection challenges the notion of separation. We are not isolated beings, confined to a single planet, but rather participants in a grand cosmic cycle where matter is continuously transformed and repurposed. The energy that flows through us has journeyed across galaxies, linking us to the birth of stars, the formation of planets, and the unfolding of life itself. If the universe has brought us into existence through such intricate and harmonious processes, what greater potential lies within us? Understanding our cosmic origins not only fosters a sense of unity with the universe, but also invites us to explore our own place within it. Could the same forces that created galaxies and nebulae be at work within us, guiding our evolution, shaping our consciousness, and unlocking abilities we have yet to discover? By acknowledging our celestial heritage, we begin to see ourselves not as mere inhabitants of Earth, but as cosmic entities, expressions of the universe itself, capable of transformation, exploration, and boundless discovery. The universe is not something separate from us. It is within us, around us, and flows through every atom of our being. As we continue to uncover its secrets, we may also come to understand the vast potential that lies dormant within ourselves. Modern physics suggests that our universe may not be what it seems. The holographic principle, a concept rooted in theoretical physics, posits that all information contained within a three-dimensional space can be fully described by data imprinted on a lower dimensional boundary. This theory first emerged from the study of black holes, where researchers discovered that the information about everything falling into a black hole could be encoded on its event horizon, a two-dimensional surface surrounding it. If this principle applies to the cosmos, then everything we experience as reality might be the projection of a deeper underlying structure. Evidence for this idea has surfaced in various fields of physics. Research into quantum entanglement, where two particles, regardless of distance, remain mysteriously interconnected, hints at a universe where locality is an illusion. Experiments studying the cosmic microwave background radiation, the afterglow of the Big Bang, suggest patterns consistent with a holographic imprint of the universe's formation. Additionally, in string theory and quantum gravity models, the concept of a holographic reality continues to gain traction as a way to reconcile quantum mechanics with the vastness of cosmic phenomena. If the universe is indeed holographic, it radically reshapes our understanding of existence. It suggests that what we perceive as physical space and time may be emergent properties of a deeper informational substrate. This notion aligns with ancient philosophical and spiritual traditions that have long hinted at the illusionary nature of reality. More importantly, it challenges us to reconsider the limits of our consciousness and perception. Could it be that our very thoughts, emotions, and awareness are part of this grand cosmic projection? If so, understanding and harnessing this principle could unlock new frontiers in science, allowing us to manipulate reality in ways we never thought possible. From advanced computing to breakthroughs in artificial intelligence, the implications of a holographic universe extend beyond physics. They reach into the very nature of human potential and the way we interact with the world around us. As science continues to explore the relationship between mind and matter, growing evidence suggests that human consciousness may not be separate from the universe, but rather an intrinsic part of its structure. Quantum mechanics has already demonstrated that observation can influence the outcome of physical events, as seen in the famous double-slit experiment. This raises profound questions about the nature of consciousness and its role in shaping reality. The idea that the universe and consciousness are interconnected is further supported by research into quantum entanglement, where two particles remain linked regardless of distance, instantaneously affecting each other. If such a mechanism operates on a fundamental level of reality, it could imply that our thoughts, emotions, and awareness are similarly entangled with the cosmos itself. Some physicists suggest that consciousness may be a fundamental force, woven into the very fabric of space-time, rather than an emergent property of the brain. Ancient philosophical traditions have long proposed that human awareness is a reflection of the greater whole, mirroring the interconnected nature of existence. In modern scientific discourse, theories like panpsychism suggest that consciousness is not exclusive to biological organisms, but is a fundamental aspect of the universe. If this is true, then our perception of reality is not merely a passive experience, but an active, participatory engagement with the cosmos. Understanding this profound link between consciousness and the universe could unlock new frontiers in both science and personal development. It could lead to advancements in artificial intelligence, neuroscience, and even space exploration by redefining how we approach the very essence of life and intelligence. If we are, in essence, expressions of a self-aware universe, then our potential is not bound by the limitations we have traditionally imposed upon ourselves, but instead extends as far as the cosmos itself. Many revolutionary ideas were initially ridiculed before reshaping science. Throughout history, new ways of thinking have often been met with skepticism, resistance, and even outright hostility. Galileo's assertion that the Earth orbits the Sun was condemned as heresy, yet it ultimately laid the groundwork for modern astronomy. Einstein's theories of relativity were once considered radical, but have since become foundational principles of physics. Even the notion that microscopic organisms cause disease, a concept we now take for granted, was initially dismissed by the scientific community. Every significant shift in human understanding has faced opposition, yet time and evidence have proven that progress is born from challenging established beliefs. The ideas that push the boundaries of conventional thought are often those that unlock new frontiers of knowledge. The question we must ask ourselves is, what modern theories and discoveries are being dismissed today only to be accepted as undeniable truths in the future? If history teaches us anything, it is that the pursuit of knowledge demands courage, curiosity, and an openness to explore beyond the limitations of current paradigms. What seems impossible or fantastical today may be the foundation of tomorrow's reality. By embracing this mindset, we create the space for transformative discoveries that can redefine not just our understanding of the universe, but our place within it. Society often resists change, but true progress demands a shift in perspective. The inertia of conventional wisdom has always been one of the greatest barriers to innovation. Whether in science, technology, or philosophy, humanity tends to cling to familiar frameworks, hesitant to abandon deeply ingrained beliefs. However, every major leap forward has required a willingness to embrace the unknown. The transition from the geocentric to the heliocentric model, the discovery of quantum mechanics, and even the acceptance of artificial intelligence all faced fierce opposition before transforming our world. History has shown that those who dare to question prevailing doctrines often pave the way for the most profound advancements. Progress is not the result of passive acceptance, but of relentless inquiry, where the boundaries of possibility are continuously redefined. By cultivating open-mindedness and fostering curiosity, we ensure that the next wave of discoveries, no matter how unconventional, has the chance to reshape the future of our civilization. Will we remain bound by outdated models, or dare to embrace a deeper truth about our reality? The decision to move beyond old paradigms is not merely an intellectual challenge, but a fundamental shift in how we perceive existence itself. If history has shown us anything, it is that true breakthroughs come from those willing to see beyond accepted limitation. The mysteries of the universe remain vast and largely unexplored. Will we continue to dismiss what we do not yet understand? Or will we step forward into the unknown, ready to redefine what is possible? Technology alone is not enough. The consciousness behind it determines its impact. While scientific advancements have propelled humanity forward, history has shown that technology is merely a tool. Its true influence depends on how it is wielded. Nuclear energy, for example, has the potential to power entire cities or unleash devastating destruction. Artificial intelligence can revolutionize industries or lead to ethical dilemmas that redefine the workforce and human identity. It is not the technology itself that defines the future, but the intention, awareness, and wisdom behind its use. For civilization to progress sustainably, technological evolution must be accompanied by a deeper shift in human consciousness. Knowledge alone is insufficient without wisdom, and scientific breakthroughs without ethical consideration risk leading humanity down dangerous paths. A holistic approach, one that integrates technological progress with an expanded awareness of interconnectedness, will determine whether we use these advancements to elevate or endanger our existence. The future is not dictated by science alone, but by the conscious choices we make in how we apply its discoveries. Our unified physics could lead to interstellar travel, sustainable energy, and an evolved human experience. The exploration of quantum mechanics, relativity, and the structure of space-time has unveiled a new frontier, one where the traditional boundaries of energy, propulsion, and material limitations may soon be transcended. If we can harness the fundamental forces that shape the universe, interstellar travel may become more than a distant dream. It may be a tangible reality. The unification of physics, particularly in understanding gravity at both cosmic and quantum scales, holds the key to propulsion systems that defy conventional rocketry. Concepts such as warp drives, gravitational field manipulation, and quantum energy extraction could enable humanity to traverse vast distances without the need for inefficient chemical fuels. With access to limitless energy sources embedded in the fabric of space itself, we could free ourselves from the constraints of fossil fuels, unlocking an era of ecological balance and technological abundance. Beyond the physical realm, a deeper understanding of the universe may lead to an evolved human experience, one where our perception of reality expands alongside our scientific achievements. If consciousness and the cosmos are indeed intertwined, then the next stage of human evolution may not be limited to biological advancements, but also to an expansion of awareness. A civilization that masters the physics of the universe may also unlock untapped cognitive abilities, redefine the limits of perception, and elevate the collective human experience to a higher state of understanding. We stand on the edge of a new era, one where we redefine our place in the universe. The convergence of science, consciousness, and technology is not merely a possibility, it is an inevitable step in human progress. The question is no longer whether we will uncover the deeper workings of reality, but whether we will have the courage to embrace them. Will we continue to perceive ourselves as limited beings bound to a single planet, or will we awaken to the vast potential that lies before us? The choice is ours. The future is not predetermined. It is shaped by our willingness to explore, to challenge, and to evolve. If we dare to step beyond the confines of outdated paradigms and embrace the limitless nature of existence, we may find that the universe has been waiting for us all along. Our journey is just beginning, and the greatest discoveries are yet to come. The time for transformation is now. The discoveries unfolding before us are not just scientific curiosities. They hold the potential to revolutionize the way we live, think, and interact with the universe. Yet knowledge alone is not enough. True progress requires action, a collective effort to integrate these insights into our technological, societal, and personal evolution. Knowledge is only the beginning. Action and awareness will shape the future. Throughout history, civilizations have risen and fallen based on their ability to adapt to new paradigms. Today, we stand at the threshold of the most profound shift in human understanding, but whether we step forward or remain anchored to outdated beliefs will define the trajectory of our future. By fostering curiosity, open-mindedness, and a willingness to explore beyond traditional boundaries, we can bridge the gap between scientific discovery and practical application. What kind of legacy will we leave for future generations? The choices we make today will echo throughout history, shaping the world that our children and their descendants inherit. Will we build a society rooted in sustainable energy, limitless exploration, and interconnected awareness? Or will we cling to systems of division and scarcity that limit our collective potential? The responsibility lies in our hands. Will we choose a path of division and limitation, or one of unity and infinite possibility? The universe is waiting, not for a passive audience, but for active participants willing to explore, question, and create. The future is not a predetermined outcome, but a canvas upon which we paint our destiny. The time has come to embrace the unknown, to challenge what we believe is possible, and to step into a future that reflects the boundless potential of existence itself. Have you ever had a day where you woke up feeling drained before even doing anything? No heavy lifting, no crisis. But somehow your energy's gone, like someone left the faucet running all night. It's easy to blame it on age, stress, or not sleeping well, and sometimes that's true. But more often than not, the problem isn't that you've run out of energy. It's that you're using it in ways that don't serve you. You're burning fuel just trying to stay in your own lane. Right now, at this exact moment, your body is alive with signals. Your skin feels the texture of your shirt. Your ears are picking up faint background sounds. Your nervous system is reading your posture, your breath, the light in the room. Your brain is tracking all of this and more without you even noticing. It's working overtime behind the scenes, filtering out anything that doesn't seem urgent. And that's the catch, because the same system that helps you focus is also quietly shutting out the parts of life where energy lives. Let's pause here. Most of us don't have an energy problem, we have an awareness problem. We walk through the day with our minds spinning in loops, memories, deadlines, problems to solve, and in that mental noise we lose connection to the body, to the moment, to what's actually here. It's like driving a car with the parking brake on. The engine's fine, the tank is full, but something's holding you back, and you don't even realize it. You weren't always like this. Think back to learning something new, riding a bike, swinging a bat, using a new tool. At first it felt weird. Your hands didn't know what to do, your body wasn't on the same page as your mind. But slowly, with repetition, it started to feel natural. What happened? You didn't just get better. Your brain literally reorganized itself to support what you were practicing. That's how energy flows. It follows the pathways you train, and if you've spent decades training stress, tension, and overthinking, guess what shows up? Disconnection, fatigue, frustration. The good news, you can change it. Your system already knows how to recharge. Your body already knows how to balance. You just have to stop interrupting it. Here's where it begins. Right now, take 5 seconds. Feel your feet on the floor. Feel your breath move in and out. Don't try to fix it, just notice. That's it. What you're doing in that simple act is redirecting your energy from autopilot into presence, not in a spiritual way, in a neurological way. Because the moment you shift your attention inward, you start accessing a deeper reservoir of energy that's been there all along. In the next section, we'll look at what this energy actually is, not in theory, but in real, observable terms. Because once you understand how energy works inside you, you'll stop looking for more of it and start unlocking what's already yours. Let's talk about energy, not in the vague, mystical sense, not as a buzzword. Let's talk about it in the most literal, physical way possible. Strip everything down. Your skin, muscles, bones, organs, and what's left? Atoms. But here's the wild part. Atoms aren't solid. They're 99.9999% empty space. What's in that space? Vibration, frequency, movement. What you think of as matter is just energy holding form. That means your body is energy. Your brain waves are energy. Your emotions, also energy. Electrical, chemical, hormonal shifts that move through your system like waves. So when you say, I'm out of energy, what you really mean is, my system isn't flowing the way it's meant to. It's like a river that's been blocked by fallen trees. The water is still there, but it can't move, and when energy can't move, you feel stuck, heavy, tired, numb. But that also means something else. If your energy can get stuck, it can also get unstuck. And you don't need fancy rituals or equipment to do it. You just need to understand how to work with what's already in motion. Here's a simple truth. You are always interacting with energy. Most of the time, you're just not aware of it. You walk into a room and feel tension before anyone says a word. You meet someone and immediately sense trust or distrust without logic. You hear a song and your mood shifts in seconds. That's not imagination. That's energetic sensitivity. Your nervous system is reading signals beneath the surface. The question isn't whether you're tuned in. You already are. The real question is, what have you been trained to ignore? See, modern life teaches us to live from the neck up. We think our way through everything. We plan, we analyze, we solve. But in doing that, we lose connection to the rest of the system. Your body is constantly giving you data through breath, posture, heartbeat, tension, warmth, stillness. But if you're not paying attention, it gets filtered out. And when that happens over time, you become disconnected from your own energy field. You're still operating, still functioning, but only at a fraction of your capacity, It's like driving a high-performance car with the engine locked in first gear. Here's a way to test it. Right now, shift your attention to the space just around your body. Not your thoughts, not your muscles, just the space. Can you sense any tingling in your hands, any pressure around your head or chest, a subtle shift in warmth? Those signals are always there, but your mind's been trained to overlook them. You're not creating energy by doing this. You're simply noticing it for the first time in a while. This is the beginning of working with energy, not in a mystical sense, but in a deeply practical one, because the more fluent you become in sensing your own field, the more you can adjust it, not with effort but with awareness. You don't need to force your energy to move, you need to remove what's blocking it. That starts with attention, then intention, then practice, in that order. In the next section, we'll explore how your mind is shaping what you feel, not just emotionally, but physically. You'll see how the filters in your brain determine what you experience and how they can be changed, not by doing more, but by seeing more. Let's continue. Here's something most people never stop to consider. You don't see reality, you see what your brain allows you to see. Let that land for a moment. Everything you experience, from your surroundings to your sensations, even your sense of self, is filtered through a lens built from years of habit, memory, and belief. And that lens? It's selective. Your brain is bombarded with over 11 million bits of data per second, but it only lets through a few dozen. The rest, it throws away. Why? Because your brain isn't built for truth. It's built for efficiency. It wants to keep you safe, it wants to keep you familiar, and it wants to keep you focused only on what you've learned to care about. So it tunes out anything that doesn't fit your current model of the world. Think of it like this. When you buy a new car, you start seeing that model everywhere. Not because there are suddenly more of them, but because your brain just made them relevant. Before, they were invisible. Now, they pop out. This is called selective attention, and it's happening all the time. Not just with cars, but with people, opportunities, emotions, even with your own body. If you've been trained to see stress as normal, your brain will filter the world through that lens. If you've learned to expect disappointment, you'll start overlooking anything that doesn't match that story. And most importantly, if you've been conditioned to ignore subtle signals like shifts in energy, intuition, tension, or flow, your brain will filter those out too. The signal was always there, you just weren't tuned to it. Here's a strange but powerful example. If you shine blue light on a yellow banana, technically your eyes should see green, but your brain knows bananas are yellow, so it overrides the input. It doesn't show you what your eyes see, it shows you what it expects. That's how powerful the filter is. Now imagine that same filter applied to how you feel in your body. If you believe you're tired, your brain will downplay signals of vitality. If you believe you're stuck, your nervous system will tighten in ways that reinforce it. But here's the good news. What your brain learned to ignore, it can also learn to notice. And that changes everything. Let's do something right now. Take 5 seconds, look around the room. Slowly, notice textures, light, color, shadow. Now, close your eyes for a moment and ask yourself, what did I miss? Most people realize they were only half seeing, they were looking without noticing. That same principle applies internally. You go through the day experiencing tension, fatigue, or disconnect, but never really turning toward it. The more you practice this noticing, the more detailed your inner world becomes, not because it changed, but because you did. This is how you begin to reclaim your energy, not by doing more, but by seeing differently, because when you shift perception, you shift access, and when you shift access, you shift power. In the next section, we'll go even deeper into the observer effect. You'll see that you're not just watching your experience unfold, you're shaping it with every thought, focus, and breath. Let's get into it. Here's something that sounds like science fiction, but it's confirmed by physics, psychology, and your own experience. The moment you observe something, you change it. At the quantum level, this is called the observer effect. When scientists try to measure a particle's behavior, it doesn't act the same as when no one's watching. It's not just spooky theory, it's proven, repeated, and measurable. Tiny particles behave differently depending on whether or not they're being observed. So what does that have to do with your daily life? Everything. Let's bring it down to earth. Have you ever had pain in your body and it wasn't that bad until you focused on it? Or maybe you were feeling fine until you started thinking about being tired. You noticed it and suddenly it got bigger. The same happens with emotion. You catch a passing irritation, and the moment you name it, "I'm frustrated," you feel it spread like heat in your chest. That's not your imagination. That's the observer effect playing out in real time. But it doesn't just amplify what you notice, it can also transform it. Think about a moment where you stepped back from anger, not suppressing it, but seeing it clearly. This is just a part of me reacting. I don't have to follow it. That slight shift in awareness from being inside the emotion to observing it changes your relationship to it. Suddenly, you're no longer a puppet of that feeling. You're a participant in how it moves. That's real power. Here's the shift. You are not a passive spectator in your experience. You are part of the system, an active influence on what unfolds. Your attention is not neutral, it carries intention, even if you're not conscious of it. What you focus on becomes stronger, what you ignore becomes weaker, and what you observe with curiosity, not control, begins to move in more intelligent ways. Try something now. Take a breath. Let your body settle. Now bring your attention, not to your breath, but to the space around your breath, not the inhale, not the exhale, but the stillness just before the inhale and just after the exhale. That's where presence lives, not in the doing, but in the space between. And when you observe that space, something strange happens. Your breath naturally deepens, your body softens. You didn't try to change anything, but something changed anyway. That's the observer effect. So what does this mean for your energy? It means that the moment you start paying attention to where your energy is stuck, tension in the jaw, pressure in the chest, weight in the limbs, you're already creating the conditions for it to shift. You don't have to fix it. You don't have to push. You just have to notice with intention. This is why energy practices aren't about magical techniques or superhuman focus. They're about the quality of your attention. A relaxed awareness is more powerful than a strained effort. A curious mind unlocks more than a controlling one, because the act of watching is also an act of creation. In the next section, we'll look at how your brain literally rewires itself based on what you observe and repeat, and how that unlocks energy patterns that once felt You're not stuck. You're just running old code. Let's learn how to write something new. Let's clear something up. You're not too old to change. Your brain didn't stop growing at 25. You're not locked into the patterns you've been running for decades. The science is clear. Your brain is adaptable every single day of your life. This isn't motivation talk. It's hard neuroscience. It's called neuroplasticity, your brain's built-in ability to rewire itself based on how you think, feel, move, and focus. Let's break it down. Every time you repeat a thought, a behavior, or even a posture, you strengthen a connection in your brain. It's like hiking through grass. At first, there's no path, but the more you walk the same trail, the clearer it becomes. Eventually, it turns into a road, then a highway. That's how habits form. Not just behavioral habits, energetic and emotional ones too. If you've spent years carrying tension in your shoulders, worrying about the future, suppressing how you feel, ignoring your body, your brain has made those things normal. Not good, not bad, just familiar. And familiar equals default mode. The good news? You can build new defaults. You can train your brain to prioritize presence over pressure, clarity over chaos, flow over force. But here's the key. You don't do it by pushing harder. You do it by repeating different inputs with intention. Think of learning to play an instrument. At first, it's awkward. Your fingers don't cooperate, your timing is off, but you keep at it. You don't force mastery, you build patterns. Through focus, feedback, and repetition, your nervous system adjusts, and over time, what was clumsy becomes natural. Energy awareness works the same way. Let's test something now. Sit still, bring your attention to your body, not just one part, but the overall sense of how it feels. Now, slowly scan. Is there tension in your jaw? Are your shoulders lifted without realizing it? Are your legs clenched even while sitting? Now, release just one of those. No big effort, just a small letting go. That's not a stretch, that's not a breathwork hack. That's your nervous system repatterning in real time as soon as you bring awareness to it. You do that consistently and the brain takes notice. It starts to say, oh, we don't need to hold that tension anymore. We don't need to rush through every moment. We don't have to filter out calm or ease or energy. It rewires, bit by bit, not all at once, but layer by layer, just like how it built your old patterns. And this is important. Rewiring doesn't require perfection. It requires consistency. 10 seconds of clear attention is worth more than an hour of forced focus. Awareness with softness rewires faster than control with pressure. In the next section, we'll talk about what happens when you stop fighting your energy and start cooperating with it. Because the truth is, your system already knows how to heal, how to move, how to flow. You've just been getting in the way. Let's change that. Let's talk about something most men are never taught. You don't need to fight harder, you need to align better. We've been conditioned to believe that more effort equals more results. Push through, power up, grind it out. And yes, there's value in discipline, in strength, in showing up when it's hard. But when it comes to energy, especially the kind that fuels your inner world, force is the wrong tool, because energy doesn't respond to pressure, it responds to permission. Picture this. You're standing in a river. The current is strong. You want to move forward. You have two options. One, fight the current, struggle, waste strength trying to overpower the water. Two, step into the flow. Let the current carry you while you guide your direction. Most people live in option one, tension, resistance, burnout. But energy wants to move. If you stop blocking it, let's go deeper. Everything in your body, from your heartbeat to your hormones to your breath, is part of a system that thrives on rhythm, not rigidity. Your lungs expand and contract, your muscles contract and release. Even your thoughts cycle waves of attention and rest. Trying to fix your energy by forcing focus or ignoring fatigue, that's like holding your breath and wondering why you feel dizzy. True energy control isn't control at all, it's cooperation. Think of a surfer. He doesn't move the wave, he studies it, times it, aligns with it, then rides it with minimal effort, maximum intelligence. That's the same posture you need with your own energy. Not dominance, not avoidance, just attunement. Let's bring this into daily life. Ever tried to solve a problem late at night, exhausted, forcing yourself to think? You pace, you pressure, you grind, and nothing comes. But the next morning, calmer, clearer, the answer arrives with ease. That's energy intelligence at work, not doing more, but working with the moment. You can apply this same principle to your body. Try this. Close your eyes for a few seconds. Bring your attention to your breath, not to change it, just to track it. Then ask, where is the breath moving freely? Where does it feel tight or shallow? What happens when you simply notice without trying to fix? More often than not, the moment you stop interfering, the system begins adjusting on its own. That's how self-regulation works. Not through force, through space. There's a reason ancient practices like Tai Chi, Qigong, martial arts and breathwork all center on working with energy, not wrestling it. They weren't built on fantasy, they were built on observation. Thousands of years of watching how the body, breath and mind interact when brought into alignment, and all of it points to the same truth. Energy flows where resistance fades. Energy stabilizes when awareness returns. Energy renews when effort stops being the answer. This doesn't mean you stop working hard. It means you start working smart, especially with yourself. The mind is powerful, yes, but it's most powerful when it listens to the body, not when it bulldozes over it. In the next section, we'll explore what might be the biggest illusion of all, the belief that you're separate from the energy you're trying to control. Because the moment you stop seeing yourself as an outsider is the moment you stop chasing alignment and start embodying it. Let's take that step together. Most people go through life feeling like they're on the outside, separated from peace, from power, from clarity. It's the unspoken mindset we're handed from a young age. You have to go out there and find it, work for it, fight for it, chase it. Success, confidence, purpose, even energy. We're taught that it's somewhere else and we have to earn it. But what if the real shift isn't chasing harder, but realizing that you've never been separate from what you seek? Think about this. You're not living on top of the earth, you're living within it. You breathe its air, you drink its water. The calcium in your bones, the iron in your blood, they came from the stars, literally. Supernova debris built into your body. You're not standing apart from the system, you are the system, one expression of it, in human form. That's not philosophy, that's biology, that's physics. And yet, most people live like outsiders to their own lives. We treat energy like a tool we have to plug into, like it's somewhere else, out there, beyond reach. But the truth is far more powerful. You are energy, your thoughts are vibrations, your emotions are currents, your breath is a tide, your body is a field of shifting signals, always in motion. The illusion is thinking you have to do something to become part of it. You're already in it, you always have been. So here's the invitation. Stop standing at the edge of the river trying to control the current. Step in, feel the movement, let it carry you, then guide your direction from within the flow. Because when you stop resisting life's natural rhythm, you don't lose power, you gain access. Here's a practice for today. Take a moment, sit quietly. Don't focus on breath or body, instead focus on space. The space in the room, the silence between sounds, the stillness underneath your thoughts. Now ask yourself, where do I end and the world begins? Where does my energy stop and everything else start? If you really tune in, the boundary gets blurry. You start to feel less like a separate self and more like a wave on the ocean, not apart from it, part of it. That's not disempowering, it's liberating, because it means you don't have to hold it all together. You just have to remember you're not alone in it. The most powerful people, athletes, artists, leaders, they don't control energy like a puppet master. They move with it, they learn its language, they listen, they adjust. And when the moment comes, they act from connection, not tension. You can do the same, not by becoming someone else, but by letting go of the idea that you're separate from what already lives inside you. You've made it this far, not just through the words, but through the process of remembering, because none of this is new. Your body already knows how to align, your breath already knows how to balance, your mind already knows how to shift. You just needed space to hear it again. So now the question becomes, what do you do with this? It's tempting to want a big change, some lightning bolt moment where everything clicks and nothing's the same. But energy doesn't work like that. It works in rhythm, in small movements, in subtle awareness, in choices made again and again, even when no one's watching. You don't need to redesign your life in one day. You need to start noticing, consistently, gently, honestly. That's where the real power lives. Here's how you begin. Step 1. Anchor yourself in the body. A few times each day, stop what you're doing for 10 seconds. Feel your feet. Notice your shoulders. Check in with your breath. Not to change it, just to witness it. No drama, no performance, just presence. You're telling your system, I'm here, I'm listening, let's reset. Step 2. Use your attention like a tool. You now know that what you focus on, you amplify, so start directing your attention on purpose. If you're feeling overwhelmed, bring it to your breath. If you're scattered, bring it to one simple action. If you're numb, bring it to sensation. Your hands, your chest, the space around you. This is how you reclaim energy without forcing it. Step 3, choose rhythm over rigidity. You're not a machine, you're a living system, designed to rise, fall, reset, and rise again. Don't expect non-stop intensity. Don't chase peak state all day. Instead, find your natural tempo. Work, rest, reflect. Action, pause, integration. You'll get more done with half the stress, and you'll feel better while doing it. Step 4, practice awareness without judgment. This is key. Most people stop themselves before they even begin because they expect mastery instead of progress. You're going to get distracted, you're going to fall back into old patterns, you'll forget, then remember, then forget again. Good. That's part of it. Each time you come back, without shame, without story, you reinforce the path. Over time, that path becomes a new default, and that's how change becomes real. Step 5, live the question. Don't rush for answers. Instead, hold this question in your daily life. Where is energy trying to move in me right now, and what's getting in the way? Sometimes the answer is physical, tightness, fatigue. Sometimes it's emotional, old frustration, fear, grief. Sometimes it's mental, overthinking, resistance, expectation. You don't need to fix it, you just need to listen. That listening is the healing. So here we are. You've learned that your energy isn't missing, it's misdirected. That your brain is filtering your reality and you can rewire what it notices. That your attention is not passive, it's powerful. That you're not separate from energy, you are made of it. Now you begin to live it, not as a theory, but as a daily return to presence, to rhythm, to awareness. Because the truth is, you don't need more energy, you need fewer blocks, and you don't need to force yourself into becoming someone new. You just need to stop forgetting who you already are. The door is open. Take the first step.